Welcome students. In this pre-calculus course, you will be learning the following topics. Foremost, we will start off with Introduction to Number System, where we will study and understand the existing number system that is required for this course. And then we will go on to Order of Operation, where we will learn about the Bedmar's rule, and then understanding what exactly is the interval notation and why is it important. And we will also learn how to combine intervals, and we will also understand the importance of absolute function, finding distance between 2 points, the graph of the absolute function. We will learn how to exactly draw the graph. We will also understand the meaning of piecewise and how a piecewise function is defined. We will understand the inequalities involving absolute values, and we will also go on to learn about fraction arithmetic and solving fractions involving multiplications, fractions involving divisions, and then we will go on to exponents and understand them. And also we will learn about some of the pitfalls that we need to avoid while dealing with radicals. We will also deal with some problems involving exponents, and then we will start off with the introduction to lines, and we will also understand about slopes, expanding the given expression by means of FOIL method, and then comparing it with the distributive techniques that are also there. We will also understand some of the examples of applying the distributive property, and then comes binomial theorem, where we will understand how to obtain expressions of different indices. And then we will also come across the Pascal's triangle and how exactly using the Pascal's triangle we would be able to obtain expansions of higher powers in the binomial theorem. And then we will give an application for Pascal's, and then followed by introduction to polynomials, types of polynomials, examples of expressions which are not polynomials, examples of polynomials with irrational coefficients, and then we will come to factor theorem, where we will also understand the rational roots theorem. We will also study some examples of rational roots theorem and the related applications. We will also learn about the advantage of using rational roots, and then we will come into quadratic functions. In quadratic functions, we will learn about how to use the vertex form and then intercept form, and how exactly the vertex form and the intercept form are different. And then we will learn about the difference of squares formulae, and then the difference of cubes, followed by factoring by grouping, and how exactly we can use this technique in solving or simplifying polynomial expansions and expressions, and then solving quadratics which are in disguise, and then followed by polynomial inequalities, and then solving cubic inequalities. And then we will come to rational functions and learn about the rational functions with some good examples, and then simplifying rational expressions and expansions, finding the domain of a rational function, and then we will do some review on functions, followed by classifications of functions, and then introduction to multivariate functions and why exactly multivariate functions are there, and some related examples of types of functions to be expected, and then why exactly we are to study functions and how functions are related in calculus. And then we will understand the domain and range and how a function is represented symbolically. And then we will also understand the distinction between domain, codomain, and range, which is very much important. And then examples of two elements going to the same element in the codomain, an example of one element going to two elements in codomain. And then we will understand the function notation and how to obtain the functional value for any given y of the form x positive h, where h is a small increment. And then we will also understand how to represent the domain of a rational function. And then coming to functions and graphs, we will understand the definition of a graph, and then understanding why assigning values and plotting a graph is inefficient way, and why there is a efficient way to handle these things. and then how to obtain the domain for addition and subtraction of functions, and how to obtain the domain for multiplication of function, and then followed by how to obtain the domain for division of functions, and understanding composition of functions, example to understand the composition of functions, and then we will come to understand how to obtain the domain for composition of functions. And coming to the inverses, we will understand how exactly to find the inverses of functions and the necessary condition for an inverse to exist for a function. And then we will also perform some examples where composition of inverses are there as the main topic, and then the necessary condition required for inverses to exist. And then we will also learn about some injective functions and the condition for inverses to be present, as I mentioned to you earlier, and then how to find the inverse of a function, how to perform the check to validate the existence of an inverse function, and then a most important topic, which is introduction to exponential functions, and define an exponential function, graphing an exponential function, understanding horizontal asymptotes and condition for which the function will dip towards the right side of the x-axis. We will also understand some variation in vertical shifts, condition for a vertical stretch, condition for horizontal stretch, and then we will also understand what are logarithmic functions, and then graphing a logarithmic function, important properties in common logarithms, important properties in natural logarithms, understanding the domain and the range of a logarithmic function, examples, finding the domain and vertical asymptotes for logarithmic functions, important graphs of polynomials, examining the graphs for odd powers of x, examining the graphs for even powers of x, understanding the end behavior of the graph, understanding asymptotes, understanding horizontal asymptotes, learning about vertical asymptotes, how to identify a vertical asymptote, and then we will also understand how to find the holes in a function, understanding the vertical line test and how to perform. And then we will come to transformations. We learn about horizontal transformations, vertical transformations, and then coming to trigonometry, we will learn how to draw the graph of sin x, how to draw the graph of cos x, how to draw the graph of tan x, how to draw the graph of cot x, and then we will also understand the right angle ratios, understanding the Pythagoras formula and how to use it in distance formula and extract the formula for distance between 2 points. And then we will learn about the unit circle, and then why theta is measured in radians, and complete the unit circle coordinate system. And then extending trigonometry, we will learn about the compound angle formula, the power reduction formula, and finally with power reduction formula we will complete the course. And then we will move on to doing calculus. So this is the exact course structure for the pre-calculus students, and I wish you the best.
Welcome students, we are starting off the pre-calculus course with the introduction to the number system. Now foremost we got to know the different types of number systems we have got. And the first and foremost, the number system is called as natural numbers. Now these natural numbers is also called as God-given numbers, and they are represented by this symbol, and the numbers, they start from 1 and go on to infinity, 1, 2, 3 and so on up to infinity. The next system is called as the whole numbers, and they are represented with this symbol called as W with a strike there, and they start from 0 and followed by 1, 2, 3 and they go up to infinity. Now the addition between the extra thing that appears in whole numbers is that from natural numbers is the presence of this 0 element. So 0 is the addition for the whole numbers, and after the whole numbers we have got what is called as integers. Now integers are divided into two classes. So one is set of all positive integers and the other is the set of all negative integers. And when we write the set of all integers, we have the set to be from negative infinity, and they go all the way to negative 1, followed by 0, 1, 2, and to positive infinity. So this is the set of all integers. Now, after the set of all integers, we got what is called as real numbers. Now, real numbers, they are two different divisions in real numbers, and the one division is called as the set of all rational numbers, and the other one is called as set of all irrational numbers. Now, in rational numbers, we have a definition. So any number of the form p divided by q such that q is not equal to 0 is defined to be a rational number. So have that in mind. Examples of rational numbers can be 2, because I can always write 2 as 2 over 1 with 1 not being equal to 0. So in that manner, 1 over 2 is also a rational number, and so on and so forth. But in case of irrational numbers, any number which cannot be written, that is the definition, which cannot be written in the form p over q, where q not equal to 0, is called an irrational number. So have that in mind. So in general, how do we define irrational number? In short, I can say a number which has no repeated patterns is called an irrational number. So in other words, if I were to take 1 over 3, 1 over 3 is a rational number. For the very fact, when you divide 1 by 3, you would get 0.3, and the 3 will be repeating itself. So that is why we call this to be a rational number. Now, root of 2, this is an irrational number. Now, for the fact that if you were to take the root of 2, you would end up something like this, 1.4, and the number would stretch on, it goes on. And if you want to be specific, the value for root of 2 is going to be 1.41421356237, and it will be going on. So this is clearly an irrational number because we are not able to get any repeated pattern. Now, next comes, how do we represent symbolically a rational number? How do we do that? So we use the letter Q to represent a rational number. And how do we represent an irrational number? We use the representation Q dash, or you can call it as Q prime. So this is about rational numbers and irrational numbers. Now, in case of irrational numbers, some of the popular examples would be e, pi, pi over e, e raised to the power of log pi. These are all some examples of irrational numbers. After studying the real numbers, we were going to be understanding what is called as a complex number. So complex number is represented in this fashion, in this symbol. Now, in complex numbers, a number of the form, this is the definition, right? A number of the form a positive ib, where a comma b are element of real numbers, and a is called the real part, okay, real part, and b is called as the imaginary part, is defined to be a complex number. Examples can be 3 positive 2i, 2 negative 3i, even numbers of this fashion. 5 is also a complex number because I can always write 5 as 5 positive 0i, right? And 21i, these are all examples of complex numbers. So if you were to give the subset or the hierarchy of numbers, so we got the natural numbers, and then we have the whole numbers, and then we got the integers, and then we have the real numbers, and they all come under, or they are all included in the set of complex numbers, which is the biggest set. So having understood the number system, we'll move on to the next topic, students. So the next we need to understand in precalculus study is what is called as the order of operations, and this is important. Now in calculus we follow what is called as bed mass. Now B stands for brackets, so we would first perform everything and anything that comes inside the brackets, and next is exponents, and after that you got division and multiplication. Now division and multiplication, they offer, in other words, they are on par, so there is no hierarchy there for division and multiplication. And next comes addition followed by subtraction. Now this is very critical. You need to understand and follow the order of operations whenever you are given or whenever you encounter questions like this. Now imagine you are given something like this, say 5 positive 4 multiplied with, say, 5 negative 8 and positive 9 times 3, right? Now if you were to see this, this is complete ambiguity because we have not used the bedmass rule to really give an hierarchy of operations. So whenever we encounter things like this, if we were to go ahead and perform this, we would end up in total incorrect answer. Now, or the operation has to be in this fashion, say 5 positive 4 multiplied with 5 followed by negative 8, so there should be a parenthesis there. So if there is a parenthesis, this would be 8 negative 9 multiplied with 3, or you can just put 3 in this fashion. Now if you are given an expression like this, clearly you know what to do. So 5 positive 4 will be 9. 9 has to be multiplied with 5 followed by 8 negative 9 is going to be negative 1 multiplied with 3, and this is going to be 45 negative negative positive 3, which is going to be 48. So we need to get 48. Now if we were to perform the same thing over here, the answer would not be the same, because if a computer or a programming language were to execute this, it would follow this bedmass rule, and if it does so, in that case the solution is going to be 5 positive 4 times 5 is going to be 20, and then this is going to be negative 8 positive 27, so this would be 25, and this one is going to be positive 19, and the resultant would be 9 with 4 and 1 3 44. 44 is not equal to 48. So you have to adopt extra caution when you are coming to using parentheses and operators. So that's very crucial. Now having mentioned this, if you are expected to enter something like this, say 5 negative 3 divided by 4 negative 9. So in this case you can always adopt a more caution approach by just placing the parenthesis. Now if you don't place the parenthesis, and if you think that okay, it's always okay for me to write it like this in a single line, 5 negative 3 slash 4 negative 9, of course your understanding is that it has to be 5 negative 3 first, and then that has to be divided by 4 negative 9. But when you have a machine to read this, the machine is not going to be reading in this fashion. This is the expected fashion that you wanted, but the machine is not going to be reading in that fashion. The machine is going to be reading in this manner: 5 negative 3 divided by 4 followed by negative 9. But both of them are not the same, because in this case it's going to be 2 divided by 4 negative 9 is going to be negative 5. So the solution is going to be negative 2 over 5. Whereas in this case, if you were to take the LCM of 4, it's going to be 20 negative 3 negative 36, and this can be further simplified as negative 39 divided by 4, which is going to be negative 19 over 4, and this negative 19 over 4 is not equal to negative 2 over 5. Are you following what I'm trying to say? So you have to be cautious whenever you are representing expressions. Specifically, make sure that you are including the parenthesis in the right fashion, because machines are programmed to follow the BEDMAS rule: the brackets first, exponents next, and then the division, multiplication followed by addition and subtraction. So have that in mind. And another important thing you have to know is, whenever you have or you want to use distributive property, say for example you got something like this: 7 negative 3 of say 10 minus 2. Now, by using the property which I just mentioned to you, the BEDMAS rule, right? Now clearly you can clearly use that. So that means it's going to be 7 followed by, first we execute this parenthesis, the quantity inside, and that's going to give me 8. So followed by 7 negative 3 times 8 will give me 24, and if I were to subtract this, I would get negative 17. Now this is following the BEDMAS rule. Now if you were to use the distributive property, now say for example this is the next way, method 2. Now if you got something like this: 7 negative 3 of 10 negative 2, the point where a student will slip is when the distributive negative is carried out. So he or she will write 7 followed by negative 3 times 10 is going to be 30, and they will totally forget the presence of this negative sign and simply write this as negative 6, and then they would say 7 added with negative 30 negative 6 would give me negative 36. So this is going to be negative 29, but this is not the right answer, because they have not considered the negative sign is also getting distributed along with the 3 there. So actually the output should be negative 3 times 10 negative 30, negative 3 times negative 2 should be positive 6. So that would result in 7 added with 6, or you can just add 6 with negative 30. In either of the cases you would end up with 24, which is negative 17. So this should be the answer. So adopt an extra caution when it comes to handling expressions in this fashion. Students, now we will learn about interval notation. We've got different types of intervals. Now, foremost, what I would like to introduce to you is what is called as open intervals. Now, this is represented in this fashion, say with the parenthesis in this manner, a comma b, and if you are saying an x present in a comma b, then using set builder notation I would represent this as x, collection of all x contained in a real number, such that x is between a and b. So please notice this inequality. So this means x cannot take the value a, and on the other side x cannot take the value b. So if I were to mention this as some set, and if I were to represent it on the number line, then it will be something of this fashion. Remember always, towards the left you got negative infinity, and towards the right you got positive infinity. And a and b can lie anywhere in this interval. So if I want to represent a and b, which is an open interval, it is, say for example, let me write a here and b here. Now to represent the extreme points, you should always draw a circle, an open circle like this, a circle which is not shaded. So the meaning of this is x can take all values just before a on the left and all values just before b on the right. So x cannot take a value a or the value b. So that is the meaning of x being present in the open interval. Now next we will have to know what is called as closed interval. Now if I were to have a x element of, we represent closed interval by a square bracket a comma b, and if I were to use the notation to represent, say let me take it as a set, so that notation is going to be x is an element of real number, collection of all x present in the real number, such that x is lying between a lesser than equal to x lesser than equal to b. So the meaning is x can always take the value a or the value b. So on the number line I would represent it in this fashion. On the left I got negative infinity, on the right I got positive infinity, and a and b is over here. Place a circle on a and b, but this time make it shaded. So that shading means the extreme points are included. Now we studied about the open interval, we studied about the closed interval. The next is what is called as half open intervals. So you can call them as half open or half closed. Say for example, if I were to take x being element of a comma b like this. So this means if I were to mention it as a set, x is an element of real number such that x is strictly greater than a but lesser than equal to b. So that is the understanding. So if I were to draw the number line, so negative infinity, positive infinity, and you got a here, you got b here, and x is lying between a and b. So in this case it's going to be a completely shaded point, and this is going to be an open point. So this is half open, so that means a on the side of a we got an open interval. Now the next possibility can be x being element of half closed and half open. So in this case, if I were to write this, x is element of real number such that x is greater than or equal to a but less than b. So this is how we represent the interval. Now having mentioned the half open intervals, we will move on in intervals which includes infinity in this particular class. Now say for example we have something like this, say x element of a comma infinity. So on this side it is closed and this side is open. Now if I were to draw the number line, so this is negative infinity, this is positive infinity, and we got a here. So this is going to be closed on the a side but completely open on the infinity side, and x is over here. Now as we move up, the value of x is going to be increasing. So the smallest value that x can take would be a, but x can also take values that are beyond a. So if we were to represent this using the notation collection of all x element of real number such that x is greater than or equal to a. So this is the notation that we need to use in this case. Now on the other end, if I were to say that x is contained in, or x is element of, say this is the situation then if I were to use the notation, I can write it like this: collection of all x element of real number such that x is actually greater than, right, strictly greater than a. So x is strictly greater than a because x is contained in the open interval a comma infinity. Now we got the next one. Imagine x is present in the negative part of the infinity side, so negative infinity comma b, right? So if it is in this fashion, then if I were to write the set builder notation using set builder, I can say collection of all x element of real number such that infinity is on this side, right, and b can be any element which is actually acting as a boundary element for x. So in this case x would be less than equal to b, right? And on the left side of b we got the negative infinity, so x can take all the values from negative infinity up. And on the other end, if I were to take x element of negative infinity comma b, left and right it's open, in that case I can represent this as x element of real number such that x is strictly less than b, so x cannot take the value b. So these are some of the combinations we can have with the intervals. Now there is one last interval which we can also think of, that is x being contained in with negative infinity on the left and positive infinity on the right. So this is also possible. So that means we are including the complete real line. So that means this is going to be equal to r. So in this lesson we will learn how exactly we can use the concept of combining intervals. Now suppose we are being given this question, say solve for x squared greater than 16, and we are expected to find all values of x that is satisfying this particular inequality. Now if you were to take the values of x to be as 4, clearly you can see here that when x is equal to 4, you can have a value of x squared being equal to 16. But we want all values of this particular x that is satisfying this inequality. So for the value x is equal to 4, I'm getting x squared to be as 16. So I need to go beyond the value of 4 to get the exact solution for this. So clearly in this case x should be all values that are strictly greater than 4, because when x is equal to 4 I'm getting x squared to be as 16. So this is the condition that I need to look for, and x is equal to 4 is not going to be of any use to me if I were to solve this. So clearly x has to be a little bit more greater than 4. Now this is on one side. Now since I have a square term, even if I were to take x is equal to negative 4, still x squared is going to be equal to 16. Now if you were to draw the number line just for visualization purpose, so I've got 0 here, I got 1, 2, 3, 4, and it goes on up to positive infinity. In this case it's negative 1, negative 2, negative 3, negative 4, negative 5, and all the way to negative infinity. Now as we move towards the left side, the numbers become smaller and smaller and smaller, but the magnitude increases. So that means if I were to take a square of negative 3, I would get 9, and if I were to go beyond negative 3, say negative 4, and I take the square, I would get 16. But negative 4 is less than negative 3. And if I were to take the square of negative 5, I would get 25. But negative 5 is less than negative 4. So as we move towards the negative infinity side, the value is becoming smaller and smaller and smaller, can easily be absorbed. So if I were to have this inequality satisfied, I need to stretch myself from -4 and go beyond. That is the only way. So on the other side, I have x greater than 4. On the left side, I should have x to be as smaller than -4. So that means if I were to write this as an interval form, this is going to be x greater than 4 but smaller than infinity. So this will be one side. And for this, it's going to be x is going to be smaller. So in this case, we will start with negative infinity and end with -4. So if I were to write this as a combination of these two intervals, then the union would be written like this. So x takes all values from negative infinity up until -4. So -4 is not included. So even -4.01 is greater than -4. So that means the condition will still be satisfied. And then from 4 onwards to positive infinity. So this is what the solution is. Since these two intervals form the part of the solution, I place the union sign. So this is the solution for the question. Now, if I were to represent this using the number line, then that representation would be in this fashion. So 0, 1, 2, 3, 4, you got the infinity there, and -1, -2, -3, -4, -5, and you got the negative infinity there. So -4, I start here and it goes up to negative infinity. So I'm shading it a little bit darker, and then I've got 4 starting here. So from here onwards it goes to positive infinity. So this is the representation, and make sure the circle is not shaded. So this is how the number line representation comes. Next important thing that we have to know is how intersection is handled. This is union, and intersection symbol is this, but most too often in calculus we don't really encounter intervals with intersection. So for example, we are talking about a question, say simplify, say we have got say 2 to 8. This is an interval, and this is intersecting with say -1 to 5. If I were to represent this on the number line, then this is going to be negative infinity, positive infinity, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, -1, -2, -3. So 2 to 8. So this is a closed interval, 2 to 8. This is the representation for that. And -1 is open. -1 to 5 is over here. So if I were to take the intersection of -1 to 5, then clearly you can see the intersecting region is 2 to 5. So this is going to be 2. 2 is a closed interval, and 5 is an open interval. So this will be the solution to 2,8 intersecting -1,5. So clearly we can see from -1 the line goes up to 5, but 5 is not included, so that's why it's an open interval, but 2 is included here.
from -1 to 5, 2 is included, so that's why it's closed. So too often, if you are given a situation like this, then this would be the solution.
Welcome students. In this class we will be learning the concept of absolute value, which is very important in pre-calculus, and then even when you get into calculus you need to use this concept. Now, how do we define it? Now, for every x element of real number, the absolute value of x is represented by these two vertical bars, is equal to, now there are two conditions for which the absolute value goes. Now for x, in this case I have just said for every x element of the real number r, such that x is greater than 0, and for that we've got the absolute value of x to be equal to x itself. So this is the first condition. Now what if x is less than 0? So in that case we've got the second condition, for every x element of real number such that x is less than 0. In that case the absolute value of x is going to be equal to negative x. Now you might be wondering, why am I taking, or why we are having negative x here? Now you have to understand, when we talk about absolute value, we are actually talking about the distance of that particular point from a reference point. So in this case we would be considering 0. So this is the basic understanding. So in other words, if I were to have a real line and we got the point 0 here, and say we have a point called 19, when we talk about the absolute value of 19, we are actually talking about the distance of this point 19 from 0. So what would the distance of this point 19 from 0 be? Simple as that number, 19. Now on the other hand, you have to understand that the distance is never negative. So distance is always positive. So this is a very important understanding you need to have. Now I mentioned that. What if I were to have, say, negative 19? And if someone wants to find out the absolute value of this value, negative 19. So clearly negative 19 is less than 0. Now distance is always positive, so the absolute value of negative 19 will be 19. Now how do I get this 19? Now clearly, if I were to go to the definition of x being less than 0, in this case let me state here, x is equal to negative 19 is an element of real number such that x is less than 0. Now when x is less than 0, clearly the modulus of x is equal to negative of x, but the value of x is negative 19, so that is going to be substituted here. So when I substitute that value, I get positive 19. So that is how we are getting a positive value. I hope you understood this concept of absolute value, and the most important is this definition of absolute value. So moving forward, if someone were to ask you to find the distance between 2 points, say A and B, simply what you need to do is we need to find the absolute value of A negative B, and this will always be positive value. So have that in mind. So distance is never negative, distance is always positive, and absolute value always returns a positive value. Now if you were to graph the function for absolute value, so how the graph would be? So graph of, say, y is equal to modulus of x. Now clearly we know for x less than 0, in fact let me write this down, for x greater than 0 we got the modulus of x to be a positive value, and for x less than 0 we've got modulus of x to be also it returns a positive value, but the definition is going to be negative x. So clearly in this case I need to obtain a graph for y is equal to positive x, and in this case I need to obtain a graph for y is equal to negative x. Now if you were to draw the graph, say x-axis and y-axis, now clearly you can see that for y is equal to x, the graph is going to be on this region, and for y is equal to negative x, the graph is going to be on this side. So this is y is equal to x, this is going to be y is equal to negative x. So we got two regions. So we got a region 1 and we got region 2. So clearly you can see that region 1 is defined by this function y is equal to x, and region 2 is defined by this function equal to negative x. So when you have two regions defined by two different formulae, you call them as piecewise defined function. Students, in this class we will understand how exactly absolute values and inequalities are understood in calculus, and how exactly it is imperative for us to have a better understanding of the concepts that combines these two. Now let us consider an inequality like this: negative 5x positive 8 less than 5. I have not used any absolute function here. I just want to explain to you how the inequality works. Now the question here is to solve for x, right? So foremost what we would do is we would get rid of this positive 8. So we would do that by adding negative 8 both sides, and when we do that we would get negative 5x. Positive 8 negative 8 gets cancelled, giving us 5 negative 8, that's going to be negative 3. So we've got something like this. Now to find the value of x, what I would do is I would divide both sides by negative 5. So when I do that, negative 5x divided by negative 5, the inequality gets changed, the direction gets reversed, so it's going to be the other way pointing. So followed by negative 3 divided by negative 5. So clearly this is going to be x, because negative 5 gets cancelled, and this would result in 3 over 5. So the solution is going to be all values of x greater than 3 over 5. So let us, for example, find out what is 3 divided by 5. So this is going to be 0 point, and we add a 0, so it's going to be 0.6. So if I'm going to take this as 0, this as 1, and if this is 0.6, the values of x for which the quantities are greater than 0.6, the inequality holds good. So let me just show you that. So negative 5x positive 8 is less than 5. Now if I were to take the value of x to be equal to 1, I would get negative 5 of 1 positive 8 less than 5. So it's going to be 3, right? Negative 5 added with 8 is going to give me 3 less than 5. So 3 is clearly less than 5. So this is true. Now if I'm going to take a larger value of x, say x is equal to x is equal to 30, clearly x is equal to 30 is greater than 3 over 5. So if I were to substitute it for x is equal to 30, so negative 5 of 30 positive 8 less than 5, this is negative 150 added with 8 less than 5. Now clearly this is going to be negative 142 less than 5. So it's clearly true. So now we have understood how to solve a linear inequality. Let us understand what we have to do when we encounter inequality which has an absolute function embedded in it. So let me just give you this example. So if I were to have negative x less than 5, we're talking about the distance of this point from 0, right? So we've got 5 here and we've got negative 5 here. So this line is moving on. This is towards negative infinity, this is towards positive infinity, and this is 0 here. So when we talk about x less than 5, we are actually talking about the distance between 0 and 5, and distance between 0 and negative 5. If I were to take any value between this region, clearly it's going to be less than 5. If I were to take 4 here, if x is equal to 4, then clearly modulus of x equal to 4 is going to be less than 5. And if I were to take x is equal to 3, clearly modulus of 3 is going to be less than 5, because when I take modulus of 3, we are going to get 3, right? So up until 0, all the values are going to be satisfying this condition. Now what if I cross over beyond 0 towards the negative region? Even in this case, if I were to take x is equal to negative 2, clearly modulus of negative 2 is going to give me positive 2, and that one is going to be less than 5. So how am I to write this? So up until this point negative 5 and to this point 5, all values of x would satisfy this condition. So how are we to represent it by means of inequality? So this is the first law you have to understand. Now if we are given, say for example, for every x element of real number, if this condition modulus of x is less than 5, if we're given like this, the understanding is that whatever values that we take between this negative 5 and 5, so for every x that is present here, this condition will always be true. Negative 5 less than x less than positive 5. So this is a very important rule that we need to understand. How do we convert this into a basic rule? So this basic rule is applied. So that means if you are given like this, a modulus of a less than b, then the value of a will lie between negative b and positive b, and this is true even if you are taking lesser than equal to sign. So have that in mind. Now we can also alternatively consider or think of this explanation. That means we are only considering all values of a that lie between negative b and positive b. This is for the case when modulus of a is less than b. So this is the case, okay, case 1. Now on the other end, if you are talking about, say, modulus of a less than equal to b, we are only considering all values of a that lie between negative b and positive b. So that means you got the values of a, negative b less than equal to a less than equal to positive b. So that is the understanding that we get here from this inequality. Now we got the basic rule number 2. So this is going to be rule number 1, and we got basic rule number 2. So if you remember, I gave you the example of 5 modulus of x less than 5, and we drew a number line of this fashion, right? So in that example, we considered only this region that is sandwiched between -5 and +5. Now, what if we are given this region? So how do we have a rule for this region? So in that case, clearly we would have modulus of x to be greater than 5. So that means we are talking about all values of x that are lying on this side. So in this case, this inequality is same as saying all values of x that are greater than 5. This is for the first part, first region, and for the second region, all values of x. So if you're going to take all values of this part, this side, they are naturally going to be smaller than -5. So this is going to be this inequality, right? So on one side x is greater than 5, and on the other side x is less than 5. So if we are given to generalize this, we can clearly say in terms of a and b, we can say that if we are given, say, modulus of a is greater than b, then the understanding is we are talking about a greater than b on one end, and on the other end we're talking about all values of a less than -b. So this is also a very important concept that we need to know. So in terms of intervals, so like the way I specified here for lesser than equal to and for strictly less than, we can also specify the same thing for this. So that in this case would be, we have two pieces, right? So the left piece would be from -infinity to -b, and the other piece would be from b to +infinity. And we are basically considering these two regions, so we place the union there. So this should be the interval that we are considering. Now we will be encountering all of this in a greater fashion as we move on to study the limit concepts. So moving on, I would like to give a small example which talks about inequality. Say for example, we are asked to find x if we have got modulus of x -4 is less than 5. Now I would like to draw your attention to the basic rule which I have explained to you. Basic rule number 1, where clearly if we are given modulus of a less than b, then the understanding is -b less than a less than b. So this is the understanding I have explained to you. Now think of your x -4 as your a, so that would mean I've got -5 less than x -4 less than +5. Now I need to get rid of this -4, so I'm going to add +4 on both sides, and that would give me -1 less than -4, and +4 gets cancelled, giving me x less than 9. So all values of x lying between -1 and -9 is the solution for the inequality. So if we had to write the solution in a different manner, so this is true, okay, for every x element of the real number, the value of x lies between -1 and +9, and in interval form you can always say x is element of -1, 9. So you can always represent it in this fashion, but this is the solution. And see more of these illustrations as we progress. Students, in this class we will learn about fraction arithmetic. Now there are three different types you will encounter when you are asked to perform fraction arithmetic. Now say for example you are asked to simplify 1/4 plus 3/4. Now clearly you can see that the denominators are same, and you can take 4 to be the LCM, and that would give you 4 over 4, and the resultant is 1. So similarly, imagine you got 5 over 7 to be added with 8 over 7, and clearly the denominator is 7, and the outcome is going to be 5 positive 8, which is 13 over 7. Now these are all simple to handle, the reason being the denominators are same. Now on the other hand, if you are given say 3 over 7 to be added with 5 over 14, let me just write that down, type 2, then you got type 1 here. Now in this case you can see we got 7 to be as one denominator and 14 to be the other denominator. Clearly one denominator can be expressed something multiplied equal to the other denominator. In this case 7 times 2 is going to give me 14. So what I'm going to do is I'm going to multiply the numerator by 2 and the denominator by 2, and then add it with 5 over 14. So this is going to give me 6 divided by 14 added with 5 divided by 14, and this is going to be, taking 14 as the common denominator, this would give me 11 over 14. So we have seen first step, we have seen second step. Now sometimes you would not be able to do anything at all. Say for example you got 3 over 7 to be added with say 5 over 12. 7 cannot be expressed to be product times of some number and that number being equal to 12. It's not possible, even though 7 is smaller than 12, because the number 7 and 12 are relatively prime, meaning there are no common factors between these two numbers. So when a case like that happens, what we do is we use this law, this rule. So for example you got A divided by B added with C divided by D, then we take the common factor for B and D. In this case BD is the common factor, and this one would result in A multiplied with D added with C multiplied by B. So this is a very important formula or rule that you can use in solving situation like this. So in this case clearly I would be taking the factors as 7 times 12, and for this term it's going to be 3 times 12 added with 5 times 7, and this is equal to 36 plus 35 added with 7 times 12 will give me 84. I can rewrite this as 71 divided by 84. So these are some of the better ways by which we can perform fraction arithmetic. So students, the next thing we will be looking into is fractions involving multiplication. In the previous example I showed you how to handle fractions involving arithmetic. Now that goes for both addition as well as subtraction. Now in this case we got a formula. Suppose we got A over B and this is multiplied with C over D. We get the output as A times C divided by B times D. You have to understand that this formula is not a hard and fast formula that we need to apply whenever we see quantities involving A over B multiplied with C over D. So have that in mind. This is just a formula for your understanding. Now why do I say that? Now imagine you got 5 divided by say 36. This is multiplied with 9 over say 125, right? Now you cannot be multiplying 5 times 9, that's 45, and then multiplying 125 with 36. So in this case it's going to be 6 times 5 is 33, 6 2s are 12, 13, 14, 15, 1, 6 1s are 6, 7, 15, 1, 6, 7, 3, 0, 10, 1, 5, 4, 5, 0, 0. You cannot be writing that. This is waste of time. So and then cancelling it out. Say 45 divides, so the output is going to be 1 divided by 100. This is going to be the solution. Of course, this will be the solution for this fraction. But we can achieve this instead of going about the formula process. So all we need to do is we need to just think of foremost how we could reuse these fractions. So clearly 5 divides 125 25 times, and 9 divides 36 4 times. So now we've got 1 over 4 multiplied with 1 over 25, which is going to be 1 over 100. So why am I showing you this method of reduction? Imagine you are asked to solve a question like this. Say x to the power 3 divided by x squared negative 4, and that has to be multiplied with, this is a little bit complex, and we cannot be just going on to multiply x cubed with x minus 2 and then trying to simplify it, because this is going to give me x to the power 4 negative 2 times x to the power 3, and this is going to give me a complex denominator, right? But instead of following this, what I can do is I can simply reduce in other words, what I'm trying to say is find ways by which you can cancel things out. So this is equal to x cubed divided by x squared negative 4. I'm going to rewrite it as x negative 2 multiplied with x positive 2, and this is one quantity, and clearly x negative 2 gets cancelled, x gets cancelled here, so this is going to give me x. So these are some of the ways and techniques that you need to adopt when you are dealing with fractions involving multiplications. So the rule that you need to adopt in most cases is, instead of multiplying first and factoring, you have to factor first and multiply later. So have that in mind. So the key word is factor first. Students, the next topic that we are going to deal here is fractions involving divisions. So in this case, we are going to be studying how exactly we can handle questions of this fashion. Say suppose you are given a over b divided by c over d. Now the understanding of this expression is a is divided by b, and that is further divided by c over d. This is the meaning of this. Now whenever you have an expression of this fashion, what you can do is you can flip the c over d up. Whenever you flip it, the d goes to the numerator and the c is in the denominator. So this is going to be a times d divided by b times c. So this is a very important concept, the concept of flipping. So have that in mind, and this is going to be coming very much in handy. Now suppose you are given an expression to simplify. Say you got 1 divided by x squared positive a squared followed by negative 1 over x squared divided by a squared. So you have an expression of this fashion. Now the meaning of this expression is 1 divided by x squared positive a squared negative 1 over x squared. Now this a squared is actually resting on 1. So we are going to be flipping it. So when we are flipping, what happens? This is equal to 1 over x squared plus a squared negative 1 over x squared. When we flip a squared over 1, it becomes 1 over a squared. So this is what we are actually getting. So this is equal to, in this case we can take the denominators. The denominators are going to be x squared positive a squared multiplied with x squared. Of course you got 1 over a squared there. So in this case you are going to get x squared for the first term followed by a negative sign, and then x squared positive a squared. Now students will make one big mistake in this case. See, the negative sign, they will simply place the negative sign like this and proceed on, but this is inaccurate, this is incorrect. What you got to do, whenever you're placing this term x squared positive a squared, you got to place it in parentheses. If you don't do that, outcome is going to be filled with error. So this is going to be x squared, negative times positive x squared will give you negative x squared, negative times positive a squared will give you negative a squared, divided by x squared times, in fact I'm just writing the x squared first, and then followed by x squared positive a squared, and then that has to be multiplied with 1 over a squared. Clearly positive x squared, negative x squared gets cancelled, giving me negative a squared divided by x squared times x squared positive a squared, and that is multiplied with 1 over a squared. Now this quantity negative a squared is actually negative 1 multiplied with a squared. Have that in mind. So that is going to be equal to negative 1 multiplied with a squared divided by x squared times x squared positive a squared, and that is multiplied with 1 over a squared. You can either place a dot like this or place these things within parentheses. Now a squared can be cancelled. You got negative 1 times 1, place that negative 1 divided by x squared times x squared positive a squared. So this is the outcome for this particular simplification. So these are some of the important things you have to know. So in this case a squared is written as a squared over 1, and then the flipping takes place, and then make sure to place the parentheses. So these are the places where students have the higher probability of making a mistake. Students, in this class we will be learning about the rules governing exponent. Now when I say a squared, it means a is multiplied twice. When I say a cubed, a is multiplied 3 times. Now the question comes, what happens when I multiply a squared with a power 3? So for handling issues like this, we have what is called as the laws for exponent. So we need to understand that law. So the first law is a raised to the power m multiplied with a raised to the power n is equal to a raised to the power m positive n. Law number 2, a raised to the power m, if n is negative, then it's going to be a raised to the power m negative n. Now the next one is, if you got a raised to the power m divided by a raised to the power n, you can always rewrite this as a raised to the power m times a raised to the power negative n, which can be rewritten again a raised to the power m negative n. So when it comes to dividing exponents, make sure that you are able to rewrite this fraction in this form. Now law number 4 is, if you have something like this, say for example a raised to the power m raised to the power n, then I can always rewrite this as a raised to the power n, the whole raised to the power m, which can be rewritten as a raised to the power n times m, or it can be rewritten as a raised to the power m times n. So have this in mind. Now the next one is, if you got a raised to the power, in fact let me write it like this, a times b raised to the power m is same as a raised to the power m multiplied with b raised to the power m. So have that in mind. ab raised to the power m is same as a raised to the power m multiplied with b raised to the power m. So that is an important property. Now next, law number 6 is, if you got, you can use the same thing for division. You got a over b raised to the power m. This is same as a raised to the power m divided by b raised to the power m. There is one more important property that you got to know. Okay, law number 7. Now if you got a raised to the power m raised to the power 1 over n, you can always rewrite this as nth root of a raised to the power m. Have this in mind. Now alternatively, you can also write a raised to the power m raised to the power 1 over n as a raised to the power 1 over n, the whole raised to the power m. So that means this is going to be rewritten as nth root of a raised to the power m. So I have that in mind. I'm using this space here. You got this a raised to the power m raised to the power 1 over n. This can also be rewritten as a raised to the power m over n. So there are several combinations by which we can represent this particular quantity, a raised to the power m raised to the power 1 over n, either using the radical sign or interchanging the indices and rewriting it in the fashion that we want. So having mentioned that, let us move on. Students, in this class we will try to understand some important basics so that we can prevent those pitfalls. Now here we have been given this question: are they equal? 3 positive 5 squared and 3 positive 5 raised to the power 2. Now for sure both these expressions are different, because if we were to consider 3 positive 5 squared, we will have to start with operating on the exponents. In the very first class I have introduced the order of operations, so exponents comes first before addition. So we solve that. 5 squared is going to be 25, then we add it to 3, so this is going to give me 28. Now if I'm going to be considering the next expression, 3 positive 5 raised to the power 2, the parenthesis, the brackets comes first, so I add the quantity of 3 with 5, that's going to give me 8, and then I square it, that's going to give me 64. So one gives me 28, the other gives me 64. So the solution is they are not the same, they are not equal or not the same. So have that in mind. So the next one is say for example I'm asking you, is x positive 5 raised to the power 2 equal to x squared positive 5 squared? Are these two terms equal? So let us just consider what happens to x positive 5 raised to the power 2. Now this is nothing but x positive 5 multiplied with x positive 5 twice. Now this is nothing but x multiplied with x positive 5 multiplied with x positive 5. So this is equal to x squared positive 5x positive 5 times x positive 25. This is x squared, 5x added with 5x will give me 10x positive 25. So this is what I'm getting. Of course you can use a positive b whole squared formula, which is a squared positive 2ab positive b squared in this case, and get the same result. And clearly if you had to consider x squared positive 5 squared, you will end up with x squared positive 25, and clearly you can see that the presence of 10x is missing here. So clearly because of the fact that x squared positive 10x positive 25 as an addition or an extra 10x term, these two are not equal. So please bear in mind that whenever you're giving expressions of this fashion, you have to adopt an extra caution. Now the next pitfall comes when you're given a radical sign, a square sign, and then you got two terms like this, 4 positive 25, and you are asked to simplify. Immediately some students would conclude that this is same as root of 4 added with root of 25, but this is incorrect. This is not equal, for the fact that we cannot have a rule like this. Root of a positive b is not equal to root of a added with root of b, so have that in mind. So whenever you're given like this, make sure to simplify the quantity inside the square root. In other words, add them up using the rules that we study. So if I want to simplify this, the utmost simplification that is possible in this case is going to be adding 4 with 25. I cannot go any further than this. So this is the final answer. If in case we were given something like this, say 4 plus 32, then adding these two, 4 plus 32 would give me 36, then I can always the solution to be as plus or minus 6. So this is possible because of the value inside. Okay students, we got a list of questions involving exponents, and we will be approaching them using the formulae that we studied. So solution to question number 1. we are given x to the power 5 multiplied with x to the power 16. So we have studied this formula. We know that a raised to the power m times a raised to the power n is a raised to the power m positive n. Now using this formula, I can always rewrite this as x raised to the power 5 added with 16, giving me x raised to the power 21. So this will be the solution for question number 1. Now question number 2, I've been given x raised to the power 4 times x raised to the power 3, the entire quantity raised to the power 2. Now we already studied a formula. If I can just state here, we know that ab raised to the power m is nothing but a raised to the power m times b raised to the power m. So by this formula, what I can do is I can rewrite x to the power 4 y cubed raised to the power 2 as x to the power 4 raised to the power 2 times y raised to the power 3 raised to the power 2. Now this is equal to, we can also use this formula. We know that a raised to the power m raised to the power n is equal to a raised to the power m times n. By this formula, we can rewrite this as x raised to the power 4 times 2 is 8, and that has to be multiplied with y times, and you got the degree of y to be 3 here, and that is raised to the power 2 here. So it's going to be 3 times 2 is 6. So this is the final answer to question number 2. Now let us move on to question number 3. Now question number 3 is x to the power 7 divided by x to the power negative 5. Now we know that if you got a to the power n divided by, say, some a raised to the power n, I can always rewrite this as a raised to the power m negative n. So by this formula, I can rewrite x power 7 divided by x power negative 5 as x to the power 7. I'm moving this to the numerator. So that means the exponent's sign will get changed by this formula. So it's going to be negative 5 is going to be changing to positive 5, which is going to be x raised to the power 7 positive 5, which would give me x raised to the power 12. So this will be the solution for question number 3, which we have obtained here. Now going on to question number 4. Question number 4 is 4th root of x raised to the power 8 times y squared. Now if we have seen the formula, we already know that if you got, say, nth root of a raised to the power n, I can, let me state that, we know that I can always rewrite this as a raised to the power m raised to the power 1 over n, right? So knowing this formula, I can rewrite this as x raised to the power 8 times y squared, the entire quantity raised to the power 1 over 4. Now I also know a formula that a raised to the power m raised to the power 1 over n is a raised to the power m over n. So by this formula, this is going to be x raised to the power 8 over 4 multiplied with y raised to the power 2 over 4, right? Because I'm able to do this because in the previous question I already gave you this formula. ab raised to the power m is nothing but a raised to the power n times b raised to the power m. So by this formula I'm able to rewrite this, but this is nothing but, now 4 divides 8 twice, so it's going to be x raised to the power 2. 2 divides 4 twice, so it's going to be y raised to the power 1 over 2. So this is what I get. Now you can rewrite this as x squared times root of y. Now we got question number 5, which is 27 divided by 216. The entire quantity raised to the power 2 over 3. So I can rewrite this as 27 is 3 raised to the power 3 and 216 is 6 raised to the power 3, and this is raised to the power 2 over 3. Now people may be tempted to strike this 3 out, so don't do that. Now this is rewritten as 3 over 6 raised to the power 3. I'm able to do this because the exponent value is same. That's why I'm doing it. I will show you the other scenario when it isn't so. So now this is raised to the power 2 over 3. Now I already gave you the formula that if you got a raised to the power m, and if this is raised to the power 1 over n, then you can always rewrite this as a raised to the power m over n. Now using this formula, I'm going to rewrite this as 3 over 6. The entire quantity is raised to the power of 3 times 2 over 3. So 3 and 3 can be cancelled, giving me a value of 3 over 6 raised to the power 2. Now clearly now I can reduce it because the exponent value is same. So 3 divides 6 2 times. So I can rewrite this as 1 over 2 raised to the power 2, which is equal to 1 over 4. Now if you are not interested in following this, you can alternatively do this in this fashion. So from here I'm starting. So I've got actually 3 raised to the power 3 divided by 6 raised to the power 3. The entire quantity is raised to the power 2 over 3. Now this method comes in handy when the exponents are different. So in this case I can rewrite this as 3 raised to the power 3. The whole is raised to the power 2 over 3 divided by 6 raised to the power 3. The entire quantity is raised to the power 2 over 3. This is in turn raised to the power, can be rewritten as 3 raised to the power 3 times 2 over 3 divided by 6 raised to the power 3 times 2 over 3. Now clearly 3 and 3 can be cancelled, giving me 3 squared. And in this case 3 and 3 can be cancelled, giving me 6 squared. Now 3 squared is 9, 6 squared is 36. 9 divides 36 4 times, so it's going to be 1 over 4. In either of the cases, the solution is 1 over 4. So it's up to you which method or technique that you wish to adopt. Now, question number 7 can be simplified using the formula which we have studied, which is a over b raised to the power m is a over m divided by b over m. So using this formula, I can rewrite this as x squared y power 3 raised to the power 4 divided by root of x times y raised to the power negative 2 raised to the power 4. Now we also know that a raised to the power m raised to the power n is a raised to the power m times n. So we know this formula also. So this is equal to x squared raised to the power 4 times y cubed raised to the power 4 divided by root of x raised to the power 4 times y raised to the power negative 2 raised to the power 4. Now we also know that a raised to the power m, of course I have already mentioned this formula, so I don't need to mention it again. So this can be rewritten as x raised to the power 2 times 4 is 8 and y raised to the power 3 times 4 is 12. Now this is actually x raised to the power 1 over 2 raised to the power 4. And in this case is going to be negative 2 times 4 is going to give me negative 8. So this can be rewritten as x power 8 times y raised to the power 12 divided by, this is going to be x raised to the power 2 divides 4 twice, so you can place that, and this is y raised to the power negative 8. Now what I can do is I can move the denominator to the numerator. So this is going to give me x raised to the power 8 y raised to the power 12 multiplied with x raised to the power negative 2 and y raised to the power positive 8. Now this can be rewritten as x raised to the power 8 multiplied with x raised to the power negative 2 and y raised to the power 12 multiplied with y raised to the power 8. Now I can place them in parentheses. So this is equal to, students, in this class we are going to be learning about lines, in particular slopes. So let me draw the coordinate axis, x-axis, y-axis, and a straight line. Now let me take a point A comma B and a point C comma D, and my intention is to find the slope. So this is going to be C comma B here, and the slope is given by the following formula. So we represent the slope of a line by the letter M, and it is given as rise divided by run. This is the basic formula. Now the meaning of this formula is delta y divided by delta x, which means change in y over change in x. So that's the understanding. So having got this, if we were to find the slope, it's going to be m is equal to d minus b divided by c minus a. So this is what we get using the formula. Now let me consider an intermediate point between a comma b and c comma d and name it as x comma y. Now if I were to take the slope using a comma b and x comma y, that slope will be same as considering these 2 points x comma y and c comma d. So I'm going to be writing down here, considering a comma b and x comma y, the slope is going to be y minus b divided by x minus a. Next, I'm going to be considering the point x comma y and c comma d. So that slope is going to be d minus y divided by c minus x. Now, let me name this as 1 and 2 and obtain the equation of the line. So from 1, we get the equation of the line to be as m times x minus a is equal to y minus b. This is what we get. Now I'm going to write y minus b on the left and place m times x minus a on the right. This is the usual way we write, and this has got a special name. The name of this formula is called as slope point formula. So that is the name for this. Now this can be further rewritten as y is equal to m times x negative m times a positive b, and simplifying I get y is equal to mx positive b. In fact, I can write this as b. I can take b out. No, let me just write that down here. So y is equal to mx positive, I open the parenthesis, b negative ma. I can write it like this, and this has a special name. So the name of this is called as the intercept form. Intercept form, and let me name it as equation 3. So all I've got this from considering 1. Now what I'm going to do, I'm going to say from 2, right, considering 2, from 2, considering 2 we get. So what do we get when we consider 2? Cross multiplying, we get c negative x multiplied with m is equal to d negative y. I'm going to rewrite this as d negative y is equal to m of c negative x. Now this is going to be mc negative m times x, and this is d negative y. Now I want to have a positive y, so I'm going to be multiplying by negative sign. So multiplying by negative 1, right? So if I multiply by negative 1, what do I get? I get negative d positive y is equal to negative mc positive mx. So this can be further rewritten as y negative d is equal to mx negative mc. Right? So this is what I have got here. Now this can be rewritten. In fact, I could have done it right in there, and never mind. So now y is equal to mx. I'm moving this negative d to the right side, so it's going to be positive d negative mc. So this is what I've got. So this is 4. If I were to write this as slope point formula, this would be y negative d is equal to m times x negative c. So this is going to be a slope point formula. So just for your understanding, and this is going to be the intercept form. Now the question comes, I've got 3 here, I've got 4 here. Are the two equations one and the same? I hope you're following the question. The question is, the equation I've got here, question number in 3, and the equation that I've got here in 4, are they one and the same? Of course they are one and the same, and I can show it to you from here. So from here I've got m is equal to d minus b divided by c minus a. Now I'm going to use the space here. Now if I'm going to rewrite this, this is going to be m times c minus a is equal to d minus b, and this is mc negative m times a is equal to d minus b. Now if I can move mc over here and b minus negative b to the left, this is going to be b minus ma, and this is going to be d negative mc. So the meaning is b minus ma is equal to d minus mc. So coming over here, we got b minus ma. B minus ma is equal to, so I got d minus mc and b minus ma. So b minus ma is same as d minus mc. Now how did I get that? I got that just by using this relationship which we started off. We started off here, and upon basic simplification, you can clearly see that b minus ma is equal to d minus mc. Students, in this class we will learn about expanding. Now the method that we would be learning, in fact applying, is called as FOIL. Now FOIL stands for first, outside, inside, and last. So what exactly does it mean? So if you got something like this, say 2x positive 5 and x positive 1, and you want to multiply this, we start with the first term. We multiply first term with the first term, so 2x times 2x, and then we take this 2x and then we go to the outside term, so it's going to be like this. So plus 2x times 1. So after that, after we have finished the outside, we go to the inside, so that would be this one. So plus 5 times x, and after we are done with the inside, we go to the last term. So that's going to be from 5, we are going to go to 1. So 5 multiplied with 1. So positive 5 multiplied with 1. So this is equal to 2x squared, positive 2x, positive 5x, positive 5. Further simplification will lead us to 2x squared, positive 7x, positive 5. Now you have to understand that most times when the expressions are big, the FOIL method will not be applicable, or it wouldn't be of much use. But whenever you have two terms, we can very well go ahead and use the FOIL technique. So for this, we would be using the distribution technique. So distributive technique or distributive property that we have studied. So the best and simple way, say if I want to multiply these two terms, what I would do, I would take 2x multiplied with x positive 1, and then take 5 multiplied with x positive 1. That's it. So this will give me 2x squared, positive 2x, positive 5x, positive 5, which in case is going to be 2x squared, positive 7x, positive 5. I would get the same result. Now when exactly this comes in handy? Now suppose you have huge terms, say for example x negative 3, and multiplied with say 4x to the power 3, positive 2x squared, positive x negative 2. You have a term like this. When handling terms like this, we cannot be applying FOIL method. So the distributive property is what is much use to us. So start with x multiplied with 4 times x cubed, positive 2x squared, positive x negative 2, and then negative 3 multiplied with 4x cubed, positive 2x squared, positive x negative 2. Now this would give me 4x to the power 4, positive 2x to the power 3, positive x squared, negative 2x. This will give me 3 multiplied with 4x squared cubed would give me 12x to the power 3. There's a negative sign, so that's going to be negative there. So negative 3 times 2, 6x squared, negative 3 times x, negative negative positive 6. So this is going to be equal to 4x to the power 4, 2x cubed with a positive sign added with negative 12x cubed. That's going to be negative 10x cubed. I got a 6x squared, negative 6x squared added with positive, and that's going to be negative 5x squared. So I've finished with this, I've finished with this, I've finished with this, I've finished with this, I've finished with this. I got negative 2x, negative 3x, so it's going to be negative 5x, positive 6. So this is the final expression that we've got. Now we can move on with another example. Maybe we got an example like this. So x positive 4 multiplied with x negative 5 multiplied with 2x positive 1. Now in this case we can very well use FOIL method. It's better to use FOIL. So what I can do, I can apply the FOIL technique to the first two components. So that's going to be x into x squared, and then the outside term is going to be negative 5x, then the inside term positive 4x, then the last term minus 20. This has to be multiplied with 2x positive 1. So this can be simplified further. So it's going to be x squared negative x negative 20, and this is going to be 2x positive 1. So now we need to use distributive property. So this is going to be 2x times, I'm taking this first, so 2x times x squared negative x negative 20, and then plus 1 times x squared negative x negative 20. So this is going to be 2x to the power 3 negative 2x squared negative 40x followed by x squared negative x negative 20. I can add these two terms, that will give me negative x squared. I can add these two terms, that will give me negative 41x followed by negative 20. So this is the result. So depending upon what you have got, what you receive in the questions, you can effectively use the FOIL method and the distributive method based on the conveniences. Welcome students. In this class we will understand the binomial formula, or otherwise called as binomial theorem. Now it is given as follows: x positive a to the power n is equal to sigma. Now the value of the sigma ranges from k is equal to 0 to n, and then we got n c k times a raised to the power k followed by x raised to the power n minus k, where the value of nck is given as n factorial divided by k factorial times n minus k factorial. Now at times this nck can also be written as nk, just like that. So have that in mind. Now where do we use binomial theorem or binomial formula? Now all the algebraic formulae that you've been exposed to either in pre-calculus or in your algebra classes, all of those formulae have been generated or obtained from this binomial theorem or binomial formula. I'm going to give you an example for that. Now imagine you are asked to obtain the expression of x positive 2 raised to the power 2. Now from the binomial formula, the value of n is 2 there, and k ranges from 0 to 2, and it's going to be 2ck times the value of a is 2 raised to the power k times x raised to the power 2 minus k. So this is the expansion that we have to obtain. Since sigma is actually there, so we will have to add up all the quantities that we have got, starting from k is equal to 0, and then k is equal to 1, and then k is equal to 2. So I'm going to show you how to get these values. Now when k is equal to 0, this expansion or this formula is going to be rewritten as 2c0 times 2 raised to the power k is 0, it's going to be 0 there, and that has to be multiplied with x times, in fact, x raised to the power 2 minus 0. So this is equal to, now 2c0, how do we find 2c0? We will be using this particular formula. So 2c0, let me just draw a line there, is nothing but 2 factorial divided by 0 factorial times 2 minus 0 factorial. Now 2 factorial is 2, 0 factorial is 1, now 2 minus 0 factorial. So that's going to be 2 factorial, which is 2. So 2 and 2 can be cancelled, giving you 1. So 2c0 is actually 1. So, and 2 power 0 is actually 1. And now you got x raised to the power 2 minus 0. That's nothing but x squared. So that can be clearly rewritten as x squared. So when k is equal to 0, I have just got that term as x squared. Now we need to do for k is equal to 1. So that's going to be 2c1 times 2 raised to the power k is equal to 1. That's going to be 2 power 1 times x raised to the power 2 minus 1. This can be rewritten as 2c1 times 2 times x, because 2 minus 1 is going to be x. So now we need to find what is 2c1. Now 2c1, I'm going to use the formula, which is going to be 2 factorial divided by k is 1 factorial. So 2 minus 1 factorial. So 2 factorial is 2, 1 factorial is 1, 2 minus 1, that's going to be 1 factorial. So 1 factorial is going to be 1. So no need to place the factorial sign. So this is going to be 2 there. So 2c1 I've actually got here as 2. That has to be multiplied with 2x. So this would result in 4x. So this is the value I have got for k is equal to 1. Now moving on, for k is equal to 2, it's going to be 2c2 times 2 raised to the power, the value of k is 2, that has to be multiplied with x raised to the power 2 minus 2. So this is going to give me 2c2. So what is 2c2? Substitute in the formula. This is going to be 2 factorial divided by k is 2, 2 factorial. Now 2 minus 2 factorial. 2 factorial will give me 2, 2 factorial will give me 2, 2 minus 2 factorial will give me 0 factorial, which is going to be equal to 1. So this quantity will get cancelled, giving me 1 there. So 2c2 is 1, 2 to the power 2, that's going to be 4, x to the power 0 is going to be 1. So this is going to be 4. Now we need to add up this term with this term with this term, and all these terms would give me the expansion for x raised to the power 2 raised to the power 2. So the first term is going to be x squared, the second term is going to be 4x, the last term is 4. So this is the expansion that we have got. In fact, this is the formula, and we all know that this is the correct answer. So having mentioned this, what we would do if they are asking us to find what is x plus 2 raised to the power, say, 8. So we need to use the formula for that. So I'm going to show you how to get it. Now, before we could go on to expand x to the power x positive 2 raised to the power 8, let us write down the binomial formula. Now I've given you that x positive a raised to the power n is written as sigma k is equal to 0 to n followed by n ck times a raised to the power k times x raised to the power n minus k. So this is the binomial formula. Now briefly expanding this, we would have the following terms. So we would start with x to the power n positive, n times a times x to the power n minus 1 positive, n into n minus 1 divided by 2 factorial times a raised to the power 2 times x raised to the power. Now we started with n, this is n minus 1, this is going to be n minus 2, positive n into n minus 1 times n minus 2 divided by 3 factorial times a to the power 3 times x to the power n minus 3, positive, etc. It goes on, and then the last but one term is going to be n times a raised to the power n minus 1 times x, positive a to the power n. So this is going to be the final term. Now I have already given you that nck is equal to n factorial divided by k factorial times n minus k factorial. So this is also a very important thing to consider. I mean x positive 2 raised to the power 8. So this is going to be equal to x raised to the power 8 positive 8 times, my value of a in this case is going to be 2. So it's going to be 2 times x raised to the power 8 minus 1. So this has to be followed by 8 into 8 minus 1 divided by 2 factorial times a is 2. So 2 raised to the power 2 times x raised to the power 8 minus 2 positive 8 into 8 minus 1 times 8 minus 2 divided by 3 factorial times 2 raised to the power 3 times x raised to the power 8 negative 3 positive 8 into 8 minus 1 times 8 minus 2 times 8 minus 3 divided by 4 factorial times 2 raised to the power 4 x raised to the power 8 minus 4 positive 8 into 8 minus 1 times 8 minus 2 times 8 minus 3 times 8 minus 4 divided by 4 factorial times 2 raised to the power 5. In fact, it's 5 factorial, not 4 factorial, divided by 5 factorial times 2 raised to the power 5 times x raised to the power 8 negative 5 followed by 8 into 8 negative 1, 8 negative 2, 8 negative 3, 8 negative 4 times 8 negative 5 divided by 6 factorial times 2 raised to the power 6 times x raised to the power 8 negative 6 positive 8 into 8 negative 1, 8 negative 2, 8 negative 3, 8 negative 4, 8 negative 5, 8 negative 6 divided by 7 factorial times 2 raised to the power 7 times x raised to the power 8 negative 7, we've got that, plus 8 times 8 negative 1, 8 negative 2, 8 negative 3, 8 negative 4, 8 negative 5, 8 negative 6, 8 negative 7, there are 7, 6, 7, 8 divided by 8 factorial times 2 raised to the power 8 and x raised to the power 8 negative 8. So this is the final term. So we started with, this is actually 1 factorial, 2 factorial, 3 factorial, 4, 5, 6, 7, 8. The question comes, we will have to find out the values of all these factorials that you see, and that is not going to be easy. We need to obtain the value of this, find the value of this, find the value of this, find the value of this, and so on. But we can avoid all of this using the concept of Pascal's triangle. Now, what does Pascal triangle mean? Now, Pascal's triangle has given us a shortcut to find out the values of all these quantities. This is a powerful way to obtain expansions of huge numbers. We start with 1 and we place 1, 1 in the second row. Then we place a 1 to start with the third row. We add 1 and 1 and we place it in between. Then follow it up with a 1 at the extreme. Then we start with 1, we add 2 with 1, it's going to be 3. We add 1 with 2, it's going to be 3. We place 1 there. And then again we add, in fact we start with 1 and then we add 3 with 1. It's going to be 4. 3 added with 3 would give me 6. 1 added with 3 would give me 4. And then a 1. We start with 1. 4 added with 1 will give me 5. 6 added with 4 will give me 10. 4 added with 6 will give me 10. 1 added with 4 will give me 5. And then we end with 1. We start with 1. 5 added with 1 will give me 6. 10 added with 5 will give me 15. 10 added with 10 will give me 20. 5 added with 10 will give me 15. 1 added with 5 will give me 6 and a 1 there. We start again with 1. 6 added with 1 is 7. This is going to give me 21. This is going to give me 35. This is going to give me 35. This is going to give me 21 and a 7 and a 1. And we start with 1. This is going to give me 8. This is going to give me 28. And this is going to give me, this is going to be 51, 56. This is 70. This is again 56. This is 28 and this is 8 and a 1. So this is for degree 8. This is for x to the power 8. In fact, this, when degree x is equal to 2, we get this to be the expansion. X is equal to 3, x is equal to 4, x is equal to 5, x is equal to 6, x is equal to 7, x is equal to 8. Now what is the meaning of these expansions? Now suppose you have something like this, say a positive b raised to the power 8. Then the expansion can be rewritten as, we start with a raised to the power 8 followed by a positive sign, and then we place this coefficient 8, and then the degree of a goes down by 1, so it's going to be a power 7, but the degree of b increases by 1, followed by 28. The degree of a goes down, so it's going to be a power 6. The degree of b increases, followed by positive 56 times a to the power 5, and then b raised to the power 3, positive 70 a raised to the power 4, b raised to the power 4, and then followed by positive 56 a raised to the power 3 and b raised to the power 5, positive 28 a raised to the power, the degree goes down by 1, it's going to be 2, but b's degree increases. It's followed by 8 a raised to the power 1 and b raised to the power 7, followed by 1 time a raised to the power 0, b raised to the power 8. So rewriting this expansion, we would get a raised to the power 8, 8a power 7, b positive 28a power 6, b squared, positive 56 a to the power 5, b cubed, positive 70 a power 4, b power 4, positive 56 a to the power 3, b power 5, positive 28 a squared, b power 6, positive 8 times a, b power 7, positive b to the power 8. So this is what we've got for a positive b raised to the power 8. If you would just remember, we started to find the expansion x positive 2 raised to the power 8. So the best way to calculate this is to take a is equal to x and b is equal to 2. If I were to do this, clearly I would say x power 8 positive 8 times the value of a is x power 7, the value of b is 2, positive 28 times x raised to the power 6, 2 raised to the power 2, positive 56 x raised to the power 5, 2 raised to the power 3, positive 70 x power 4, 2 raised to the power 4, positive 56 x raised to the power 3, 2 raised to the power 5, positive 28 x raised to the power 2, b is 2 raised to the power 6, positive 8 x, and then b is going to be 2 power 7, positive 2 power 8. So this can be expanded further. So upon simplifying, this is going to be x power 8. 2 times 8 is 16, x power 7 positive. This is 4 times 28. So 28 multiplied with 4, 32, 3. 4 times 2, 8, 9, 10, 11, 1, 1, 2. So this is x power 6 positive. And this is 8. 6 8s are 48, 4, and 40, 56, and this is going to give me 448 x to the power 5 plus 16 multiplied with 70, that is going to give me 1120 x to the power 4, positive 2 power 5 is 32, 32 multiplied with 56, that's going to be 1792 x to the power 3, followed by, this is 64, 2 power 6 is 64, 64 multiplied with 28, and that would give me 1792 x to the power 3, positive x to the power 2 is going to give me x power 2, positive, this is 128 multiplied with 8, that's going to be 1024 x, positive 8 power 4, so 2 power 6, 32, 64, 128, 128 times 2, that's going to be 256. So this is the complete expansion for x positive 2 raised to the power 8.
Welcome students, in this class we will be talking about polynomials and trying our best to understand the concept of polynomials. So what is a polynomial? So polynomial is an algebraic expression consisting of variables, exponents, constants, and along with this we have also all unified with addition operations. Now, variables are sometimes called as indeterminates. So this is just an additional information. Now, if you were to ask an example for a polynomial, x squared negative 2x positive 1 is an example for a polynomial expression. Now, one of the most important thing that we have to add here is the domain is the set of all real numbers. That is important. So, having mentioned this, let us go and study the types of polynomials. Types. Now, if you were to see here, this is a polynomial expression. Now, if I were to place something like this, say p of x is equal to x squared negative 2x positive 1, then this becomes a polynomial function. So, having mentioned that, let us talk about the different types of polynomials that are available. So, the first type of polynomial is called as monomial. Now, monomial is a polynomial with just one non-zero term. And example would be, say, 3x. So what is this? This is a monomial with just one variable. Now, if I were to write this as 3xy squared, this is again a monomial with two variables. Now, if I were to write this as, say, 3xy squared z cubed, something like this, then this is a monomial with three variables. So all these are all some possibilities. Now the next comes binomial. So binomial is a polynomial with just two non-zero terms. So if you were to take examples of binomial, then say 3x squared plus 4xy. This is an example of a binomial. Binomial with two variables. So on and so forth. So in general, if you were asked to define a polynomial, in general, we can define a polynomial expression as, say, some p of x is equal to a n x power n plus an minus 1 x to the power n minus 1 plus an minus 2 x to the power n minus 2 plus etc., and we reach a 2x squared, a 1x, plus finally say a 0. Now an, this is called the leading coefficient. Now this n is just an index for an, and a naught is called the constant term. Now n that you see here, they are called the degree of the polynomial. So this is a polynomial function, but if I were to write this as an x power n plus an minus 1 x to the power n minus 1 plus etc. end with a naught, this is called a polynomial expression. So having mentioned this, let us see some cases where the expression is not a polynomial expression. Now if I were to write something like this, this is not a polynomial. Suppose you got 1 over t negative 1 over t squared positive 1 over t cubed plus etc. This is not a polynomial because the variables are present as a denominator, and we don't deal with expressions of this form as a polynomial. And if instead of this, suppose you got like this, say 1 over square root of t positive 1 over third root of t negative 1 over fifth root of t, this is also not a polynomial. So have that in mind. So these cannot be a polynomial. Now on the other end, if they are asking you, so this is one more example, not a polynomial. I'm going to give you that example. Suppose you have an expression like this, say x squared negative 2 divided by x positive root 2. Suppose you have something like this. Now if I were to simplify this, I can rewrite this as x negative root 2 multiplied with x positive root 2 divided by x positive root 2, and then I can cancel them and I land up with x negative root 2. Students might think that this is a polynomial because the degree of x is 1 and we have a coefficient, but the problem here is, if you can see this quantity will vanish when x equal to negative root 2. You understand? When I substitute x equal to negative root 2, this entire expression or function, you can call it whatever you want, depending on what they give you, this will vanish. But according to definition, a polynomial should be an algebraic expression with constants, variables and exponents satisfying for all values of the real number as its domain. So the domain should not perish for any values of the real number, but in this case this perishes for x equal to negative root 2. So have that in mind. Now some of the other valid examples for a polynomial is, I want to give you a few examples. Say I can always have root of 3 x to the power 5 negative root of 2 x to the power 3 and positive 1 over root 2. This is perfectly acceptable. The coefficients are not integers, they are real numbers, that's fine. But the underlining point is that exponents that you see here should always be integers. Have that in mind. So having mentioned this, let us move on, students.
Students, in this class we are going to be learning two theorems. One is factor theorem and the other one is rational roots theorem. Now first let us get started with factor theorem.
Now, for all our purposes in this course, we will be taking the polynomial to be of the form p of x is equal to an x to the power n positive an negative 1 x to the power n negative 1 positive an negative 2 x to the power n negative 2 plus etc. and goes up to a naught. As I mentioned to you, a suffix n, this is called the leading coefficient, this is called the constant term, this is called the degree of the polynomial. Now, this is the statement or the definition of factor theorem, which I am presenting it to you. If p of a is equal to 0, then x minus a is a factor of the polynomial p of x. If p of a gives us 0, then x minus a is a factor of p of x. So that is simple as that. Now I'm going to show you an example. So we are given, say, given some polynomial p of x is equal to 2x squared positive, say, 7x negative 15. I want to see that if x is equal to, say, negative 5 is a root. If x is equal to negative 5 is the root of this particular polynomial. So that means p of x equal to negative 5 should give me 0. So I'm going to check if x is equal to negative 5 produces 0. So this means p of negative 5 is going to be equal to 2 of negative 5 squared positive 7 of negative 5 followed by negative 15. So this is equal to 5 squared with a negative sign, 25 times 2 gives me 50. This gives me negative 35. This gives me negative 15. Negative 35 added with negative 15 produces negative 50. I've got a positive 50. So positive 50, negative 50 gets cancelled. Gives me 0. So this implies clearly x is equal to negative 5 is a root of p of x, and x positive 5 is a factor of p of x. So that is how we obtain the factor theorem. And going forward, we can use the factor theorem in obtaining many such solutions. Students, now we will proceed to learn the rational roots theorem. Now, what does it state? Rational roots theorem. Now, let me start with the polynomial. Given p of x is equal to an x to the power n positive an negative 1 x to the power n negative 1 positive etc. a naught to be a polynomial, and p to be a factor of this term, constant term a naught, and q to be a factor of the leading coefficient an, then p over q will be, so this is giving us the root, will be a rational root of p of x. Now, just for an additional information, p and q will be relatively prime. So that means this is to state that in the least form, p and q will be relatively prime. So this is just an additional information. You don't need to be much bothered about this, but you need to be concerned about these two quantities, these two definitions. P to be a factor of the constant term, q to be a factor of the leading coefficient. So now we are going to do some examples for rational root theorem. And one more thing, this rational root theorem is also called as rational zero theorem. Have it in mind. So having mentioned that, let us do some examples, students. Students, we are given this question to find the rational roots, or I would use this word, find the possible rational roots, because we are not sure if we can get a rational root. So this is the function given. So what I'm going to do, I'm going to get all the factors. P is actually the factors of the constant of a0. So those factors would be the factors of 6. So the first one would be plus or minus 1, plus or minus 2, plus or minus 3. Well, the final one is going to be plus or minus 6. The possible factors for a naught. And Q is the factors of a n, the leading coefficient. So the factors of 2 would be plus or minus 1 and plus or minus 2. So that's it. So we got the factors of the constant term, factors of the leading coefficient. Now we need to find the possible rational roots. So we need to write it like that. Possible rational roots. So what are those? They are of the form P over Q. So that would give me 1 over 1, 2 over 1, 3 over 1, 6 over 1. So this is the first set. The second set, now I will place 2 as a denominator. So followed by 2, 2, 2, and 2. So if I were to group them and write them as a factor, so possible factors would be possible rational roots. I can't call them as factors. Possible rational roots would be, I would just group them in a single line. So it's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. This is going to be plus or minus 1 over 2 and plus or minus 1. But I have already written plus or minus 1 here, so I don't need to write it. And then plus or minus 3 over 2. 6 divided by 2 gives me 3. It's already there, so I don't need to write it. So this would be the possible roots. Now what we need to do is we need to check. Now first is identifying the roots. The next is checking them. So what I'm going to do, just to, in fact, if we have to check, we got to start actually from plus or minus 1 and move on. But since our time is limited, I would want to show you briefly how exactly taking x is equal to 2. If I were to take x is equal to 2 and substitute it in this system, I would get x is equal to, I would get f of x to be equal to 0. So that's what I'm going to show you here. So I'm going to substitute x is equal to 2. So it's going to be f of 2. So this is equal to 2 of 2 raised to the power 4, negative 5 of 2 raised to the power 3, negative 4 of 2 raised to the power 2, positive 15 of 2, followed by negative 6. This is equal to, now 2 2s are 4, 4 times 2, 8, 8 times 2 is 16, times 2 is 32, negative, this is going to give me 8, negative 5, 40, this is going to give me 4, negative 16, this is going to give me plus 30, this is going to give me negative 6. So this is equal to, I can, from here 32 negative 40, that will give me negative 8. So negative 8 can be added with 16 gives me negative 24. Negative 24 added with negative 6 will give me negative 30. Added with positive 30, this gives me 0. So clearly f of 2 is equal to 0. So this means x is equal to positive 2 is a rational root. Is a rational root. So that I have identified. Now I can move on to substitute one more quantity. Say if you were to substitute x is equal to 1 over 2 it will provide you with another rational root. You can try that out. Now, what is the main advantage of rational roots theorem? Number one, it gives us all possible rational roots for a function. Number two, it allows us to check with the values and find out which works out and which doesn't work out. Number three, once we know the rational roots, there are other techniques available by which we can find out irrational roots. The next advantage would be, once we know the rational roots, we can easily graph the function. We can graph the polynomial. So these are some of the advantages of the rational roots theorem. So we will move on to the next topic, students. Students, in this class we are going to be looking into quadratic function. Now, quadratics have got many applications in the field of engineering, so specifically in optimization techniques. So it is imperative that we understand quadratics and how to factor them and how to get the roots. Now, the word quadratics has been derived from the word quad, so which means 2. So we are talking about equations or functions which are of degree 2. So the general form of a quadratic equation will be in this fashion: ax squared positive bx positive c, where a, b, c are constants. Now, the domain of the quadratic functions is going to be stretching from negative infinity to positive infinity, meaning all real numbers are possible. So that is the understanding. Set of real numbers will form the domain for a quadratic function. Now, having mentioned that, there are many ways to solve a quadratic equation. So when we are talking about equation, the equation is of the form ax squared positive bx positive c is equal to 0. Now, we are going to look into a few methods. So the first method would be using the formula, the quadratic formula. The second method would be using the vertex form. So I'll be explaining to you these forms. The third method would be using what is called as the intercept form. Of course, you can also solve a quadratic function using graphical method. So as of now, we will start off and understand how to use the quadratic formula. The quadratic formula, say for example you are given a function, say f of x is equal to ax squared positive bx positive c, and taking the equation ax squared positive bx positive c is equal to 0, the root for this equation is given by x is equal to minus b plus or minus root of b squared negative 4ac divided by 2a. So this is how we get the root. Now let me show you an example. We are given, say, a quantity like this, say f of x is equal to 2x squared negative 8x positive 3. This is a quadratic function, and we are converting it to an equation. 2x squared negative 8x positive 3 is equal to 0, and we are getting the values of a, coefficient of the leading term, b, coefficient of x term, and c, the coefficient of the constant. In other words, I should say the constant term. So the formula, substituting in the formula, in 1, I'm taking that as 1, we get, so what do we get when you substitute in 1? Negative b is negative of negative 8 plus or minus root of negative 8 squared negative 4 times a times c is 3 divided by 2 times of 2. Now this is equal to 8 plus or minus root of
negative 8 squared 64, negative 4 times 2 8, 8 times 3 24, divided by 2 times 2 is 4. So this is going to give me 8 plus or minus root of, now 64 minus 24, that's going to give me 40. So it's going to be root of 40 divided by 4. This can be rewritten as 8 plus or minus 40. I can rewrite 40 as, say, 4 times 10 divided by 4. This can be rewritten as 8 plus or minus root of 4 times 10 is going to be 2 times root of 10 divided by 4. Now I can take 2 out and rewrite this as 4 plus or minus root of 10 divided by 4, which would give me, 2 can cancel out with 4, giving me 4 plus or minus root of 10 divided by 2. So this is the root. So why do I use this quadratic formula? Normally, to get this root, it will be a challenging quest for us if we are going to use any other method. But with quadratic formula, it is nicely done. So students, having obtained this actually means that we have got 2 roots. So one is going to be x1 is equal to 4 plus the root of 10 divided by 2. Of course, I can simplify this and rewrite this as 2 plus root of 10 over 2. And the other root is going to be 4 negative root of 10 over 2, which can be simplified and rewritten as 2 negative root of 10 over 2. Now, I just want to apply factor theorem here to show you the check. Rewrite this root in this fashion as a factor form. So it's going to be x negative of 2 positive root of 10 over 2 and x negative 2 negative root of 10 over 2. So this is how I'm writing it. Since we're talking about equation, I'm taking it to be equal to 0. So I'm going to simplify this and get back this equation. And if I get back that equation, then clearly this is indeed the root. So this is just for a check. You don't have to do this every time you're asked this question. So this can be rewritten as x negative 2 negative root of 10 over 2 and x negative 2 followed by positive root of 10 over 2. And of course this is equal to 0. Now this is nothing but x negative a multiplied with x positive a, which will give me x squared negative a squared. So this is an algebraic formula I'm using here. So this is going to be 2 times of x negative 2 whole squared negative root of 10 over 2 squared and equal to 0. So this is rewritten as 2 times of, I expand this, I get x squared negative 4x positive 4. I expand this is going to give me negative root of 10 squared is going to be 10, 2 squared is going to give me 4 is equal to 0. So this is nothing but 2 of, if I were to simplify these two, this will give me x squared negative 4x 16 negative 10 divided by 4. So that is going to be positive 6 over 4 equal to 0. And if I were to multiply 2 inside by distribution, this would give me 2x squared negative 8x, and 2 multiplied with 6 over 4 can be written as positive 3 is equal to 0. So this is exactly what we started with, 2x squared negative 8x positive 3. So that means our technique of quadratic equation solution, the method we adopted is perfectly right and the root is also right. So next I will show you how to handle questions in vertex form. Welcome students, in this class we will learn about the vertex form. Now we are given a quadratic equation or quadratic function, I should say, ax squared positive bx positive c. Then the vertex form is written as a times of x negative h raised to the power 2 positive k. So this is how we write the vertex form. where h comma k is the vertex. So that is how we use this technique. Now let me give you an example to understand the vertex form. Now why do we use this vertex form? Because for graphing it comes in very much handy. Now the value of a, say, you have to understand one more thing. The equation of a quadratic function will always lead us into a parabola. If we were to graph this, we would always get a parabola. Have that in mind. Now, within keeping these things within the scope of the subject, we would be studying about the U-shaped parabola and the inverted U-shaped parabola. Of course, you got the other varieties also, but just to keep everything in concise fashion, I'm just giving you these two examples. Now, we would get a U-shaped parabola if a is greater than 0. The a that we are talking about is present here. Now, if a is less than 0, then we get this inverted U-shaped parabola. So vertex form comes in very much handy to get that graph. Now, having mentioned that, let us do an example to understand this. So suppose I've got f of x to be the same question I'm taking, 2x squared negative 8x positive 3. Then the vertex form, I need to get my a and I need to also get my b. So the h value is obtained as h is equal to negative b over 2a. This is my h value. And my k value is got by substituting this quantity f of negative b over 2a into the function. Now let us obtain the a value. Now a is equal to 2 and b is equal to negative 8. We don't need c there. Now clearly h is equal to negative b, it's going to be negative 8 divided by 2 times a is 2. This is going to give me 8 over 4, which is equal to 2. So h is equal to 2. Now coming to k, k is got by substituting the value of h into the function. So f of 2 is equal to 2 of 2 squared negative 8 of 2 positive 3. This is going to be 2 squared is 4, 4 times 2 is 8, negative 8 times 2 is 16 positive 3. I add 3 with 8, I get 11 negative 16, which is going to be negative 5. So this is my value of k. Now if I were to write the vertex form, so therefore the vertex form is, I'm writing the formula, f of x is equal to a times x negative h the whole squared positive k. So this is going to be 2 of x negative 2 raised to the power 2 and the value of k is negative 5. Now this is the solution. So we are done with this. Now on the left is actually f of x, but f of x is nothing but y. Coming to the graph of this function, if I want to draw the graph, then it can be done as such. Now a is equal to 2, so it's greater than 0, so the parabola is U-shaped. I can write it, parabola is U-shaped, and the vertex is given to be as h comma k, so that means I've got 2 comma negative 5 to be the vertex. So if I were to, and let me, from here I can also get the x-intercept. So the x-intercept, so now to get the x-intercept, we substitute y is equal to 0, right? So if I were to substitute y is equal to 0, we would land up with the equation 2 of x negative 2 raised to the power 2 negative 5 is equal to 0. I expand this, I would get x squared negative 4x positive 4 negative 5 is equal to 0. So expanding it, this is going to be 2 times x squared negative 8x positive 2 times 4 would give me 8, negative 5 is equal to 0. This is going to be 2 times x squared negative 8x, positive 8 negative 5 would give me positive 3 is equal to 0. Now this is exactly the quadratic equation that I showed you and how to obtain the values of x, and we have achieved the values of x, and that is going to give me the x-intercept. Now having obtained that, to get the y-intercept, what we need to do is we would substitute x is equal to 0 into the system. So that means this is going to be I substitute x is equal to 0 here, so it's going to be 2 of 0 negative 2 whole squared negative 5, and that would give me negative 2 squared is going to be 4 negative 5. 8 negative 5 is going to give me 3. So this is going to be the y-intercept. 0, 3 is going to be the y-intercept. I have shown you how to obtain the roots. Now, having got all this, let us draw the graph in a rough manner. So this is the intercept. So if I were to show you the graph, I'm going to show it to you here. So this is the vertex actually. This is the vertex. We have got the vertex as 2, negative 5. So it's going to be 1, 2, and negative 5, 1, 2, 3, 4, 5. So this is going to be the point. The y-intercept is 0, 3. So that means 1, 2, 3. So there is a interception over here, 0, 3. The graph is going to intercept at that particular point. Now, the x-intercept, there are two routes for the x-intercept. So with regard to the x-intercept, we have got, in the previous example I've shown you that we have got two roots, so x1 and x2. So one is going to be 2 positive root of 10 over 2, the other one is 2 negative root of 10 over 2. Now this quantity is approximately 1.58. So the first root would be 3.58. Now the second root from 2.0 we have to subtract 1.58. So that would give me 2 and 4 and approximately 0.42. So we have to work only with approximate values in this case. So 3.58, if this is 2, 3.58 would be somewhere over here. So that is for the x-intercept of one value. The other value 0.42 would be somewhere over here. So just to show you how the graph works. So the graph cuts here and it goes through this 0.42 and hits at the vertex and then climbs up. So that is how the graph goes. Now to get the axis of symmetry, that is the center line, x is equal to negative b over 2a, we would be using that value. So that means the line axis of symmetry would be just going along this particular vertex. So this is briefly how to use the vertex form, students, and in the next class I will show you the intercept form. So students, this is how we solve the intercept form. Now I will tell you why do we call this to be intercept form. So how do we get this done? Now foremost, what we need to do is we need to take this constant term and multiply with the constant of the leading coefficient. So in this case x squared is always the leading coefficient since we are dealing with quadratic functions. So take the constant term, multiply with the coefficient of the x squared term. In this case the coefficient is just 1. So 6 times 1, place it here. And then what you need to do is draw a line and place the coefficient of x, which is case negative 5. Now what you need to do, you need to choose two numbers so that when you multiply them you get 6, when you add them you get negative 5. So clearly in this case the numbers are going to be 3 and 2. So 3 times 2 would give me 6, but when I add them I should get negative 5. The only way it is possible is that the sign of 3 is negative and the sign of 2 is negative. So negative 3 added with negative 2 will give me negative 5. Negative 3 multiplied with negative 2 will give me positive 6. Now the question is, how do we write them? The writing is the key. So in this case, when I write them, I just take them as the factors like this. So I just take them as x negative 3 and x negative 2 is equal to 0. That's it. You need to just simply take the number as the factor like this and write it then in this fashion that I've shown you. Do not change the signs, because if I were to express them or expand them, this would give me x into x squared. I can use the FOIL technique, and then x into negative 2 will give me negative 2x, then 3 into negative x will give me, 3 into positive x will give me negative 3x, and then negative 3 into negative 2 will give me positive 6 is equal to 0. When I add them I get the result x squared negative 5x positive 6. So which is what we have got. So in this technique, you got to be extra cautious when you are writing the form. So this is what is called as the intercept form, the form that I have just placed here, because from here, so this is for your understanding, there's nothing to do with this question, just to show you that the check is true, that we have got the function back. And this is what we want. This form is what is necessary. So from here I can clearly say x is equal to 3 and x is equal to positive 2. So these are the intercepts. I can say x intercepts. So have that in mind and we will move on.
Students, in this class we will learn some factoring formulae. The first one is called as the difference of squares. I have introduced it, but just to have a refreshment of the topic, and I'm introducing it here. So what it means is that if we have got, say, x squared negative a squared, then I can rewrite this as a quantity x negative a multiplied with x positive a. So this is a very important formula, or I should say a very important formula that you have to take note, and this will allow us to, in fact, disintegrate a complex square. So having mentioned that, let me give you some examples. So suppose you got something like this, say x squared negative 5, then I can rewrite this as x squared negative root of 5 squared. Now this is nothing but x squared negative a squared form, so this can be rewritten as x negative root of 5 multiplied with x positive root of 5, and we will still get the same expression, x squared negative 5. Now we can also, I want to give you one more example. Say for example you got something like this, x squared negative 36. I can rewrite this as x squared negative 6 squared and then use the difference of squares formula to rewrite x squared negative 6 squared as x negative 6 times x positive 6. So have this in mind. Then moving on, the formula could also be extended to cubes. So this is what is called as difference of cubes. So if we got something like this, x cubed negative a cubed, then I can rewrite this as x negative a times x squared positive ax positive a squared. And on the other end, x cubed positive a cubed can be rewritten as x positive a times x squared negative ax positive a squared. So the difference between x cubed negative a cubed and x cubed positive a cubed is the term x minus a being present here, and the sign of ax is positive here. For x cubed positive a cubed, the term x positive a is present here and the sign is negative. So an example, if I want to show you, say I have, say, 8a cubed negative b cubed, something like this. Now this can be rewritten as 2a raised to the power 3 negative b raised to the power 3. This is actually of the form x cubed negative a cubed, so this is going to be 2a negative b times 2a squared positive 2a. So I'm going to write it as 2ab positive b squared. So this is how we write using the difference of cubes. Students, in this session we will learn about another factoring technique which is called as grouping. Now we are given this expression, we are expected to factor it. So let me take this to be an equation and then proceed on. Now what I'm going to do is I'm going to be grouping 4u cubed with 8u squared, and then I'm going to be grouping 6u with
negative 12. So I would take out 4u squared out, and that would give me u negative, in this case is going to be 2 there, followed by, for 6u negative 12, I'm going to take 6 out, so that is going to give me u negative 2 is equal to 0. Now I can clearly see that u negative 2 is a factor. I'm taking u negative 2 out, and that would lead me to 4u squared positive 6 is equal to 0. And I've got an additional term 4u squared positive 6. So this is actually sum of squares. Sum of squares. And remember, whenever you have sum of squares, they are irreducible. So this is as far as we can go in factoring this particular equation. 4u cubed negative 8u squared positive 6u minus 12 equal to 0 using grouping. Having shown you this technique, it is imperative to remember that this isn't an effective way of factoring, because there are times when this technique will fail. Students, in this class we will learn what is called as quadratics in disguise. Now we have given an equation. This isn't a quadratic because the degree is not 2, but we can convert this into a quadratic by making a sensible substitution. So what I'm going to do first is I'm going to rewrite x to the power 4 as x squared raised to the power 2, and followed by negative 5x squared positive 6 is equal to 0. Then I'm going to make a substitution of let x squared be equal to t. So if I were to name this as 1, therefore 1 can be rewritten as t squared negative 5t positive 6 is equal to 0. Now this is clearly a quadratic. This is a quadratic in t. So we can very well solve this depending upon how you want to solve it. So I'm going to use the quadratic formula. So t is equal to negative b plus or minus root of b squared negative 4ac divided by 2 times a, where a is equal to 1, b is equal to negative 5, and c is equal to 6. I substituted all this information in the formula. That's going to be negative of negative 5 plus or minus root of negative 5 squared negative 4 times a times c divided by 2 times a. This is equal to positive 5 plus or minus root of negative 5 squared is 25, followed by negative 24 divided by 2. This is 5 plus or minus root of 25 minus 24 is going to give me 1 divided by 2. So therefore t is going to be 5 plus 1 over 2. That's going to be one root, which is 6 over 2, which is 3. The other root is going to be 5 negative 1 over 2, which is 4 over 2, which is equal to 2. But my value of t is x squared. So this means x squared is equal to 3 and x is equal to root of 3 plus or minus. Also x squared is equal to 2 and x is equal to plus or minus root of 2. So therefore the solution is we got plus or minus root of 2 and plus or minus root of 3. So 4 roots we have got by understanding this technique, quadratics in disguise. Students, in this class we will learn about polynomial inequalities. This concept is very important for handling questions related to optimization and curve sketching, and it is imperative that we understand how to handle polynomial inequalities. I've got 2 questions here. The first one is a linear inequality. The second one is quadratic inequality. I'll show you how to solve the linear one. So let us consider the linear one first. 5x positive 7 greater than 6. I add negative 7 both sides. When I do that, I get 5x positive 7 negative 7 greater than 6 negative 7. positive 7, negative 7 gets cancelled, giving me 5x greater than negative 1. Now I divide by 5, so that would give me 5x over 5 greater than negative 1 over 5, which would give me x greater than negative 1 over 5. So that means if we are going to write an interval notation, this is true for all x element of negative 1 over 5 to infinity. So that is the understanding. Now if I were to place, just to check, x is equal to 2, clearly it is satisfying, right? And you can just try other values for which x lies in this range, and you will find that it is going to be true. So that is an easier way to solve linear inequalities. Now next, what we are going to do is we are going to solve this quadratic inequality. Now we cannot handle the procedure that we have followed here for quadratic. It is not going to be working out. So for this, what we are going to do is I am going to move all these to the left side. So it's going to be x squared negative 5x positive 6 is greater than 0. So the idea is to obtain the factors for x squared negative 5x positive 6. From there we would be able to obtain the intervals for x for which this quadratic inequality holds good. Now having mentioned that, in the previous class I have shown you how to factorize this. Clearly I know that negative 2 and negative 3 are going to be the factors, so I can use them over here. So x negative 2 is going to be a factor and x negative 3 is going to be a factor. Clearly when you multiply you get this, so this is going to be greater than 0. Now what we are going to do now is to use the sign diagram. Now how do we use the sign diagram? So just draw a simple straight line and mark these points as 2 and 3. Now why do I say place 2 and 3? Because 2 and 3 are the roots. X minus 2 is a factor, but x is equal to 2 is a root. And similarly x minus 3 is a factor, x is equal to 3 is a root. Now what we need to do, we need to know the signs. Now pick any value. Say I'm going to take x is equal to 4 here and I substitute it here. Now clearly when I substitute x is equal to 4, I'm going to show you 4 negative 2 times 4 negative 3. This is going to give me 2. This is going to give me 1. 2 times 1 is equal to 2. It's clearly greater than 0. So over here I'm going to get positive always, no matter what value you're going to take. Now on this end, imagine I'm taking a value which is negative 1. So let me take x is equal to negative 1, substitute it over here. So negative 1 negative 2 times negative 1 negative 3, this is going to give me negative 3, this is going to give me negative 4. Multiplying negative 4 with negative 3 will give me positive 12, which is greater than 0. So this is going to give me positive. I would say between 2 and 3, let me take a value 2.5. If I were to take x is equal to 2.5, now what happens when I substitute? I'm going to show that over here. Now taking x is equal to 2.5, which is present between 2 and 3, I would get 2.5 minus 2 times 2.5 minus 3. Now this is going to give me 0.5, right? 2.5 minus 2 is going to give me 0.5, but over here I'm going to get negative 0.5. So that means the inequality fails here. It doesn't hold good. So in this case I'm going to get only negative values. So there is a failure of the inequality. Now having obtained this information, we are talking about all values of x, that is from infinity, negative infinity to 2. So let me write that down, negative infinity to 2, and I am talking all values that are from 3 to positive infinity. 3 to positive infinity. So that is how we do inequality involving quadratics. So this is the solution. So we will go on to the next example, students. So in this class we will learn how to solve this cubic inequality, students. So foremost what I want to do is I'm going to move everything that I see here towards the left side. So that would mean I have now x cubed, negative 2, negative x, positive 2x squared greater than 0. I can rewrite this as x cubed, positive 2x squared, followed by negative x, negative 2 is greater than 0. Now I'm going to use the technique of grouping. I'm going to group them like this. So from the first I'm going to take x squared out. This would give me x positive 2. From the second I'm going to take negative 1 out, and that would give me x positive 2 greater than 0. Clearly x positive 2 is a factor. I can take that out, and that would give me x squared negative 1 greater than 0. By the concept of difference of squares, I can rewrite x squared negative 1 as x negative 1 multiplied with x positive 1 greater than 0, and this is going to be x positive 2. So from here I can get the roots. So the roots in this case is going to be minus 2, positive 1 and negative 1. So I'm going to use the sign diagram. So if I use the sign diagram, so it's going to be negative 2, negative 1 and positive 1. So from this sign diagram we need to find out the intervals for which the cubic inequality holds good. This is what we have got. We have got x positive 2 times x negative 1 times x positive 1 is greater than 0. So what I'm going to do is I'm going to choose a value that is present onto the left of minus 2. So I'm going to take x is equal to negative 3. When I do that, negative 3 positive 2, negative 3 negative 1, negative 3 positive 1. So this is going to give me negative 1. This is going to give me negative 4. This is going to give me negative 2. So negative times negative positive, and this is going to give me a negative. So this is not going to be greater than 0. It's going to be a negative value. This is a negative value. So this is negative. Now if I were to pick a value between, or I would say let me go to the other extreme. So let me take a value x is equal to 2. So I substitute it into this inequality. So 2 positive 2, 2 negative 1 and 2 positive 1. So clearly I can see everything is going to be positive here. So this is positive. Now between negative 1 and 1 I have a 0 there, right? So let me substitute the value 0 here. So if I were to take x is equal to 0, I would get 0 positive 2, 0 negative 1 and 0 positive 1. Now this is going to give me a negative value. This is going to be negative. Now I have got a negative here. So now the question is, what would happen if I take a value between negative 1 and negative 2? So let me take x is equal to 1.5. I'm going to take this value. Now if I were to take negative 1.5, I'm substituting it into this inequality. So that's going to be negative 1.5 positive 2 times negative 1.5 negative 1, negative 1.5 positive 1. Now this is going to give me a positive value. I get a positive here. This is going to give me a negative value, and this is going to give me a negative value. So negative negative positive times positive will be a positive value. So this is going to be positive. So for this inequality to be true, the understanding is x should be an element of negative 2 to negative 1 union 1 to infinity. Now if in case we have been given a sign that is greater than or equal to, then say for example, instead of the question being x cubed greater than 2 positive x negative 2x squared, instead of this, if they would have given a greater than equal to sign, then the solution would be x element of negative 2 comma negative 1 union 1 comma infinity. So we would have a square parenthesis. So students, this completes our study on polynomials. We will go on to the next topic. Students, in this class we will learn about rational expressions. Now, rational expressions are obtained by having a polynomial in the numerator and a polynomial in the denominator. So if I were to define it, I can say an expression of the form p of x over q of x such that q of x is not equal to 0 and p of x and q of x are polynomials. So this is the exact information or definition that we need to work with rational expressions or rational functions. So if I were to place f of x here, this would become a rational function. Now I'm going to give some examples and show you how to solve them. So example number 1, let me consider a rational expression of the form 4x cubed negative 6x squared over say 2x or 3x, something of this fashion. Now numerator is a polynomial, denominator is a polynomial, and clearly this is not equal to 0, so this is a rational expression. If you want to solve this, what I'm going to do, I'm going to take x squared out. In fact, I can take 2 out also. So this would give me 2x, because 2x times 2x squared will give me 4x cubed, followed by negative 3. So this is what I got, divided by 3x. So clearly an x and x can be cancelled, giving me 2x times 2x negative 3 divided by 3. So this is the reduced form of the expression. Now if in case we have anything of this fashion, say 2x positive 4 divided by x squared positive 5x positive 6, then I can rewrite this by taking 2 out. So it's going to be 2 of x positive 2 divided by, now x squared positive 5x positive 6, this can be factored and rewritten as x positive 3 times x positive 2. So x positive 2, x positive 2 can be cancelled, giving me 2 over x positive 3. So these two examples are given here to show how we can solve a rational expression. So we need to specify the domain. So this is basically defined, you can write it here, defined for all x which is not equal to negative 3. So that would complete our solution for this question. Let me give you one more example. Example number 3. Suppose you are given a function, say f of x is equal to say 2x to the power 3 positive 4x squared divided by say 8x to the power 2 negative 16x, something you've got like this. Now as usual, I would try to factor things out. One important caution is don't go and cancel these x squares out. That's not going to work. If you are interested to simplify this, the first and foremost thing that you need to approach is through factorization. So without that, don't touch any terms. So having mentioned that, from the numerator I'm going to take 2x squared out, and that would give me x positive 2. So clearly 2x squared times x would give me 2x cubed, and 2x squared times 2 would give me 4x squared. So from the denominator I'm going to take 8x out. So this is going to give me, I can cancel the x out, I can cancel the x here, and 2 divides here 4 times. So this is going to give me x of x positive 2 and 4 of x negative 2. So this is the final simplification for this particular function. However, we need to state this. This is defined for all x which is not equal to 2.
So if it is equal to 2, the function vanishes. Continuing on our studies on rational function, in this section we will learn how to find the domain of a rational function. And I will start with some basic examples. So foremost, let us consider f of x to be equal to x positive 5 divided by x squared positive 8. Now, this function is valid as long as the denominator is not equal to 0, or the denominator doesn't become equal to 0. Once the denominator becomes equal to 0, the function goes undefined. Now, clearly we see that x as a degree 2, that means it will always return a positive value. So, the function f of x as a domain for all x present in the interval negative infinity to infinity. So that is the solution. Because why? Because x squared positive 8 is always positive. So that's the reason. So let's do another question. Example 2. Now this is example 1. Now imagine you are given f of x to be equal to, say, 2x positive 9 or 2x positive 91 divided by 2x squared positive x negative 15. Now f of x is defined as long as the denominator doesn't become equal to 0. Now let us consider 2x squared. So let me write it down here. Let us consider 2x squared positive x negative 15 to be equal to 0. Now clearly upon solving, we can find the roots to be as x is equal to negative 3 and x is equal to 5 over 2. Because if you were to substitute x is equal to negative 3 here, this would give me 2 of negative 3, negative 3, negative 15. This is negative 18. This is 9. 9 times 2 is 18. 18 negative 18 is 0. So clearly x is equal to negative 3 will be a root, and also you can try that out. X is equal to 5 over 2 is also a root. Now if you were to draw the number line and place the point, say this is 0. Now 5 over 2 is over here and negative 3 is over here, right? Just for assumption. Now at this point, at this particular point, negative 3 and 5 over 2, the function vanishes, the denominator vanishes. So f of x is defined only at places from negative infinity to negative 3, and these 2 points are not included. So the region in between is defined. So negative 3 comma 5 over 2 union and the region that is present beyond 5 over 2. So that's going to be 5 over 2 comma positive infinity. So this will be the region for which the function is defined. Thank you, students.
Welcome, students. In this class we will have a review of functions. Now while doing calculus, it becomes necessary to understand functions at least to some level of detailness. So having mentioned that, it is important for us to know the types of functions. Now you got to know that functions are actually classified based on the following 4 types. So these are the following types that I'm going to give you here. So a function is classified based on the set of elements. You can say set elements. Number 2, based on the equation. Number 3, based on the range. Number 4, based on the domain. Now, let us see based on the equation. So if I were to write f of x is equal to, say, 5x negative 2, this is a linear function. If I were to write something like this, say x squared negative 5x positive 6, this is a quadratic function. So I am classifying the function based on the equation. And still further, say if I were to write f of theta is sine squared theta negative 2 times cos 2 theta, this is a trig function or trigonometric function. And if I were to write, say, something of this fashion, f of t is equal to gt squared negative 2t. Now this is a function is based on the time. Please don't think that function should always involve just x's, because here we have a function which involves time, and this is also a function. Now, having mentioned that, you have to understand that we have different types of functions in mathematics, and it is just important for you all to know that we have something called as the common, let me write it down here, common functions. This is the most common types. And then we got inverse functions. And then we got complex functions. We got distribution functions. So these are some of the examples. Now remember that functions involving two variables, for example, you might also come across functions involving two variables. Functions involving two variables. Say, for example, a is equal to half times b into h. This is a, which and b and h are, b is the base, h is the height. Now, in this case, you have to understand that the function has got two variables. So, types of functions like this, we call them as multivariate functions. Because of physical constraints, there are cases where only positive values are taken when we are calculating the values. Now, having given you the examples, certain examples of functions and their different types, let us now define what is a function. Now, you have to understand that there are two ways in which we can define a function. So I'm going to give you the common way. So what is a function? And then I will give you the mathematical way. So it is a rule, or you can say a law, that defines a relationship between two variables, where one is called the independent variable and the other dependent variable. Now, this is basically the common man's definition, but there is something called as the mathematical definitions of a function. So I'm going to give you that mathematical definition here. So this is the mathematical definition of a function. So we start with, let x and y be two sets. A function from x to y is a rule that assigns to every x element of x to an unique y element of y. So this is important, unique. So having mentioned this word unique, this would be the important word for which we will use to define if a relationship is a function or not. So this comes in handy to ascertain whether a relation is a function or not. So these are some of the important concepts of functions. Now in your study you will be studying the following types. The following types will be studied. So what are those? You will start with linear functions, and then you will also study power functions, quadratic functions, rational functions, exponential functions, logarithmic functions, and of course sinusoidal or sinusoidal functions. So these are some of the important functions that we will study in this course. Now this is an important question that you need to know. Why study functions in calculus? Now the most important challenge in a function is to define a function, and calculus helps us. So we can always, for example, I can give you this, say y is equal to sine x is the solution of the differential equation. So this is a very important topic. Differential equation, say d squared y over dx squared positive 2y is equal to 0. So this trigonometric function is defined by this differential equation with certain conditions, having y is equal to 0 and dy over dx is a change, dy over dx being equal to say 2 when x is equal to 0 and y is equal to cos x. So this is just some basic understanding or basic way to define a function, and y is equal to cos x is the solution of the same equation, having y is equal to 1 and dy over dx is equal to 0 when x is equal to 0. So you don't need to confuse yourself with all those things that I've written. When time comes you will be able to understand it. So the focus point that I would want to show you here is how exactly this function is defined using the differential equation. So that is the reason we use functions in calculus. In fact, anything that is physically occurring or happening can be called as a function. See, even the food that you eat, say for example you as a body, there are some foods which you eat will elevate your energy levels, and there are food that you might eat will bring your energy level down. Right? So say for example coffee, when you drink coffee your presence of activity goes up, but instead of coffee, suppose you take some heavy food, instead of not drinking coffee you take something heavy food, your level of activity goes down. So there is again some change in the entire physical body. So everything can be connected to a function. So that's why functions are very important in calculus.
Students, in this class, it is necessary that we have a concrete understanding of the concept domain and range. Now, I have a function, and the function is represented in this fashion. Now, this fashion is called as the rooster form. Now, you have to understand that there are different ways in which a function can be represented. So, the first way, popular way, is called Venn diagram, and the next way is graphical method, and the other most popular way is called as the rooster form. So what you're seeing is the rooster form. Now we have a function and it is represented in this fashion, and we are asked to find the domain. Now the domain is all values that you see occurring as the first element. So write that down: 1, 2, 3, 4. This is the domain. Now the other term is range. Now range is the second value that you see here. So in this case it's 1, 4, 9 and 16. 1, 4, 9 and 16. So what do you understand here? The first elements are nothing but x values that we take, x element of real number, and this x is called as the independent variable. And the next values that you see here, they are all y, and this y is called as the dependent variable. So always remember, for every x there should just be a unique y. For every x that you take, there should be just one unique y. As I mentioned to you, there are different types of functions, but these types of functions are actually further classified. Okay, they are further classified into one-to-one function, or you can write it like this: 1-to-1 function, and many-to-one function. There's also a classification called many-to-one functions, and onto function, and one onto function, one onto. I would say there are many types into which functions are further classified. In the beginning I told you, I gave you an illustration based on elements. So all of these things, they come on based on elements. Now there is also based on equations. There is also a classification based on equation. I don't want to go forth onto writing down the different classification. Maybe I will give in a small notes on this video. So just to mention, based on the equation. Now you can also classify the function based on the equation. So you can say whether the function is an identity function, so that is also a type of function, or is it a linear function? I gave you some examples of linear function. Or is it a quadratic? Is it a quadratic function? Is it a cubic function? So these are some of the ways in which, or some of the types of functions, cubic functions, or is it a polynomial functions, right? So for now, just to have a recap, it is imperative that we understand how we are finding the domain and the range. Now, whenever we have a function, the symbolic way to represent a function is f of, say, x going to y. This is the way we represent a function. Sometimes we also represent it like x going on to y, like this. In calculus, you have to understand, most of the times we define a function by equation. A function is defined by equations. So have that in mind also. So having given you this
definition and explanation, we will now move on to the next topic, students.
So in this class, students, we will understand the concrete differences between domain, codomain and range. Of course, in the previous illustration there weren't much difference between the codomain and the range in the example that I showed you, but in this illustration you will clearly understand how codomain and range are totally different. And for that, what I'm going to do is I'm going to consider this illustration. F of x is equal to 3x positive 1, and I'm going to say the domain to be equal to elements 1 to 5, and the codomain is going to be equal to elements from 1, 2, 3 to say 50. This is the codomain. Now for every x from the domain, if I were to make this representation, so let me take this as x and let me have this as y. In x I've got 1, 2, 3, 4 and 5, and y goes from 1 to 50. Now when x is equal to 1, f of 1 is equal to 3 of 1 plus 1. So the input value is 1, output is going to be 4. Input value is 2, output value is going to be 7. Input value is 3, output value is going to be 10. Input value is 4, output value is 13. Input value is 5, output is 15 and 16. So 1 is going to 4 and 2 is going to 7, 3 is going to 10, 4 is going to 13 and 5 is going to 16. Now this is a function. So f of x going to y is a function. So that we have got. Now the domain is clearly given there. This is the domain, x values. Now the codomain is all probable values that f of x can take. So that is the understanding here. So that is a larger set. But when we're talking about the range is nothing but what is the actual output. So that is important. Probably in classes that you have heard or see, that emphasis would not have been made, or it would have been accepted that the concerned student has understood. So that assumption is sometimes to be avoided, or it can be a pitfall. So that's why I'm trying to explain you here what is the difference between the term codomain and range. So range is what actually comes when you put in the value. So all these fall under the category of range. So when you talk about codomain, the possibilities that can actually occur. So that's why we state the codomain to be a larger set at times. So having said that, it is important that you don't need to think that codomain will always be bigger, or it will not include the range. At times, in the previous cases, illustration which I've showed you, the codomain and the range was very much same. They were equal because of the values that we have taken. So everything matters on the values that we take. Say, imagine they have given the codomain as just 4, 7, 10, 13 and 16. So the codomain and the range are basically one and the same. But the major distinction comes if we have to make a distinction. Then the distinction is codomain is all possibilities that can come out when you put in the values of x for a function, and the range is what actually comes. So that is the difference that you have to know. Now, having mentioned this, one important thing that you have to know is, okay, let me give you this illustration.
I've got 1, 2, 3 and 4, and I've got elements from 1 to 100, and I've got 4 here, and 9 and 16. So this is A, this is B, and we got a function defined as f of x is equal to x squared. So 1 is going on to 1, 2 is going on to 4, 3 is going on to 9, 4 is going on to 16. So the domain is 1, 2, 3, 4. The codomain is elements from 1 to, imagine 2 is also there. So the codomain for this set is 1, 2, etc. up to 100. The range for this is going to be 1, 4, 9 and 16. So this is the range. Now I've got a question. Imagine there is a presence of -2. So that means the domain has a -2 here. It is newly added. Now is it okay if I send this -2 to 4 by this function definition? Will that constitute a function? Think about it. Tell me yes or no. For 3 seconds. Okay, 3 seconds is up. The answer is yes, it still constitutes a function. From definition, it is okay to have more than one element in this domain to have a mapping on to a single element in the codomain. In other words, it is okay for 2 to go to 4. It's also okay for -2 to go to 4. But what is not okay? One cannot go to 1 over here, and one cannot go to some number over here, say 100. This is not okay. So I can always have 2 and -2, say going to 4, 5, 6. This is okay. Say x, a and b, and this is still a function. It's okay that elements are left out in the codomain. It doesn't matter. So the range in this case is just going to be 4. The range is just going to be 4 here. Of course, the domain is going to be -2, 2. The codomain is 4, 5 and 6. That's fine. So this is still a function, but on the contrary, if you got a and you got a b and you got a 2 and a -2 and you got a 4 and a 5 and a 6, 2 going to 4 here, -2 going to 4 here, and 2 also going to 5. This is not a function. It's not a function. Because 2 is going to 4, 2 is going to 6. So have that distinction in mind.
Students, in this class we will understand the function notation. Now, whenever we say f of x is equal to, say, x squared negative 5x positive 6, the understanding is that x can take values from the real number, any values from the real number, and produce an output. So this is like a computer program. Now imagine you're writing a C program. Say you have a company and you want to find out what is the age of your employees. So what is the input that you would give? So the input, this particular C program needs an input, right? So an input is given to this C program, and it produces as an output the age. So it can be age of your employee. Say for example you want to find the age of Catherine and Alan, right? So Catherine gives the age, I would say gives the date of birth into the program, and she gets the age. Similarly, Alan, he gives the input into the program, and Alan gets his age. So just like the computer program,
function is actually a mini program. So what exactly we are doing here is we are feeding in x values into the function, and the function produces an output. So that is exactly what is going on. So in other words, if I were to say R to R, so this is my domain, this is my codomain, and I'm taking an x element of R, say for example x is equal to some 2, then my output has to be produced using the following notation. So f of 2 is going to be, I'm going to put in the input into the program. This is my program. So 2 squared negative 5 of 2 positive 6. This is going to be 4 negative 10 positive 6. I add 4 with 6. I get 10 negative 10, which is equal to 0. So the output is 0. So similarly, if I were to feed in negative 2, x is equal to negative 2. Clearly negative 2 is the element of real numbers. So the output has to be obtained using the following notation. So negative 2 raised to the power 2, negative 5 of negative 2, positive 6. Negative 2 squared is 4. This is positive 10, positive 6, and the output is going to be 20. Now you can give any input into the function. So you can also give, say, some a present in real number r. Then f of a is going to be a squared negative 5 times a positive 6. So this is going to be a squared negative 5a positive 6. So this is going to be the outcome, mean value. Now imagine you have, say, some y I'm taking, and we are asked to find f of y. So in that case, f of y is going to be y squared negative 5 times y positive 6. But y is not defined. But suddenly, somehow you get y to be defined as f, in other words, y being equal to x positive h. And h is some small value. You would get to see this small value when you study the concept of limits. Now, having mentioned this, to obtain the value of the function, we need to substitute this f of x plus h. That's the way it is done. Don't simply place this positive h and conclude that to be the functional value. It doesn't work out like that. So in place of y, I substitute x positive h, I raise it to the power 2, followed by negative 5 times x positive h positive 6. So this is equal to, expand this, I get x squared positive 2 times x h positive h squared negative 5 times x negative 5h positive 6. So this is going to be the output that we get when x positive h is substituted for y. So this is how the notation works, and this is how the output is produced. So we'll move on to the next topic, students. So students, continuing on our studies on notation, imagine you are given this function f of x is equal to 1 over x squared negative 5x positive 6. We are asked to obtain the domain of this function. DOM stands for domain. We want to get the domain of this function. So foremost, what we would do is we would rewrite this rational functions in factor form as x negative 3 times x negative 2. If you were to multiply, you get x squared and negative 5x and positive 6 clearly. Now we are interested in finding those values for which the function vanishes. So that means the denominator will become 0 for those values. So we don't want to add those values as our domain. So clearly we can see that x cannot be equal to 3 or x cannot be equal to 2. So when x is equal to 3, I should say the denominator vanishes. Similarly, when x is equal to 2, the denominator vanishes. So we don't want these two values to be part of our domain. Now when we are writing them, in other words, when you're writing the domain, we should write it in this fashion. Now this is called the set builder form.
So this will be more popular when you're studying abstract algebra or modern algebra. Even in discrete mathematics, this set builder will feature. So how do we start? This is called as flower parenthesis. So we are talking about all x element of the real number. This slash means such that. Okay, such that x is not equal to 2 and x is not equal to 3. So we want to avoid these two numbers in our domain. So that's the way we write. So this is one of the example that I would suggest that you go through. Now the next example. Let me consider this example. Say g of x is equal to square root of 36 negative x squared. Now, since we are only dealing with real numbers, not complex numbers or imaginary numbers, we cannot have this quantity to be complex or imaginary in nature. We want this quantity to be real number always. So we don't want any negativity inside this radical sign. So that means we are always interested in 36 negative x squared being greater than or equal to 0. Now I want x squared to be featuring as the leading term. So what I'm doing, I'm going to be multiplying by negative 1. So when I do that, the inequality gets reversed. So I would get x squared negative 36 is less than or equal to 0. Now this can be rewritten as x negative 6 and x positive 6, which is less than or equal to 0. And from here I clearly know that x cannot be equal to positive 6 or x cannot be equal to negative 6. So these two values have to be avoided. I don't want them to be forming or being a part of my domain. So I write it like this. Domain of G is equal to collection of all x element of real number such that I have x featuring in this region. X is greater than or equal to negative 6 and less than or equal to positive 6. So this is how I write. Now if you want to write it in interval notation, this is interval notation. If you want to write it in interval notation, then it's going to be negative 6 comma positive 6. And similarly, if I want to write the previous question, if I want to write this in interval notation, so clearly you can place 2 over here and 3 over here. So for values of x between 2 and 3, say I take x is equal to 1. If I want to take x is equal to 1, this is going to be 1 over 1 minus 3 and 1 minus 2, which is going to be 1 over negative 2 and negative 1, which is 1 over 3. So this inside this is going to be a positive region. So this is going to be positive. So if I were to take x is equal to 4, then I get 1 over 4 negative 3 times 4 negative 2, and this is going to be 1 over 1 of 2. So it's going to be 1 over 2. It's going to be positive. So I get a positive value here. And if I were to take, say, x is equal to 0, x is equal to 0 would give me 1 over 0 minus 3 and 0 minus 2. So it's again going to be a positive value. So now why am I showing you this values? In case if we have an inequality, then this is how you have to use the rule of sign. Okay, so you can judge the intervals. So if I were to write the interval notation for this domain, then it's going to be all values from negative infinity. Of course I have not taken a negative value, so let me just take a negative value to show you. So if I were to take x is equal to, say, x is equal to negative 1, then I would substituting it in this function 1 over negative 1, negative 3 and negative 1, negative 2. So this is again going to be a positive value. You see that? This is again going to be a positive value. So
coming back to writing it in interval notation, so from minus infinity to 2, at 2 the function vanishes, so x cannot be equal to 2, so don't place 2 there, so it's going to be open interval, union 2 to 3, and then open interval, and then union from 3 onwards I stretch to infinity. Now coming back to this notation, interval notation, so this should be the answer, negative 6 comma 6. It's clearly visible from the output that we have got here. If you really want to use the rule of sign in this case, say for example we have got x negative 6 and x positive 6 less than or equal to 0, all you need to do is draw the number line. This is negative 6 and we got positive 6 here. We need to get this inequality satisfied. Now suppose if I take a value say beyond 6, say x is equal to 7, this is going to be 7 negative 6 times 7 positive 6. Clearly this is going to be a positive value, so this side is going to be positive. Now I take a value beyond x is equal to negative 6, so imagine I'm taking a value x is equal to negative 7. So in that case, negative 7 negative 6 times negative 7 positive 6. So this is also going to be positive, right? This side is also going to be positive. Now if I were to take a value between negative 6 and 6, say let me choose a value x is equal to 0, right? If I do that, I get 0 negative 6 and 0 positive 6, which will clearly satisfy this inequality. So it's only true in this region. So that's the reason I placed negative 6 comma 6.
Students, in this class we will learn about the graphs. Now graphs gives us a visualization of a function, or in fact of any given function. Now as I mentioned to you in the earlier classes, graphs along with the Venn diagrams, they are pictorial representation. Now while coming to graphs, you have to understand that a connection has been made between algebra and geometry, because long time ago, before the coming of René Descartes, algebra was totally an independent field and geometry was also an independent field. There was no connectivity between these two areas up until the time René Descartes came in, and he said, well, he was sleeping on his cot and one fine day he saw a fly which was moving, right? And then he said, well, this fly is going here and there. I can clearly describe the path of the fly if only I know the distance of the fly from the two walls. So this is going to be the x-axis wall and y-axis wall according to him. And from here clearly you will be able to locate the coordinate of the fly given x and y. So René Descartes was a revolutionary mathematician who was able to come up with this idea. Up until that time, these two areas, these two huge areas, algebra and geometry, were thought to have no links at all. And that is the reason this particular grid that we are talking about is actually called as the Cartesian coordinate system. Why do we call it as Cartesian coordinate system? Because of the presence of the x and the y. Let me give you the definition of a graph first. So that would form a better idea. Now say you have this y is equal to some f of x, that's given to be as x squared negative 5x positive 6, some quadratic function. Now if I were to ask you to produce the graph of this function f of x, then it is defined in the following manner. The graph of this function f of x, which is stretching from say x to y, is nothing but the set of all ordered pairs
remember the word, this is the key word, ordered pairs, x comma y, element of capital X cross capital Y. Now this is called as the Cartesian product. Okay, so that means we are taking an element x from this capital X and an element y from this capital Y, and their order matters a lot. This is very critical, such that for any y we got f of x. So this is the definition when we talk about graph. Now you don't need to be much worried about these Cartesian products. So this is how we represent Cartesian product. The understanding is that we take an element x from capital X and a y from capital Y. We call this as ordered pair because x comma y is not the same as y comma x. So that is the catch here. But these are all just information given to you. Now having mentioned this, if I want to graph this y is equal to x squared negative 5x, what we usually do is we take the value, say we take x is equal to 0. When x is equal to 0, we get the value 6. So when x is equal to 0, I get the value of y to be a 6. So that 6 is going to be somewhere over here. And when x is equal to, say, 1, when I substitute x is equal to 1, I get 1, negative 5, positive 6. That is going to be 7, negative 5. That's going to be y is equal to 2. So when x is equal to 1, if 1 is over here, then the value of y becomes equal to 2. So that 2 is going to be present somewhere over here. Now if I were to plot it, I have to find the intersecting point, right? I have to find the intersecting point, but that is a different concept altogether. So in general, if I were to plot the graph for this function, what I have to do is, what I would do is I would have to take the values of x is equal to 1, x is equal to 2, x is equal to 3, then try to plot it. So this is the way the plotting took place. But this is an inefficient way and it is time consuming, because just to know where exactly the intersection takes place over here, I need to spend probably, who knows, maybe hours together to find out this intersecting point. If you have a program, if you are a software at your disposal, then it would be a simple thing. But we don't have that privilege. So in other case, what we have to do is just to take in the values and put it into the function and obtain the value, relative value of the f of functional value, and then plot it. So that is Herculean. So having mentioned this, in the following classes, I will be showing you how to plot the graph.
Students, in this session, we will understand how functions work in case of arithmetic. So in this class, we will learn about function arithmetic, and more so in specifically addition, subtraction, multiplication, and division. So I'm going to take an example to make this concept more clear. So let me consider f of x to be equal to root of x positive 1 and g of x to be equal to 1 over, say, x negative 3. Now, according to function addition or function arithmetic for addition and subtraction, suppose you are expected to obtain f positive g of x, then the operation on the right is going to be f of x added with g of x. Now similarly, if you are given f negative g of x, on the right it's going to be f of x negative g of x. So this is how the addition and subtraction works. Now let us perform the addition here. F of x is given to be root of x positive 1. So that means when x is equal to negative 1,
I still have f of -1 to be equal to 0, which is acceptable. But when x is equal to -2, f of -2 is root of -2 positive 1, root of -1. This is not acceptable because the domain being set of real numbers. So if I were to write the domain of f, then the domain of f would include all values from -1 to infinity. So this is going to be my domain of f. Now if I were to write the domain of g, now g is 1 over x minus 3. Say when x is equal to 3, the function vanishes, g of x vanishes. So we don't want that in our domain. So we can take all values. Say for example you have a number line here, we got 3 here, so we can take all values to the left of 3 and to the right of 3, but not 3. We don't want this 3. So how do I write it? I start with -infinity up unto 3, and then I take a union and then place 3 to infinity. So this is my domain. So I've got the domain for f, domain for g. Now the question comes, how am I going to write the domain of f positive g? So for that we need to take the intersection. The domain of f positive g is going to be domain of f intersecting with the domain of g. So that's how we do it. So if you were to draw the number line, this is 0, this is -1. I am taking all values from -1 to infinity for domain of f. So that would be from starting from here, all the values up unto infinity. This one is included and this is not included. And then the domain of g, -infinity to 3. So -infinity is over here. So from here I go all the way to 3. This is 1, this is 2, this is 3. So all the way to 3. So there is an overlapping here. So there's an intersection here, right? So that intersection is going to be from -1 to 3. 3 is not included here. So -1 to 3, that's going to be a union. And then it is going on. So there is a break here. There is a break at 3. Then from 3 onwards, it goes up to infinity. So this is united with from 3 to infinity. You see that? So this is going to be my domain of f positive g. Now the same concept is valid even for subtraction, and for multiplication of functions. Let me define that. So if I've got f g of x, then this is going to be equal to f of x times g of x. So given the function, we are given that f of x is equal to root of x plus 1 and g of x is equal to 1 over x negative 3, then f g of x is going to be f of x root of x positive 1, g of x 1 over x negative 3. So this is going to be written like this. And the same principles of domain, finding the domain, applies even for multiplication. Now the next comes division. So in this case we got f of g of x, and that is going to be equal to f of x divided by g of x, and this only happens if g of x is not equal to 0. So that's a very important condition. Now if we were to use the same definition, or I would say the same expression given for f of x and g of x, then this is going to be equal to f of x is root of x positive 1 and g of x is 1 over x negative 3. So when we flip this is going to be root of x positive 1 multiplied with x negative 3. Now you might be tempted to say that, well, in this case I can have the domain 3 to be included. Say in this case 3 is not included, so we excluded 3 when we counted the domain for f positive g. But in this case, clearly if I were to take x is equal to 3, this is going to be 0, and 0 is perfectly acceptable. Not so. The reason being, we were able to arrive at this quantity because g of x was defined. The reason it was defined because clearly we had this 3 excluded. We did not include 3 at all. We took away 3 from this domain. The domain of g did not include 3. So the very fact we were able to arrive at this particular defined function is because we were able to divide the quantity f of x with a defined quantity, and that's why we were able to arrive at. And so the domain that we obtained when we found the domain of f positive g still holds good even for division.
Students, in this class we will learn about composition of functions. Now, to define composition of functions, a simple way would be to state the following. In composition of function, what happens is that the output of one function becomes the input for the other function. So if they are asking us to find f composition g of x, and we have g going from x to y, and in this case the function f would always start from y and it goes to z. In other words, the domain of f would actually be containing the range of g. So just to briefly describe what exactly happening in composition. So having mentioned this, there are a few formulae that you will have to know. So if I were to say f o g of x, so when we are stating this, the understanding for this is that we are trying to find f composition g. That's what we are trying to find, and that is equal to f of g of x. So how to say this? We say this as f of g of x. So this is how we say it. In this case we say this as f composition g, and on the right we say f of g of x. Now g of x is the inner function, and it will always be the inner function whenever we have this composition. Now on the other end, g of f of x, this is equal to, in other words I should say g composition f of x is written as g of fx or g of f of x. Now in this case f of x is the inner function. Now remember that f of g of x, or I would say f composition g of x, is not necessarily equal to g composition f of x. So the commutative law will not hold good here. So this is, you can't expect them to be equal. There might be situations where they can be equal, but now having mentioned that, let me show you an example how to obtain f of g of x. Now suppose you have f of x to be equal to, say, some x positive 1 squared, and g of x is equal to e raised to the power x.
then f composition g of x is equal to f of g of x, which is equal to f of g of x is e raised to the power x. Now wherever you got x, you have to substitute this e power x. So this is equal to e raised to the power x positive 1 squared. And what is this? This is f composition g of x. Now if you want to find g composition of x, g composition f of x, then this is equal to g of f of x. Now this is nothing but g of f of x is this quantity x positive 1 squared. So wherever we see x, we substitute this quantity. So this is equal to e raised to the power x positive 1 raised to the power 2. So clearly if I were to take this as 1 and I take this as 2, from 1 and 2, f composition g of x is not equal to g composition f of x. So we can also write it like this. So as I mentioned, commutative law doesn't hold good. Now we can also use other examples. We can say, for example, let me show you this. Given this is example 2, so you got f of x to be equal to 1 over x positive, say some 2, and g of x is equal to 1 over x positive some 3. Now for this function g of x, the domain is all x element of real number such that x is not equal to negative 3. So have that in mind. Now clearly g of x is defined and we are asked to find f composition g of x. Now this is nothing but f of 1 over x positive 3, and which is nothing but 1 over, in place of x we substitute this quantity 1 over x positive 3 positive 2, which is equal to 1 over 1 positive, I take x positive 3 as the LCM. So this is going to be 2 of x positive 3, which is equal to 1 over, in fact I can flip this, so this is going to be x positive 3 and this is going to be 2x positive, 2 times 3 is 6, 6 positive 1, 7. So you have got x positive 3 divided by 2x positive 7. So this is nothing but f composition g of x is x positive 3 divided by 2x positive 7. This is what we have got. Now the domain for this is 2x plus 7 is equal to 0, which means negative 7 divided by 2. So I cannot have an x taking this value. So x cannot be equal to negative 7 over 2. So if I were to write this as domain of f of g of x, this is going to be collection of all x element of real number such that x is not equal to negative 7 over 2. But I have already defined x not equal to negative 3. So you should also include that, and x is not equal to negative 3, because if this is defined alone, we are able to perform this f composition g of x. So without g of x being defined, we would not be able to obtain this, because g of x is the inner function. So have that in mind.
Welcome students. In this class we will be studying about inverse of a function. Now imagine we have a function which is going from x to y such that every x element of x as a y such that y is equal to f of x. So this is a basic function. Now what does this function do? It takes every element of x and it connects to subsequent elements in y. Now what will f inverse do? F inverse will actually reverse the operation done by this function. So f goes from x to y, f inverse will go from y to x. So the meaning is, if I were to take the composition of f with f inverse, then this would be same as taking the composition of f inverse with f, and the composition of f inverse and f will actually give me back the x. So the understanding that we need to have here is, whatever effect f has produced on x, it will be totally reversed back when f inverse acts on it. So that is the understanding. Now the best way to understand this would be by an example. So imagine, I'm going to use this illustration. Now you all have learned how to convert Celsius to Fahrenheit and Fahrenheit to Celsius. So this is totally two different ways to measure the temperature of a place. Now we have given a formula for Celsius, that is C of x is equal to 5/9 of x negative 32. Now if you are given a temperature of a place to be as say 77 degree Fahrenheit, then you want to convert this temperature into Celsius. So what would you do? You would take this value and substitute it here. So C of 77 Fahrenheit is now equal to 5/9 of 77 negative 32. So 77 negative 32 would give me 5 and 4. So 5/9 of 45. 9 divides 45 5 times. So this is going to give me a value of 25. So if I were to conclude or make a inference, I can state here that 77 degrees Fahrenheit is now converted into 25 degrees Celsius. So for this I've used this formula. Now what if I want to convert 25 degrees centigrade to Fahrenheit? What would I do? So I've got a formula for this. So that formula is f of x is equal to 9/5 of x positive 32. This is the formula. So therefore if I were to use 25 degrees here, this is going to be 9/5 times 25 positive 32. 5 divides 25 5 times. 9 times 5 is 45 plus 32. This is going to give me 77. So what is the conclusion here? 25 degree Celsius is converted into 77 degree Fahrenheit. So if I were to show you pictorially, what is happening here is 77 degree Fahrenheit. When I apply the function Celsius, C of x, it gets changed into 25 degrees centigrade. So now from here on, when I apply the function f of x, 25 degree Celsius gets converted into 77 degree Fahrenheit. So both these functions annul each other's effect, leaving what we call as identity. So what do you mean by identity? Say for example, you take 7 added with 0 is same as 0 added with 7, which is equal to 7, and in this case we call 0 to be the addition identity. So that means there is no effect at all when 0 is added. Now if I were to multiply 7 with 1, and that is same as multiplying 1 with 7, leaving me 7. So 1 is the multiplicative identity. Right, so there is no effect at all. So that is exactly what is happening when we combine two functions which are inverses to each other. Now clearly you can see here 77 degree Fahrenheit will lead us just to 25 degrees Fahrenheit. So if I want to reverse it, it is possible. So what do we understand? The basic understanding here is F inverse is only possible if the function f is 1 to 1. So I'm writing down here, it should be 1 to 1. So that means what? Every element, say I've got A, B, C. This A, B, C should have an unique element in the codomain. So if this is my domain, the elements in the codomain, say this is alpha, beta, gamma. A going to alpha should only go to alpha. That's it. B going to beta should only go to beta. In other words, A going to alpha and B going to alpha and C going to, say, gamma. This cannot have an inverse. Not possible, because two elements in the domain has got a same element in the codomain or in the range. As a function, we can have some real leniency because I've given you examples before. But when it comes to finding the inverse, this is a complete no scenario. So in other words, the reason being, we have to revert back to the original element. Now if a function is giving us this, say from A to alpha, if there is a function from A to alpha, the inverse function G inverse should be in a position to go back from alpha to A. So we should be able to retrace the origin. That is the utmost importance when it comes to an inverse function. So F inverse is only possible if F is 1 to 1. So 1 to 1 is also called as injective functions. So that is another name. So this is the important condition. If this condition is not existing, if this condition fails, then we would not be able to get back to where we want. Now this is a practical example. I will give you a function based example also. So students, we are given this question: verify algebraically that the function defined by f of x is equal to x over 2 negative 5 and g of x is equal to 2x positive 10 are inverses. Now this is the solution for this question. So the condition for inverses is, given f to be a function having f inverse to be its inverse, right? This is claimed. So then this would mean f composition f inverse of x would be equal to f inverse composition f of x, which in turn will be equal to x. So the final output should be x. We should get back this x, which is the element in the domain of the function. Now, having mentioned this, we are given that f of x and g of x. So let us consider f composition g of x, which is nothing but f of g of x.
and this should give us x. So this is equal to f of g of x is 2x positive 10, and this is equal to, substitute the value of 2x positive 10 into the function. So this is going to be 2x positive 10 divided by 2 negative 5, which is 2x positive 10. You take the LCM, is going to be negative 10 over 2. Positive 10, negative 10 gets cancelled, giving me 2x over 2, which is equal to x. Now consider g composition f of x. So this is equal to g of f of x, which is equal to g of f of x is x over 2 negative 5. I take this and substitute it into the function g. So it's going to be 2 times of x over 2 negative 5 positive 10. Distribute it, it's going to be 2 times x over 2 negative 2 times of 5 positive 10. This is 2 gets cancelled, giving me x. This is negative 10 positive 10, which is equal to x. So if I were to take this as 1, take this as 2, from 1 and 2, clearly we can conclude that f of x and g of x are inverses. So that completes the question, students. Students, we are given this question: if f of x is equal to 5x negative 3, find if f inverse of x exists. Now the condition, I'm going to give you the condition for f of x to have an inverse. So for that, if I were to take, say, any x1 and x2, so for any x1 comma x2, if f of x1 is equal to f of x2, then surely x1 should be equal to x2. Now what is the meaning of this? If I have two outputs which are equal, then they should have come from the same input. That is the understanding. So this is the required condition for a function f to have f inverse. So in other words, what are they trying to say? They are saying that f should be a one-to-one function, should be an one-to-one function. So what does it mean? For every element x present in the domain of f, there should only be one element or one f of x present in the codomain, or you can say range. It's up to you. So no two elements can have the same f of x in the range or in the codomain. The codomain is a better word. So that is the understanding if a function has to have f inverse. Now, having mentioned that, let me show to you that f of x is indeed a one-to-one function. So how do I do that? So let me just start like this. Suppose f of x1 is equal to f of x2. I got it like this. So that means 5 times x1 negative 3 is equal to 5 times x2 negative 3. Now add positive 3 both sides. So what happens when you do that? You get 5 times x1 negative 3 positive 3 is equal to 5 times x2 negative 3 positive 3. This one would give me 5 times x1 is equal to 5 times x2. Divide by 5 both sides. When you do that, what do you get? You get 5x1 over 5 is equal to 5x2 over 5. This would give me x1 is equal to x2.
So when we take f of x1 to be equal to f of x2, we land up obtaining x1 is equal to x2. So this means f is 1 to 1, and which in turn means f inverse x's. So that is how we show that. Now, having shown that the function has f inverse, why not we find out the inverse? So how do we go about finding the inverse? So this is how we do that, finding f inverse. So we are given that this is given, right? Given that f of x is equal to 5x negative 3. I rewrite this as y is equal to 5x negative 3. Then you solve for x. So that means move 3 to the other side. It will become positive 3 is equal to 5x. And then rewrite this as x is equal to y positive 3 divided by 5. Now you replace x by y and y by x. So now the inverse, f inverse of x is this quantity, x positive 3 divided by 5. Now if you are interested, you can do the check. So how to do the check? I'm going to use the space here to do the check. So what is the check? What are the check states? If f inverse of x is the inverse of f, then what should be true? F composition f inverse should be, maybe of x I'll place it, should be equal to f composition of f of x, and that would give me x. So the composition of f and f inverse should give me x. I can show that. So I'm going to use the space here. So I've got f of x to be equal to 5x negative 3. My f inverse is x positive 3 over 5. So I'm finding the composition of f with f inverse of x. So this is equal to f of f inverse of x. But f inverse of x is this quantity. So x positive 3 over 5. So I take x positive 3 over 5 and place it into the function. So this is equal to, I take the quantity here and substitute it into the function value. So that is equal to 5 times of x positive 3 over 5 negative 3. 5 gets cancelled, giving me x positive 3 negative 3. Positive 3 negative 3 gets cancelled, giving me x. Now also we need to find f inverse of f of x. This is equal to f inverse of f of x, which is equal to f inverse of f of x is 5x negative 3. I take this quantity, I substitute it here. So this is going to be equal to 5x negative 3 positive 3 over 5. Negative 3 positive 3 gets cancelled, giving me 5x over 5, which is equal to x. So in either of these cases I'm getting x. So this implies f inverse of x is the inverse of f of x. Students, in this class we will learn about exponential functions. Now we have already learnt about y is equal to x squared and how to graph it. This is a quadratic function and the graph would be u-shaped. Now what would it be if I were to reverse the position of 2 and x, and I would get something like this, 2 raised to the power x. Now this is called an exponential function. Now why is it called exponential function? Because we got the variable as an exponent. The variable is the exponent here. So that is why we call this as an exponential function. The exponential function is of the form f of x is equal to a raised to the power x. Now, what we are going to do is we are going to first graph the exponential function. So let us graph and learn. Graph y is equal to 2 raised to the power x and see what happens. Now, since x is an element of real number, x can take any values. Say for example, x can take values from 0, 1, 2, 3, 4 and so on. And on the negative side, it can take values as -1, -2, -3 and so on. So let us graph this function and see how it looks. So I'm going to start out with the coordinate axis x and y, and I'm going to take the value of x to be as 0. When x is 0, I get 2 power 0, which is equal to 1. So 0 is here. When x is 0, 1, if this is going to be 1, this is going to be the point. Now when x is 1, I get 2 power 1, which is equal to 2. So 2 is going to be over here. So this is going to be the point. When x is 2, it's going to be 2 raised to the power 2, which is equal to 4. So if this is going to be 3, which is going to be 4, this is going to be the point. Now when x is 3, 2 power 3 is going to be equal to 8, and if 8 is going to be somewhere over here, it's going to be moving up. Now clearly you can see that the graph is increasing exponentially. We started with 0 and then 1. When x is equal to 1, we got 2. From 0 to 2, and from 2 it went on to 4. Now from 4 it jumps to 8. Now when x is equal to 4, it's going to be 2 power 4, which is 2 times 2, 4, 8, 8 times 2, 16. Now when x is equal to 5, you get 2 power 5, which is 32. When x is equal to 6, 2 power 6 is 64. When x is equal to 7, 2 power 7 is 128. You see that how the increment is occurring? 16, 32, 64, 128 and so on. So the graph will be moving up. Now if I were to consider the negative end, say x is equal to -1, that's going to be 2 power -1, which is going to be 1 over 2. Now x is equal to -1, -2, -3, 1 over 2. 1 over 2 is 0.5, so that point is going to be over here. Now when x is equal to -2, it's going to be 2 power -2, which is 1 over 2 squared, which is 1 over 4. That's going to be smaller than that, right? Now similarly, if I were to take x is equal to -3, that's going to be 1 over 8. X is equal to -4, that's going to be 1 over 16. So the value of x, the function value, will be reducing as we move towards the negative end. So at one particular point of time, the graph would be something like this. So it will not touch the x-axis, but it will be closer to this x-axis, and we call this particular line to be an horizontal asymptote. And the equation for that, we give it as y is equal to 0. So this line is an horizontal asymptote for the function y is equal to 2 raised to the power x. So the graph of this line will never touch the x-axis, and that line, this straight line, is called the horizontal asymptote. It has the equation y is equal to 0. Now, so this is the graph of the exponential function y is equal to 2 raised to the power x. Now, we can have many such graphs. For example, we can have a graph of y is equal to 10 power x, where the value of a is 10, and so on and so forth. So we will study another example to understand the concept of exponential functions.
Students, let us graph this function, exponential function. So in this case,
we can see that the value of a is greater than 0, but it is not equal to 1, because the value of a is 1 over 2. Now we're going to take in the values and then graph it. So the positive side of the x-axis, and taking the value of x to be as 0, I get 1 over 2 raised to the power 0, which is equal to 1. So this would be the point. When x is equal to 1, it's going to be off. So when x is equal to 1, the value is going to be over here. When x is equal to 2, it's going to be 1 over 2 squared, which is 1 over 4. When x is equal to 2, 1 over 4 will be something over here. And then x is equal to 3 is going to be 1 over 8. It will be even smaller than 1 over 4. And x is equal to 4 is 1 over 16. So you can clearly see the value is reducing. So clearly the function, if you were to draw it, it would be just so closer to the x-axis, but it will never touch the x-axis. Now on the other end, let me take values for the negative side. So if I were to take x is equal to -1 on this end, x is equal to -1, this is going to give me 1 over 2 with a negative sign. That's nothing but 2, right? Similarly, x is equal to -2 will give me 4. X is equal to -3 will give me 8. X is equal to -4 will give me 16. So clearly you can see that when the values are going towards the negative end, the function is increasing. So x is equal to -1, it's going to be 2 here. X is equal to -2, 4, and 8, it goes on. So if you were to draw the graph would be something like this. So clearly you see that the function is tipping. The function will tip towards the right for this particular exponential function. Now there is a specific rule you can apply, and you can also see that the function as an asymptote as y is equal to 0. So just like the previous case. Now as I mentioned to you, there is a rule you can apply to find the tipping, whether the function is tipping towards the right or to the left, and that rule I'm going to give you here. Now imagine you got y is equal to a power x. Now if case 1, when a is less than 1 and x is greater than 0, the function will go down to the right. So the function will basically go down towards the right end when this is true. Now number 2, for the same thing, when a is greater than 1 and x is less than 0, the function will go down to the right. Now having mentioned this, there is another case. This is the next case. So let me write this as case 2. Now if we are given this exponential function and we got a to be greater than 1, strictly greater than 1, and the base, the exponent value x is also greater than 0, in that case the function will
rise up to the right. So what does that mean? It means, like in the previous case, we add y is equal to 2x, right? Y is equal to 2 raised to the power x, we add it in the previous case, and the graph was something of this fashion. So it was rising up on the right side. So the next case under this situation, when a is less than 1 and the value of x is less than 0, in this case the graph will again rise up to the right. So students, a very important note, which is in either of these cases the domain is all real numbers and the range is all positive real numbers. So students, in this class we will learn some variations of the graph y is equal to 2 raised to the power x. Now, as I showed you in the previous class, if this were to be x-axis, y-axis, and this is the point when x is equal to 0, you got the value of y is 1 there. So the graph is actually moving up like this. And this is 2 units, 3 units, and so on. Now imagine you are given, say, y is equal to 2 raised to the power x positive 1. So in that case, this graph actually gets a vertical shift of positive 1 unit. So that means instead of starting from here, instead of having an intersection over here, it would have an intersection over here. So the new graph would be having the intersection at this particular point. So if I were to draw that, it would be like this. So this would produce a vertical shift of 1 positive unit. So instead of having an intersection at 1, it will have an intersection at 2. Now what would be the situation if you have y is equal to 2 raised to the power x positive 1? What would be the graph? Because in this case the exponent gets an increment of 1 unit. So when that happens, the graph, I'm going to draw the graph here. So x-axis, y-axis. So usually we add this to be the intersection, like 0, 1. So this was the original graph. It went on like this. But instead of having an intersection at point 1, this point 1, the graph would now move from here. It would start from here. So this would be the shift. So it would have this to be the point and the graph would start from here. So the entire graph, instead of having the intersection at this particular point, this would be the point in which the graph would move. So this was going to be the shift. So we call this as the horizontal shift of negative 1 unit. So this is going to be the graph. Now, let us consider another illustration. Say y is equal to negative 2 raised to the power x. So what would happen? Now, let me draw the graph of y is equal to 2x, 2 power x. So this is the graph of y is equal to 2 power x. Now, for y is equal to negative 2 raised to the power x, there would be a reflection at negative 1 unit. So the entire graph, instead of going up like this, it would move like this. So this would be the graph. So we call this as reflection across x-axis. Now, if instead of placing the negative sign here, if you were to place the sign like this, y is equal to 2 raised to the power negative x. Now this is actually y is equal to 2 raised to the power negative 1 raised to the power x, which is nothing but 1 over 2 raised to the power x, right? So I have already shown you how the graph looks. So if you were to draw this, instead of having the reflection across the x-axis, the graph which I showed you for y is equal to 2 power x, which is moving like this, will be reflected across the y-axis. So instead of coming down for y is equal to negative 2 power x, y is equal to 2 raised to the power negative x will be on this side. So this would be the graph. So this is called reflection across y-axis, x-axis, y-axis. Finally, one last thing you got to know. If you have a coefficient, say y is equal to some m times 2 raised to the power x, then this will produce a vertical stretch. And on the other hand, if you have y is equal to 2 raised to the power some n times x, so this is a coefficient, this will produce you an horizontal stretch. So that is how we graph the exponential functions. Students, in this class we will learn how to draw logarithmic functions. Say you have a question like this: y is equal to log x to the base 3. Now, to obtain the logarithmic value for different values of x taken to the base 3 is quite a challenging, even if you were to use a calculator. So what we are going to do is we are going to change this logarithmic function into an exponential function. So how do we do that? Now I'm going to use this formula: log a to the base b, if it is equal to x, then a is equal to b raised to the power x. So using this formula, this is nothing but 3 raised to the power y is equal to x. Therefore we got a function something of this fashion: x is equal to 3 power y. Now what we are going to do is we are going to take in the values for y and find the values for x. Now it is imperative to understand that graphing this function x is equal to 3 raised to the power y will be same as graphing y is equal to log x to the base 3. So what I'm going to do, I'm going to take values for y and obtain the values for x. So I start with 0, I move to 1, 2, 3 on this side, and for this end it's going to be negative 1, negative 2. When y is equal to 0, I substitute, I get the value of x to be as 1, and when y is equal to 1, it's going to be 3, this is going to be 9, this is going to be 27. Now similarly for negative 1, when y is negative 1, it's going to be 1 over 3. So I just simply say 1 over 3 there. And when y is equal to negative 2, it's going to be 1 over 9. Now let's try to draw the graph for this function. x is equal to 3 raised to the power y. Now drawing the graph for this is actually drawing the graph for y is equal to log x to the base 3. So let me have these points as 1, 2, 3, 4, 5, 6. So in fact it would have been much better if it would have taken a bigger range. So anyway, since I've taken it like this, let me move on. 7, 8, 9, and the values of y, say 1, 2, 3, and this is going to be -1, -2, -3. This is 0. Now when y is -2, it's 1 over 9. So 1 over 9 will be very close over here. X is, and when y is -1, it's 1 over 3. So 1 over 3 would be a little bit further away. And when y is 0, it's 1. So this will be the point. And when y is 1, we have a point 3. So it's going to be over here. When y is 1, we have a point 3. And when y is 2, we have a point 9. So 9 is over here. When y is 3, we have a point 27. So 27 will be further away, right? So if I were to draw this point, it's going to be moving like that. So this is a beautiful graph for logarithmic function. So maybe you can put an arrow just to indicate that the graph is moving up. So this is how you draw a graph for logarithmic function, students. Now just extending, if you went to draw the graph for y is equal to 3 raised to the power x, now that graph would be something of this fashion. It will exactly cut at 1 and then it would move up like this. So if you were to compare this is y is equal to 3 raised to the power x. Now these two would be symmetrical along the x is equal to y axis. And not only that, these two functions, y is equal to 3 raised to the power x and x is equal to 3 raised to the power y, they are called as inverse functions. So that is some of the important points that you have to know, and we will move on to the next topic, students. Students, in this class we will review some properties on logarithms. These are some of the important properties you got to know in solving questions. Now one of the reasons that people like to use logarithms is because logarithms can change complex expressions into solvable expressions. So that is the reason logarithms are used in a greater fashion. And not only that, in comparison to exponential functions, logarithmic functions, they increase slowly. So that is also a very noteworthy feature. And the reason that, as I mentioned to you, their popularity is because they have the ability to transform a complex expression into simple, manageable and solvable expression. So having mentioned all this, let us state the first law. The first law or the rule would be log of 1 is equal to 0. Now the logarithms that I'm introducing here is called as common logarithms. Common log. And after I introduced common log, I will go on to demonstrate what is called as natural logarithms. The next one is log of a to the base a is equal to 1. Number 3 is log of m times n is equal to log of m plus log of n. This is called as the product rule. Law number 4, log of m over n is equal to log of m negative log of n. This is called as quotient rule. Now, law number 5, the exponent rule, or I would say the power rule. See, log of a over b is equal to b times log a. Number 6, the change of base. Suppose you got log of a to the base b. I can rewrite this as log of a to some base c divided by log of b to the same base c. So this is called as change of base, and this is called the exponent rule or the power rule. Now, having given you these rules, rule number 7, if you have any number x, I can rewrite that number x in form of logarithm. So that would be in this fashion. Say I can rewrite this as, with the base b, log of x with the same base b. So that would give you back that number. So this is an additional rule or tip I'm giving you. Now let us move on to the natural logarithms. Now there are few exceptions to use the natural logs when it comes to applying them, but when a situation arises, I will show you how exactly the log applies. So we represent natural logarithm with the symbol ln or ln. We call them as ln or ln. And since I mentioned to you, logarithms and exponential functions are inverses of each other. So in this case, when I say ln x, we are talking about ln to the base e. So the meaning of this is, this ln is actually the inverse of the exponential functions e raised to the power x. That is the understanding we have here. Now, to state the properties, what I'm going to do is I'm going to take a to be as e power x. So this would mean that if I take ln of a on both sides, I would get x here. In fact, I'm actually getting ln of e power x, but ln of e power x is nothing but x. Take it as y. This would be equal to y. So we got a to be e power x. That would mean ln a is equal to x, and b is equal to e raised to the power y, and that would mean ln b is equal to y. So having assigned the values for a and b, let's move on to obtain the property. So ln of ab. So ln of ab, this would be equal to ln a plus ln b. How did we get this? Let me just show you how exactly we have got this. Then probably you will be able to understand the proof better. Now ln of ab is nothing but ln of a is e raised to the power x and b is e raised to the power y. But I have shown you the exponent law, a raised to the power m times a raised to the power n is a raised to the power m positive n. By this property, this is ln of e raised to the power x positive y. Now, since ln and e are inverses, this is going to be equal to x positive y. But what is x? X is nothing but ln a is equal to x and ln b is equal to y. So this is equal to ln of a plus ln of b. On the left we got ln of ab. So this is the proof. Now we can also go on to do the quotient rule. So ln of a over b. So ln of a over b is nothing but ln of e raised to the power x divided by e raised to the power y. I can rewrite this as ln of e raised to the power x times e raised to the power negative y. This is ln of e raised to the power x negative y. But ln and e are inverses, so this is going to be x minus y. But x is nothing but ln a and y is nothing but ln b, and we got a negative sign separating them. So this would be the solution. On the left we got ln of a over b. So this is the quotient rule. So now I'm going to demonstrate the exponent rule. So which would be ln of a raised to the power, say, some k. Now I've taken a to be as e raised to the power x, and this subsequently I have shown you or we would have got that x is equal to ln of a, and also for b is equal to e raised to the power y, and I've got y to be equal to ln of b. We've already done this. Now from here, this is nothing but ln of a is e raised to the power x, so I'm going to substitute e power x. There is a k there. Now by exponent property, a raised to the power m raised to the power some k is nothing but a raised to the power mk. So this is equal to ln of e raised to the power xk. But I know that ln and e are inverses of each other, so this would give me x times k. But x is nothing but ln a, so I can rewrite this as k times ln of a. So that is the law that we were talking about, ln of a raised to the power k. Now one important thing, or one important feature that you have to know is that when we're dealing with logarithms, the domain is stretching from 0 to infinity. We cannot have negative values for domain in logarithm. So log of a negative value, negative number, doesn't exist. But for the range, it is from negative infinity to infinity. And that is why when we had the graph of logarithm, it was actually starting, or it was basically from the negative axis of y. This is y, this is x. We had negative values for y, and the graph actually overflowed on the negative end. So range is perfectly alright to have negative infinity to positive infinity, but in case of domain, the values should be from 0 to infinity without 0 being included.
Students, we got this question. Find the domain of ln of 3x negative 9. We know that the domain for logarithms are from 0 to infinity, and the range is from negative infinity to infinity. So this quantity 3x negative 9 should be greater than 0. So this would mean 3x should be greater than 9. If I were to divide by 3 both sides, I would get 3x over 3 greater than 9 over 3. And this would give me x is greater than 3. So that means when we were to graph this, the graph would be having a vertical asymptote. So if this is 1, this is 2, and if this point is 3, exactly at 3 we will have a vertical asymptote. Now why do I say that? If I were to take x is equal to 3, ln of 3 negative 9 vanishes. So that's the reason I'm getting x is greater than 3. So this would be the vertical asymptote. So this is going to be x is equal to 3. And to draw the graph, we know that log of 1 is equal to 0. So that means if I were to take 3x negative 9 to be equal to 1, this would mean 3x is equal to 9 positive 1, which in turn is nothing but 10. So this is going to be x is equal to 10 over 3, and that would be approximately, if I were to divide 10 by 3, 3 times 3 is 9, 1.0. So it will be approximately 3.33. It goes on like that. So if this is going to be 4, my graph is going to be having an intersection at this particular point, which is 3.33. So if you were to draw the graph would, it will have the same shape except for the shift that we have shown here. So that would be the solution for this question. Students, we are given this question. We are expected to evaluate this. We got ln of a raised to the power 4, b raised to the power 2 divided by c cubed raised to the power 3. So in this case, the input is raised to the power 3, and divided by ln of a squared b c raised to the power negative 3. The entire logarithmic term is raised to the power 2. So it is not the input is raised, but the entire logarithmic term is raised. So we got to be a little bit careful. Now we have
learned that ln a to the power of b is b times ln a. We know this formula. So from this formula I can rewrite this to be as 3 times ln of a raised to the power 4 b squared divided by c cubed. I can always have this. And also I know a formula, a ln of a over b is equal to ln a negative ln b. So by this formula, this is 3 of ln of a raised to the power 4 times b raised to the power 2 negative ln of c cubed. Now this can be further rewritten as, I've also known another formula. I'm placing the formula here because of lack of space. Ln of ab is equal to ln a plus ln b. So by that formula, this is equal to 3 of ln a raised to the power 4 positive ln b squared negative. So this is again the rule of exponents, or the formula which I've given you. Ln of a raised to the power b is b times ln a. Using that law, I can rewrite this as 3 times ln c. Now this can be further rewritten as 3 times of 4 times ln a by the formula positive 2 times ln b negative 3 times ln c. So this is equal to 3 times ln a is 3 units. So 4 of 3 plus 2 of ln b is negative 2, negative 3 of ln c is 4. So this is equal to 3 of 4 times 3, 12, negative 4, negative 3 times 4, 12. So positive 12, negative 12 gets cancelled. 3 times negative 4 will give me negative 12. So I've got this for the numerator. So let me write that down, numerator. Now I need to obtain the value for the denominator. So denominator is, first what we need to do is we need to simplify the quantity. So I've got ln of a squared b c raised to the power negative 3. This is what I've got, but this is raised to the power 2. So let me place that. Now this is equal to, if I were to use the product rule, this is going to be ln of a squared plus ln of b plus ln of c raised to the power negative 3. So this entire thing is raised to the power 2. So this is equal to, I can further rewrite this as 2 times ln a plus ln b, I can't do anything with that, negative 3 times ln c, and this is raised to the power 2. So this is equal to 2 times ln a. Ln a is 3 units. 3 units. So I place 3 units there. Plus ln b is negative 2 units. So I place negative 2 there. Negative 3 times ln c is 4 units. So I place 4 units. So this is all raised to the power 2. So this is going to be equal to 2 times 3, 6 units, negative 2, negative 3 times 4, 12 units. This is raised to the power 2. 6 negative 2 will give me 4, 4 negative 12 will give me negative 8. So negative 8 raised to the power 2. That will give me 64. This is for denominator. So therefore, numerator divided by denominator is equal to, numerator is negative 12, denominator is 64. So if I were to use 4, 4 divides 12 3 times, and 4 divides 64 1 time and 6 times. So 16 times. So 16 times 4, 24, 2, 64. So this is what I've got. So this is the final answer for this expansion.
Welcome students, in this lesson we will be studying some of the graphs of polynomials. Now when we talk about polynomials, we would be taking f of x is equal to a times x raised to the power n, where n takes values from 1 to 3 on and so on. Now foremost, we will be studying about values of a to be greater than 0, and in this case the degrees of n is going to be 1, 3 and 5 and 7 and so on like that. Now imagine you are asked to graph a function, say f of x is equal to, I'm taking the value of a to be say 1, and we got f of x is equal to x, so that is y is equal to x. So the graph of this particular function is going to be a straight line. This is the x-axis, and y-axis, of course, it passes through the origin. So this is the straight line graph. Now when n becomes equal to 3, then the graph changes. So let me draw the graph. The graph for n equal to 3 would be something like this. Now for n is equal to 5, now this is approximate graph for y is equal to x to the power 3. Now if I were to draw the graph for, say, let me just take this point to be as 1 and this point to be as 1. I want to draw the graph for y is equal to x to the power 5. Now you have to understand that y is equal to x to the power 5, y is equal to x to the power 7. In fact, for any odd powers, when n is odd, and we have a to be as 1, in fact it doesn't matter whether it's 1 or 2, it's just going to be the coefficient. What matters is the degree of n. Now when the degree of n is odd, all of the graphs will look like y is equal to x to the power 3. Have that in mind. But the only difference is they will tend to become more flatter, but as they go up at the edges, they will become more steeper. So y is equal to x to the power 5 will actually flatten, here, but when it is rising up, it will rise up more steeper than y is equal to x to the power 3. So if this is going to be the y-axis, so in this case it will be more flatter. It will be more flatter than y is equal to x cubed. So it is getting flattened over here towards the x-axis. But when it is coming down, it will fall much steeper than y is equal to x cubed. So this is going to be the graph for y is equal to x to the power 5. So that is the important point you have to know. Now if I were to draw the graph for y is equal to x to the power 7, then that graph, say for example, it will be more flattened, so it will be more flattened than y is equal to x to the power 5. But when it is rising up, it will rise up more steeper than x to the power 5 and x to the power 3. So this is going to be y is equal to x to the power 7. It's more steeper than x to the power 5 and x to the power 3, but more flattened than x power 5 and x power 3. And similarly, when it is coming, it is going to be more flattened than x power 5. And when it is coming down, it will be more steeper. So this is the best way to show. It will become more steeper than x power 5 and x power 3. So that is the guiding line that you should follow. So now let us study the graph for even powers. Say n is equal to 2, n is equal to 4, and n is equal to 6. Now we know the graph for y is equal to x squared. So if I were to draw the graph would be something like this. Y is equal to x squared.
Now is equal to x to the power 4. At the x-axis, the graph will become more flattened. So away from the origin, in other words, at the edges, y is equal to x to the power 4 will be more steeper. But at the bottom, it will become more flattened. So let me reiterate one more time. Y is equal to x to the power 4 at the edges will become more steeper. At the bottom, it will become more flattened.
Students, we are given this question, we are expected to graph this function. Now foremost, what you need to do is we need to find the highest power of this particular function. Now why am I interested in highest power? Because that highest power will give us the end behavior of the graph. So that's important. So in this case, clearly, if I were to take the highest power, x to the power 3 is the highest power, right? So we have already seen the graph of y is equal to x cubed. The graph is something like this, right? So if I were to compare this graph with this graph, then I have an idea that y is equal to x negative 1 times x plus 1 the whole squared will have the same end behavior. So what is the meaning of this? The meaning is at the end they are going to be rising up and ending at the positive quadrant for this side and ending here on the negative side with the third quadrant. So first quadrant they will be positive here, and towards the end they are going to be ending at the negative end. So that is what I have got, but other than that I've got no idea. So we are going to picturize how to obtain it. So the first and foremost thing for sketching the graph, find out the points. X minus 1 is equal to 0. I got x is equal to 1 here, and x positive 2 is equal to 0. I got x is equal to negative 2 here. So draw the number line. I got negative 2, I got positive 1. So find out the signs. So this is the sign diagram. So when x is say 3 on this side, I'm just going to this side first. Taking x is equal to 3, what happens? I get 3 minus 1 times 3 positive 2 whole squared. Now this is going to be a positive value. This is positive. Now having got this positive, let me pick up a value in this region, minus 2 and 1. So if I were to take x is equal to say 0, then it's going to be 0 negative 1 and 0 positive 2, and this is going to give me a negative value. So I have a negative here. Now if I were to take x is equal to say negative 3, then that's going to be negative 3 negative 1 negative 3 positive 2 whole squared. This is always going to be positive. This is going to, so that would mean the outcome is going to be negative. So this is going to be negative. So having obtained this information that between 1 and negative 2 the function is negative, and beyond 2 the function is negative, the only way it's positive is after 1. So getting that information, let us draw the graph. X-axis is 1 minus 1 minus 2. So these 2 points, and let me find out the y-intercept. I can get the y-intercept by taking x to be as 0, and that would give me, it's going to be negative 4. If this is going to be 1, -1, -2, -3, -4. So this is the point the graph is going to make an intersection. Now I know that the graph is rising up because after 1 we have already known the graph is positive, so it's going to go up. Now between 1 and -2 graph is negative, so it's coming down, hitting here, and then it will hit this point. Beyond 2, clearly the graph is going to be negative. Now the most important point is we do not know the behavior of the graph at this particular point. In other words, we do not know how far it is going down. So that vertex or that behavior is what is given by calculus. So we don't know how far it is dipping in and then where exactly it's climbing. We don't know that. That is where calculus comes in. So that change, the direction it is coming down, we don't know when or how far it's going to go down and rise up. That climb is the most important part in the graph. Of course, the end behavior we can find out using algebraic technique, but that behavior, or I would say that change in direction, can only be given by calculus. So of course over here it reaches here and then it comes down. So this is the graph for the function.
Welcome students. In this class we will be studying about asymptotes and poles. Now when we talk about asymptotes, there are 2 types specifically we will learn. One is called as horizontal asymptote and the other one is called as the vertical asymptote. Now today we will learn how to graph this rational function y is equal to 1 over x. Now this quantity y is equal to 1 over x is very strange, because when x is equal to 0, the function becomes undefined. So this is a challenging function in fact to graph. So I'm going to demonstrate it how to do that. First let us draw the coordinate axis x and y, and then let us take the points. So what I'm going to do is I'm going to construct a table and take values for x. So let me have x here and y here. So let me take values for x as -1, -2, -3, -4 and -5, and find out the values for y. Now when x is equal to -1, or let me just take this point as -1, +1 and +1 and -1, and move on with -2, -3, -4, -5. So when x is equal to -1, what happens to y? Y is 1 over -1, which is -1. So the point that we are talking about would be y -1. So this is the point. So let me place the point there. Now when x is equal to -2, we are going to get 1 over -2. This is going to be my y. So y is -1 over 2, and when x is equal to 2, -1 over 2 is 0.5. So that is going to be in the center, right? If this is going to be 0, so that point is going to be over here. And when x is equal to -3, y is equal to -1 over 3. So that is going to be still further down. Okay,
over here. When x is equal to negative 4, y value is going to be negative 1 over 4, and that is going to be still further closer here. Now as you move towards negative infinity, as you are moving towards negative infinity, when x value is going towards negative infinity, the function is actually becoming closer and closer to 0. So if I were to draw this function, you would see that the function is actually becoming closer to 0. So the function will be going towards 0 when x is moving towards negative infinity. Now let me just draw another table and find out what happens when x is going towards 0 from the left hand side. So let me write that down here. As x approaches 0 from the left, so we can also say left hand side. So x is actually moving towards 0 from the left. So that means x would have to take values in this fashion. So let me draw a small table here and place the values of x. So x is taking values like negative 1 over 2, negative 1 over 3, negative 1 over 4, negative 1 over 5, negative 1 over 6, values like this. And y would take, when x is equal to negative 1 over 2, say suppose I'm placing the value here, say y is equal to 1 over x and x is negative 1 over 2, that's going to give me negative 2 for y. So this is going to be negative 2, negative 3, negative 4, negative 5, negative 6, right? So when x is negative 1 over 2, somewhere over here, the value of y is going to be negative 2. So this is going to be the point. If I were to place here negative 2, this is going to be the point when x is negative 1 over 2. Now when x is negative 1 over 3, say further down, closer, that point is going to be negative 3. So that is going to be somewhere over here. I would say when x is negative 1 over 4, 1 over 4 is still further close, that point is going to be negative 4, closer. So as we stretch down towards, the line is actually heading towards negative infinity. As we are going still closer, next x value negative 1 over 5, y is going to be negative 5. So negative 5, if we were to place here as negative 5, this point is going to be still further close. So if you were to draw the graph would look something like this. So as x is going towards 0 from the left hand side, the function y is approaching negative infinity. So that is the understanding that we have here. Now let us consider the other side. Having the graph before us, let us consider what happens. So I need that space also. So let me use this space here. Let me take values of x as x is moving. In this case, x is actually going towards infinity. So let me write that down. As x is going towards infinity, what happens to the functional value? So what happens to y? Or instead of y, I can also use the function f. right? I can simply use f. So whatever you are convenient, you can either say y or f. Let me take values for x when x is equal to 1, when x is equal to 2, when x is equal to 3, when x is equal to 4, and when x is equal to 5. So when x is equal to 1, clearly I get 1, y is 1. So that point, when x is equal to 1, y is going to be equal to 1. That's fine. Now I need to stretch this further. So x is equal to 2, x is 3, x is 4, x is 5. And it moves, goes towards positive infinity. So when x is equal to 2, y is going to be 1 over 2, x is equal to 3, y is 1 over 3, and 1 over 4, and so on, 1 over 5. Now when you try to plot it, when x is equal to 2 is 1 over 2, that's going to be 0.5, and 1 over 3 is still further close, 1 over 4 is still further close, 1 over 5 is still further close. So if you were to connect it, your graph will be something like this. So clearly what you can see here is, as x is getting bigger, f is becoming closer and closer towards 0. So f is actually heading towards 0. This is the case when x is becoming large. Now having got that, let me draw one more table here. Let me draw one more table here for a better understanding. So this time, what happens is that as x moves towards 0 from the right side, from this side, okay, right hand side, what happens? So I need to take the values of x. So x is actually going towards this end. So the values that x would start with is 1 over 2, 1 over 3, 1 over 4, 1 over 5, and 1 over 6. In fact, I should have, okay, that's fine. So y will be 2, 3, 4, 5, and 6. So when x is 1 over 2, that's somewhere over here. The value of y is 2. So if I were to draw this point as 2, and let me stretch this a little bit, and this point is 3, this point is 4, you can clearly see when x is equal to 1 over 2, this is going to be the point. When x is equal to 1 over 3, this is going to be still further close, and 1 over 4 still further close. So if you were to draw the graph would be something like this, right? On either end, in this case, as x is heading towards 0, the function is going towards positive infinity. So we had three, or I would say we had four scenarios, right? When x is becoming or heading towards negative infinity, the function headed towards 0. And when x was going towards 0 from the left side, the function was heading towards negative infinity. And when x was becoming larger, function was heading towards 0. And when x was becoming smaller, heading towards 0 from the right side, the function was heading towards positive infinity. This is, over here we have positive infinity. So this particular graph has got two asymptotes. See, you see this line here, this is an asymptote. This is an horizontal asymptote. And this asymptote is y is equal to 0. Now you see a line here, the straight line. This is called a vertical asymptote. And this vertical asymptote is called as x is equal to 0. So there are two asymptotes for this particular graph.
Students, in this class we start off with learning how to spot the vertical asymptote.
So we are given this function y is equal to x over x squared negative 60.
And clearly we see that the function f of x vanishes when x is equal to, for example, I can rewrite this as x over x negative 4 times x positive 4. So the function will vanish when x is equal to positive 4 or when x is equal to negative 4. Now these two values cannot be part of the domain.
So vertical asymptotes are those values of x that are not part of the domain of the function. So clearly in this case, x is equal to 4 and x is equal to negative 4 are vertical asymptotes. So how do we represent that? So we draw the axis, x-axis, y-axis, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, and we have a dashed line like this. So these are the vertical asymptotes. Maybe you can probably write here x is equal to 4 and over here x is equal to negative 4. So we got two vertical asymptotes. So having talked about the vertical asymptotes, we are now going to look into horizontal asymptotes. Now, in case of horizontal asymptotes, there can only be one horizontal asymptote. Have that in mind. Just one is possible. In vertical asymptote, we can have more than one, but horizontal asymptote, only one is possible. And when do we have that one? I'm going to show you here. Now, if you can express the function in this fashion of a polynomial, say a times x to the power m divided by b times x to the power n. Please remember, the numerator and the denominator should be represented as polynomials. Otherwise this doesn't work. Now you have the degree here. Now case 1, when the degree of the denominator is greater than the degree of the numerator, when this happens, so when n is greater than m, then there is an asymptote, there is an horizontal asymptote, and that is given as y is equal to 0. So I'm reiterating one more time, when the degree of the denominator is greater than the degree of the numerator, where n is greater than m, there is a horizontal asymptote, and that is y is equal to 0. Now case 2, when the degree of the numerator is greater than the degree of the denominator, that is m is greater than n, the degree of the numerator is greater than the degree of the denominator, m is greater than n, then there is no horizontal asymptote. Now there is a third situation where the degree of the numerator is equal to degree of the denominator. When this occurs, then the horizontal asymptote would going to be the coefficient of the largest degree in the numerator. So that's going to be the coefficient of x to the power m divided by the coefficient of x power n. So in this case, y is equal to a over b will be the horizontal asymptote. So we have three scenarios, and I have listed out all of these three.
So students, having understood all of this, it is time for us to graph this function y is equal to x divided by x squared negative 16. So clearly we see that the degree of the denominator is greater than the degree of the numerator. So this would mean there is a horizontal asymptote, and that is y is equal to 0. So now we have found out the vertical asymptotes already. So let me place the axis. Now 1, 2, 3, 4. So this is the vertical asymptote. 1, 2, 3, 4. Negative 4, negative 3, negative 2, negative 1, 0. So this is, we got two vertical asymptotes. And this is the horizontal asymptote. So this is going to be y is equal to 0. Now how are we going to sketch this? Now to sketch the graph, it is enough that we pick up points closer towards the asymptotes on the left and points that are leaving the asymptotes. That means going towards negative infinity. And similarly, points that are approaching this asymptote, and then points that are approaching the asymptotes on this end, and then going towards positive infinity. So these are the points we need to really add to sketch this graph. So having mentioned that, what I'm going to do is I'm going to pick some points. So I'm going to pick points 3 over here, and then I'm going to pick up a point negative 3. So this is closer to those vertical asymptotes on the left, and this is closer to this vertical asymptotes on the right. And then I'm going to pick a point, say, away. So that would be, I can pick negative 5 or negative 6. So if I were to pick negative 6, I would also pick positive 6 on this side. So I can do that. So let me just show you how the graph works out. So foremost, what I'm going to do, I'm going to pick a point x is equal to 0. When x is equal to 0, function, I can always represent y as f of x. So f of x, let me write that down. F of x is equal to x over x squared negative 16. Will become 0. When x is equal to 0, function is 0. When x is equal to, say, a point closer, so in this case I will start with 3. When x is equal to 3, f of 3, let me find out what is f of 3. F of 3 is 3 divided by 3 squared is 9 negative 16. That is equal to 3 divided by, this is going to be negative 7. So this is going to be 3 over negative 7. So we need to find that value 3 over negative 7. So that is going to be negative 0.43. Now if I were to take this as negative 1, let me place these points 1, 2 and 3. Negative 1, negative 2, negative 3. So when x is equal to 3, we are getting negative 0. So that is going to be somewhere over here, right? Negative 0. So that means when we take x really closer towards the vertical asymptote, I'll give you one more demonstration. Say x is equal to 3.5. So 3.5 is closer to 4, right? So let me show you. F of 3.5 will be equal to 3 divided by 3.5 squared negative 16, which is 3 over. This is going to be 12.25 negative 16, and that's going to be 3 over negative 3.75, and that is going to give me negative 0.8. So negative 0.8, if 3.5 is over here, negative negative 0.8 will be a little bit away from this point. That's going to be negative 0.8. Now clearly the graph, when x is equal to 0, the graph is hitting 0 here, and then it will actually go down all the way, because as you increase the values for x as tending towards 4, the graph is going to be getting closer to this asymptote. So if I were to draw the graph would be something like this. It will be going towards. So now I have found out x is equal to positive 3 to be as negative 0.43. So x is equal to negative 3. So negative 3 is towards this asymptote. So x is equal to negative 3 would give me negative, in fact in this case when x is equal to negative 3, f of x in this case is going to be positive 0.43. It's going to be positive. So that positive sign is going to be over here. Okay, it's going to be over here. Now if I were to take a value, as I took the value x is equal to positive 3.5, if I were to take x is equal to negative 3.5, I would get the functional value of x is equal to positive 0.8. I would get it. I will get this value. So positive 0.8 would be still further up, right? So that's going to be over here. So if you were to connect this, the graph would hit here, and then it would go up. It will go up like this. So that's the way this graph is going to look. Now, what if x is actually moving away? X is going towards negative infinity and positive infinity. We have to find those values, right? So let me just use this space here. When x is equal to negative 6, the function f of x is going to be equal to negative 6 divided by 36 negative 16, and that's going to be negative 6 divided by 20. So this is the value that we have got. So let's check that value out. Negative 6 divided by 20, that's going to be 0.3. So negative 0.3. So negative 0.3 is going to be still closer over here. Negative 0.3 is going to be closer. Now if I were to take a value, instead of taking x is equal to negative 6, if I were to take x is equal to say negative 10, when x is equal to negative 10, I get the functional value to be negative 10 divided by 10 squared is 100 negative 16. So this is equal to negative 10 divided by 84, and that's going to give me negative 0.11. You see that the value is becoming smaller. So that means for negative 10 it will be even closer. It will be even closer to the asymptote. So this is, it's heading like this. It's heading like this. Now the question is, as we go towards negative 4, is it coming down? I want to know what happens to it when it's getting closer to negative 4. So in that case, I want to pick a value, say x is equal to, I can't take negative 4, so let me take x is equal to negative 4.1. When x is equal to negative 4.1, f of x is equal to negative 4.1 divided by negative 4.1 squared, negative 16. So this is going to be negative 4.1. I just want to show you the calculation. Divided by square. This is going to be 16.81, negative 16. So that's going to be negative 4.1 divided by 0.81. That's going to give me negative 5.0617. So you see there is an increment. So that means the value is going down. So if this is negative 4 and this is negative 5 and this is negative 6, when x is negative 4.1, the value is actually over here. So if I were to connect these points, the value is going to be going down. So why I needed have to take so many points, but I am taking all these points just to give you a better picture what is exactly happening in the graph. So we have got this part, we have got this part. Now negative 6 I have already taken here, so negative 0.3 I get. If I were to take positive 6, it's going to be positive 0.3, right? When x is equal to negative 6, I got negative 0.3. When x is equal to positive 6, it's going to be positive 0.3. So positive 0.3 is, this is 1. So positive 0.3 is going to be somewhere over here. And if you were to go closer towards, say, 4, so I took x is equal to negative 4.1. If you were to take x is equal to positive 4.1, it is going to be climbing up. So if this is 3 and this is 4 and this is 5, the value of positive 4.1 is going to be somewhere around over here, right? So if I were to plot this and connect this, the graph is going to be coming like this. It's going to be heading closer. You can check that out. So this is how the graph for the function looks, and you can also verify this graph using sign diagram if you are interested. Having mentioned this is heading towards positive infinity, negative infinity. So we will move on to the next topic, students.
Students, in this class we will learn and understand what it means when we talk about whole. Now, it is a point where the graph jumps and moves on. And why does it do so? In order to avoid division by 0. So that means to prevent the graph from being undefined, or to prevent the function from getting undefined, and that's why that jump takes place. Now the question comes, how do we find that whole? So let me just show you this example. I got this function f of x is equal to x squared negative 4 divided by x positive 2. Now if you can see this function, clearly people will immediately jump to say that this as a vertical asymptote. At x is equal to negative 2. This is what they would say. But actually this conclusion is inaccurate, because if I were to factor this function out as x negative 2 times x positive 2 divided by x positive 2, x positive 2, x positive 2 can get cancelled, giving me x negative 2. So this is my final function. So on seeing this function, the point where x or the denominator vanishes, that is what is called as a whole. So on observing, I'm writing it down here, on observing the original function, we see that when x is equal to negative 2, f of x vanishes, or f of x vanishes, right? So this particular value, so this means, this is all for your understanding, right? This means x is equal to negative 2 is a whole, and it is located at, how do we get the value of the whole? Now the reduced function is x negative 2, right? So substitute negative 2 here. So find out f of negative 2. So that's going to be negative 2, which is equal to negative 4.
So this means the hole is located at negative 2 comma negative 4. So how do we represent it in a graphical manner? So I'm going to use the space here. Now we got 1, 2, 0, x-axis, y-axis. This is negative 1, negative 2. Now when x is negative 2, y is negative 4. So negative 1, negative 2, negative 3, negative 4, just for consistency I'm placing 1, 2, 3 here. So when x is negative 2, y is negative 4. So that's going to be a point here. Now when you draw the hole, just draw it as an open circle. Now if I were to plot the graph, I need to plot the graph for this particular function, f of x is equal to x negative 2. So when x is equal to 0, if I were to take x is equal to 0, y becomes negative 2. So y is negative 2, so this is going to be the point. When I substitute y is equal to 0, so this is actually y is equal to x negative 2. When y is equal to 0, I get x is equal to 2. So at 2, there is this particular intersection, right? So if you were to draw the graph is going to be something like this, but when it hits a hole, it jumps and it goes forward. So this is how the graph will be looking. So this is the graph that we have drawn, and this is the hole. So maybe you can write that down here, hole, and the coordinates of the hole is negative 2 comma negative 4.
Students, in this class you will understand what it means by a vertical line test. Now this is used to identify whether we have a function defined or not. So what is the meaning of this? This means if you have a graph, you should be able to say that it is a function, and there are a lot of different types of relationships or different types of objects that look like functions, but they are not functions. So vertical line test gives us that quick way of testing whether any graph or any diagram that we see represented is a function or not. So what is the vertical line test? So if you were to draw a vertical line, then if the vertical line intersects the graph at just one single point, then we have a function defined. Okay, I think that's enough. Take some illustrations. So we have a curve like this. Say this is example number 1, and I'm drawing a vertical line. You see that intersection? The vertical line intersects at a point. That's it. So now let me take another example. So the popular example, a circle. Is it a function? If I were to draw a straight line, a vertical straight line, the intersection takes place at 2 points. So this is not a function. Not a function. Now if you have, say, another graph, something like this, and you draw vertical lines, you got a vertical line here, you draw a vertical line, you draw a vertical line. In each of the cases, the intersection is just 1. So this is a function, this is a function, this is not a function. Now imagine we have something like this. I draw a vertical line. You see that? This is not a function. So this is not a function. So
The vertical line is a good tool. You can follow this. Now, before I head to the next section, it is imperative to understand that two values of x can have a value of y. That's possible. So two values of x, say suppose you have a point, say 1 and 2, and this is positive 1. Now 1 and 2 are represented by a single value of y. This is possible. This can form a graph, or it can form a well-defined function. But remember, no two values of y can have a single x. So this is not possible. For example, I got 1 here and then I got 2 here. So 1 and 2 having a single value of x, say 2 is also going to 1 and 1 is also going to 1. This is totally should not occur, should never occur. So when this happens, the function, you can't call it a function. So students, in this class we will have a review of all the functions and graphs that we were dealing with, so that you will have a better picture what to expect. We have looked into this graph, mx, y is equal to mx positive b. Now this is a straight line, so you will encounter more too often graphs like this. This is a straight line, everybody knows. B is the y-intercept, because when x is equal to 0, when we take 0, this point is going to be the point where the graph hits the y-axis. M is the slope. We've already looked into how to get the slope for the graph, and having said that, this is going to be type 1 on, and then we move on. The next one is going to be y is equal to x squared. So this is a quadratic function and the graph is a parabola. So the graph would be a U-shaped graph. Now we also looked into y is equal to x cubed, the cubic graphs, and I've also shown you how to obtain y is equal to x to the power 5 and x to the power 7. And the graph would be starting from this end, it will hit the point 0, it will get flattened a bit, and then it will move up. So this is y is equal to x cubed, and then we got the y is equal to root of x. This is nothing but when I square, I get y squared is equal to x. So this is actually the part of a parabola when it is flipped. So that graph would be in this fashion. So this is the x-axis, this is the y-axis, this is y is equal to root of x. And then we got y is equal to 1 over x. I've also shown you this. Y is equal to 1 over x, and how this graph behaves. So this is going to be like this, x-axis, y-axis. So you got the horizontal asymptote and the vertical asymptote. So please be cautious, or please bear this in mind, that horizontal asymptotes need not always be the axis. Horizontal asymptote needn't always be the horizontal axis, or in this case be the x-axis. It is not hard and fast rule, because once we have a shift, if I were to place a shift for this function, say some quantity, some constant quantity, then the graph would shift. So from here it will move up depending upon the shift that we apply. So remember that horizontal asymptote need not always be the x-axis, and so it also applies the vertical asymptote. So I can just place the vertical asymptote also. So in this case, it need not have to be the y-axis that you see here. It can be anywhere. Horizontal and vertical asymptotes will depend on the function that we have got. So having mentioned this, let us move on. Now you will also encounter trigonometric functions. Say y is equal to sine x, cos x, tan x, and so on. Now the graph for trigonometric function will be something of this fashion. So when we do trigonometry, I will go in detail. So when it is pi over 2, it's going to be over here. The graph will hit 1 because sine pi over 2 is 1. So it will go through the origin and hit the point over here, and then it will curve up and down. So it's really a curvic graph that we have here. And when sine pi, when we take sine pi, it's going to be 0. So the graph would be like this. It's a curve shaped. So this is going to be negative pi over 2. So we will look into this graph as we do trigonometry. And next we will look into 6 and 7. We will look into y is equal to e raised to the power x. And this is an exponential graph. We already looked into this graph. So as x is increasing towards the positive infinity, the graph would climb, because when x is equal to 0, we got 1. So this is going to be 1 here. So 0 comma 1, this point is going to be 0 comma 1. So it will hit this point and it will move up, because the climb would be greater, and as it goes towards negative infinity, it will dwindle, it will become smaller and smaller. So this is what is going to happen for y is equal to e power x, and we have already seen this graph. And for log, it's going to be the reverse of it. So the graph will just going to be stooping down. I've already shown you how the graph looks for logarithmic, so let me show you that. So this is going to be 8. So the log, so y is equal to ln of x, and that graph would be some in this fashion. So this is the x-axis, this is the y-axis, and the exponential graph headed like this. The logarithmic graph will actually, because log 1, when log 1 comes, it's going to be 0. So it's going to be 1 comma 0 at this particular point, because if I were to substitute here log 1 will give you 0. So at this particular point, it hits here, and then it increases very, very slowly, and then as we move down, so y is equal to ln x. Now suppose you have y is equal to ln of modulus of x, that means we can also take the negative end. So in that case it would be the other side. It will be like what? Like a wing. So it will be going like this. So these are some of the illustrations of the graphs that we will be looking forward. Maybe. So finally, there is one last graph that we have already come across, that is y is equal to modulus of x, and that would be something of this fashion. At 0, there is no derivative, so the graph is a V-shaped graph. So these are some of the graphs that we will be coming across in the course.
Students, in this class we will be learning about transformations. Now there are two types of transformations. One is horizontal. So these are the two types we are going to be studying, and the other one is vertical. So for horizontal transformation, we take the function and we perform an operation inside the function. So it's something like this, f of x minus a. Now when this happens, we are actually producing a translation. So this is the change that the graph will undergo. Now
in case 2, suppose you are multiplying a constant inside the function, then we are actually performing a stretch to the graph. Now the third scenario, when we change the sign of x to negative x, then what we are doing is we are performing a reflection. So these are the 3 stages which a graph can be subjected. Now for the vertical direction, or for the vertical transformation, the first thing, f of, say, we perform the operation outside the function. It can be f of x positive a, or maybe, say, let me use another letter, b. So when this happens, we have a transformation that is taking place along the vertical direction. So this is going to be called a translation. So the translation is taking place along the vertical direction. Now for the next case, the function, the operation on the function is not done inside, as in the case of the horizontal transformation. It is done outside. So we multiply the function with a constant b. In this case, we perform a vertical stretch. Now finally, in this case, x has been changed to negative x, and we are getting a reflection along the horizontal direction. For this, we are taking a negative sign outside the function. So we are obtaining a reflection along the vertical direction. So this is what I call is the art of any transformation if you want to perform. So having got that out, let us move on. So students, we are going to perform some horizontal transformation for the graph y is equal to x squared. Now remember that when a is positive, the shift takes place on the right. A is negative, the shift takes place to the left. Now we know that the graph of y is equal to x squared is of this form. Now if I were to take example, so let me have this example. Say y is equal to x negative 6 whole squared. Now in this case, clearly a is positive, a is equal to 6. Now performing this translation, the same graph would move towards the right 6 units. So it's going to be starting from 1, 2, 3, 4, 5, 6. So this is going to be the starting point of the graph, and that's it. All you need to do is to just find out the value of a and perform the shift. Now if in case you are asked to draw the graph, apply the horizontal transformation for y is equal to root of x. So how would that occur? Say for example, they are asking you y is equal to, say, root of x positive 2. So in this case, a is actually negative, right? A is negative because f of x negative a. So we are having x positive 2. So that is only possible if a is negative 2. So when a is negative, the shift will be taking place towards the left. So let me draw that. Let me draw first y is equal to root of x. So y is equal to root of x is actually, this is the graph for y is equal to root of x. Now if I were to move towards left, so from here I need to move 2 units. So negative 2 is over here, negative 1 is here. So moving, the graph would actually start from negative 2 and it will move on. So this is going to be y is equal to root of x positive 2. What we have to do now is to obtain the stretch. Say for example, you got f of, say, 3 times x and you are performing for this function f of x is equal to x squared. So in this case f of 3 times x is going to be 3 times x the whole square. Now remember that with this constant, if you draw the graph would be becoming more narrow. So this is the graph for y is equal to x squared. This is the graph for y is equal to x squared. But for the graph y is equal to 3x squared, this is actually nothing but 9x squared. So if you were to draw the graph would be very narrow. This is y is equal to 9x squared. Now if we were to take the reflection part, I have not given you the reflection part, f of negative x. If we were to apply the reflection part, f of negative x, then it's going to be same as x squared because this is an even function. So we can't have much in this fashion. But if I were to take the reflection for y is equal to root of x, in this case this is f of x is equal to root of x, so f of negative x is root of negative x. So if I were to take the reflection in this case, then the graph for it's going to be the values for which this function will exist only will be on this side, only on the negative side. So y is equal to root x, this was the graph for y is equal to root x, but y is equal to negative root of x, the graph would actually start, it will be something like this. It would be the reflection on the other side. So this is y is equal to root of negative x, and y is equal to root x is going to be this. So clearly we can see that y is equal to root of negative x is going to be the reflection of y is equal to root x. So these are some of the important concepts that you will have to know. We will do more questions when we go to this topic.
So students, in this class we will look into vertical transformations. So that's what we are going to see. So let us talk about f of x positive b. Now in this case I am going to take a function of this fashion, y is equal to say x squared negative 2. Now y is equal to x squared is this regular graph, right? This is y is equal to x squared, the x-axis and y-axis. Now y is equal to x squared negative 2. What we need to do is we need to move the graph down by 2 units. So this is going to be 0. Now this is negative 1 and negative 2. So we move the graph 2 units down. So the graph would be starting from negative 2. So this is how the graph would look for y is equal to x squared negative 2. So having obtained this, let us see what would happen if I were to take it for the function f of x is equal to root of x. Say I want f of x is equal to root of x positive 2. So because this is the quantity is added outside, so in this case I want to draw the graph of f of x is equal to root of x positive 2. Now we know f of x, right? See, f of x is actually this. F of x is equal to root of x would be in this fashion. So because when x is equal to 0, it starts from 0, right? But f of x is equal to root of x positive 2. That means the graph will have to be shifted up. So in this case the graph will move up by 2 units. So if you were to draw the graph, this is 0, this is 1 unit, this is 2 units. So the graph will actually start from here and it will move up. So this is y is equal to root of x positive 2, or you can call it f of x is equal to root of x positive 2. So let's try to graph this function, students. So we know that y is equal to x squared is a U-shaped parabola because the value of a is greater than 0. Now in this case we get negative sign
So that means it's going to be inverted U-shape. And first we will start by observing the quantity positive 3. Positive 3 means this parabola is going to be shifted towards the left by 3 units. So it's going to be negative 1, negative 2, negative 3. So this is going to be the point for this parabola. But it's not going to be U-shaped because of the negative sign. It's going to be inverted U-shaped, and we got a scalar multiple of 2. That means it's going to be narrower. Now this presence of negative 4 is going to push the parabola down by 4 units. So that means it's going to be negative 1, negative 2, negative 3, negative 4. So this is going to be our parabola. So if you were to graph this, it's going to be something of this fashion. So that completes our topic on graphing. So the idea is, if you know some of these basic graphs and the table that I've given you before, even though someone is going to be giving you a complicated question, no matter what the question looks or how complicated the question looks, still you will be able to arrive at the solutions. So the bottom line is, make sure that you understand the basics, and then you'll be able to handle questions of greater complexities.
Students, in this class we are heading to trigonometry, and we are going to study the graphs of sine function, the cos function, and the tan function. And you can always call it as sine theta, cos theta, and tan theta, or sine x, cos x, or tan x. Now we start with graphing the sine function. Say sine x, as I mentioned to you, you can also call them as sine x, cos x, and tan x. So I will be drawing the graph of sine x, and the domain is all real numbers. So that is what you have to know. And of course, the sine function oscillates between negative 1 and positive 1. So these are the values that sine x takes. So having mentioned that, let me draw the graph of sine x. So you got x, you got y, and you got 0. So I'm going to divide it in multiples of pi, and you got 2 pi there, and this is going to be, we are going to need this 3 pi over 2, this is going to be pi over 2, this is going to be pi, is going to be 2 pi, it's negative, and it's going to be negative 3 pi. Okay, that's okay. So over here you got pi over 2, over here you got negative pi over 2, this is going to be negative 3 pi over 2. Now when x is equal to 0, sine is 0. So when x is equal to 0, sine x is equal to 0. Now when x is equal to pi over 2, sine pi over 2 is 1. So let me have that 1 over there. So when x is pi over 2, sine as 1 there. So negative pi over 2 is going to be negative 1. So let me draw the negative 1 here. So that's going to be over here. Now at pi, when x is equal to pi, sine pi is equal to 0. So that is going to be the point there. When x is equal to 3 pi over 2, sine 3 pi over 2 is negative 1. So that is going to be over here. Now let me try to connect these points. So positive 3 pi over 2, the next is, let me also place this point. X is equal to negative 3 pi over 2, sine of negative 3 pi over 2 will give you positive 1. So that is going to be over here.
and 2 pi is going to be 0. Sine negative 2 pi is going to be 0. So that's going to be here. So the question now is to connect these lines in a waveform. So make sure that you are getting a wave. Okay, so that's fairly acceptable. So f of x is equal to sine x. So just to make sure that the points, so just to make sure, so x is equal to 0, sine 0 is 0, x is equal to pi over 2, it's going to be 1, and sine pi is 0, sine 3 pi over 2 is negative 1, sine 2 pi is 0, sine negative pi over 2 is negative 1, sine negative pi is 0, sine negative 3 pi over 2 is 1. So this is the waveform for the sine function, students. So we will go on to draw the cos function also. So students, in this class we will graph the cos x. Now let me draw the x-axis, y-axis. Now I'm going to start with 0 and then I'm going to divide it into pi and 2 pi, and this is going to be negative pi and negative 2 pi. This region is going to be pi over 2, 3 pi over 2, pi over 2 with a negative sign, and negative 3 pi over 2. And let me have this point as 1 and this point is negative 1. I'm taking it a little bit larger because it will allow me to graph the function in a manner that it's acceptable, so this is x-axis and y-axis. So what we are going to do now is we are going to take the values for cos x. Remember that cos of 0 is 1. These are standard values you need to know. Cos pi over 2 is 0. Cos is an even function. So whatever goes for positive pi over 2 will also go for negative pi over 2. And cos pi is negative 1. So in this case cos of 2 pi is going to be positive 1 and cos of 3 pi over 2 is going to be 0. So this is all we need to get the graph. So these are all some standard values. It will do good if you could have this in your memory, and we can go on. So cos 0 is 1. So cos 0 is 1. So this is going to be the point. Cos pi over 2 is going to be 0. That's the point. Negative pi over 2 will also be 0. Cos pi is negative 1. So plot that point here. Negative 1. Cos 3 pi over 2 is 0. Cos 2 pi is going to be positive 1. So that's going to be over here. And the graph will hit down, okay, at 5 pi over 2. So if I were to have 5 pi over 2 there, it will hit down. So this is negative pi, cos of negative pi. Now cos of negative pi will be negative 1 because I told you cos is an even function. So cos of pi is negative 1, cos of negative pi will also be negative 1. Cos of negative 3 pi over 2 will be 0 and cos of negative 2 pi will be 1. And this is going to be negative 5 pi over 2. Cos of negative 5 pi over 2 will be 0. So the graph should be drawn in a waveform. So let's do that. So the graph comes here and it will move up. So that is the graph of y is equal to cos x. So students, in this class we will draw the graph of y is equal to tan x. Now y is equal to tan x, unlike other graphs of sin x or cos x, is not going to be in this fashion. So we have to know that tan x can also be written as sin x over cos x. Now we have studied about vertical asymptotes, and those are values for which the domain becomes or the domain vanishes. Now in this case, whenever cos x becomes equal to 0, the domain vanishes. So those are the points that we would take as vertical asymptotes. So the points where cos x becomes equal to 0 will give us the vertical asymptotes. So that is the first and foremost thing that we need to get, vertical asymptotes, right? So where are those points? And that could be got from the graph of cos x. So we can clearly see that at pi over 2, at 3 pi over 2, at 5 pi over 2, and similarly at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. So let's draw that. So I'm going to draw the x-axis and then the y-axis. So let me just mark these points as we start with, say, pi. So let me give some space and write that down. So I need a bigger space, so let me stretch this off. So pi, and this is going to be 2 pi and 3 pi. So this is negative pi, negative 2 pi and negative 3 pi. So this region is going to be pi over 2. This is going to be 3 pi over 2. This is 5 pi over 2. This is negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. So when x is equal to pi over 2, cos x becomes equal to 0. So these are the asymptotes. So we have an asymptote here, we got an asymptote here, we got an asymptote over here. Similarly, there is an asymptote here, vertical asymptote, a vertical asymptote here, a vertical asymptote over here. So we will draw these vertical asymptotes first. So and similarly negative pi over 2, negative 3 pi over 2 and negative 5 pi over 2. So this is the point. So these are all the vertical asymptotes. Now next we will have to look at, now we just saw that y is equal to sin x over cos x. Now next we need to look at those points where the function becomes equal to 0. So when x is equal to pi, sin x, sin pi becomes equal to 0, right? We know that. So those points will be occurring in between pi over 2 and 3 pi over 2. So these are the points where the function becomes equal to 0, and it also becomes equal to 0 here, it becomes equal to 0 here, it becomes equal to 0 here. So if we were to draw the graph would more or less be the graph of the cubic function that we come across. So that means it would start off along the vertical asymptote, then hit this point and move up. Now along with this, there is one particular point we need to look in, that is positive 1 and negative 1. So this point is 0. So before we could move up, let us just make sure to place all the points where the function becomes equal to 0. The function is also 0 at this origin. When x is equal to 0, sin x is 0. So if we were to draw the graph would be something of this fashion. So this is the rough graph of tan x function, students. So now we will try to get the graph of y is equal to cot x. Now students, we are now going to draw the graph of y is equal to cot x. We know that cot x is cos x over sin x. Now what we are going to do is we are going to look for all of the points where sin x becomes equal to 0. So that means the domain of the function perishes. In other words, the function perishes at these points. So those points and those points will give us our vertical asymptotes, right? So we want that first. So we know that when x is equal to 0, sin x or sine of x is equal to 0 is going to be 0, and sine pi is 0, sine 2 pi is 0. So let's get those points on. So this is going to be my x-axis, my y-axis. So this is going to be 0, pi, 2 pi, 3 pi, negative pi, negative 2 pi, negative 3 pi, and this is going to be positive 1, negative 1, and these are the points that we are looking forward. So sine pi is 0 here, and 2 pi is 0, 3 pi is 0, negative pi it's 0, negative 2 pi, negative 3 pi. So let me draw these asymptotes first. So I'm going to use dotted lines. So the points between these 0 and pi is going to be pi over 2. This is going to be 3 pi over 2 and 5 pi over 2, negative pi over 2, negative 3 pi over 2, and negative 5 pi over 2. So probably I can okay. So having got this, what we are going to do is we will find out those points where which cos x becomes equal to 0. So that means the function becomes equal to 0. So these are the points. So pi over 2, 3 pi over 2, and then 5 pi over 2. So in this case it's pi over 2, 3 pi over 2 with a negative sign, and negative 5 pi over 2. So these are the points where the function is going to become 0, because cos x will be 0. So now if we were to draw the asymptotes, it is going to be the reverse fashion that we had for tan. So it's going to be coming like this and moving down. So let me get that. So it's coming along the asymptotes, and it will take a curve, and then it will flow down, but it will never touch the vertical asymptotes. So that's the case. And then so this is the graph of the cortex function, students.
Students, so we've been continuing our review on trigonometry, and in this case we will start off with the right triangle ratios. So most so often we are given this right triangle, and this side is called as hypotenuse, and this is taken as theta, and the side opposite to theta is called as the opposite side, and this side is called as the adjacent side. Now if I were to take this as A, B, C, then sine theta is going to be opposite side over hypotenuse side. Cos theta is equal to adjacent side over hypotenuse side, and tan theta is equal to opposite side over adjacent side. Now if we were to write them in terms of sides, then this is going to be equal to BC over AC and AB over AC and BC over AB. So this is how we can write them. Now having mentioned this, we should also know a very important theorem, which is called as Pythagoras theorem, or formula based on the right triangle. So that is going to be given as AB squared positive BC squared is equal to AC squared. Now this comes in very handy if we were to look to find the distance between 2 points. So if I were to take a point, say x1 comma y1, and another point, say x2 comma y2, and we need to find the distance d between, say, point A of x1 comma y1 and point B of x2 comma y2, then we can use the Pythagoras. What we need to do is to find the delta x component and delta y component. Delta x is going to be x2 negative x1, delta y is going to be y2 negative y1. If we were to use the Pythagoras, then the distance d is going to be given as d squared is equal to delta x squared positive delta y squared, which in this case is going to be x2 negative x1 raised up over 2 plus y2 negative y1 raised up over 2, and this is equal to d squared. This is the most famous distance formula, which is also rewritten as d is equal to root of x2 negative x1 whole squared positive y2 negative y1 whole squared.
So it is also imperative to mention here is theta is taken to be as degrees in these measures, but we cannot do calculus taking theta to be in degrees. So to handle that, what we need to do is we need to take always theta to be in radians, in radian measure. This is important. Now let us now talk about the unit circle. Now unit circle, why is it so much important? Because in unit circle every theta can be associated with a real number. That is why we are using the unit circle. So when I say unit circle, the radius is 1 unit, and with this unit circle we can use or we can solve so many problems, and it becomes very important to understand this unit circle. So we got a circle of, say, radius 1 unit, so it's going to be something of this fashion. Now we are taking a point, say x comma y, and this measure is going to be r, and this is going to be theta, and this is going to be 1 unit. Now the idea is, if I were to drop a perpendicular and make this as 90 degrees, then I can easily obtain the ratios for cos and sine. So this is going to be y, and this distance is taken to be as x. And if I were to take, say, cos theta, so cos theta is equal to x divided by r, and r is going to be 1 unit here, right? So let me write this as r and rewrite it as x over 1. So from here I can clearly say that x is equal to cos theta. And similarly, if I were to take sin theta is equal to y over r, which is equal to y over 1, and that would mean I have y to be equal to sin theta. Now of course we have obtained this by our understanding of the trigonometric ratios, right? But these two equations are actually taken as definition in calculus. Have that in mind. So when we are talking, or when we are studying calculus, x is equal to cos theta, y is equal to sin theta is standard. So that is the understanding that we have got. Having made that as a point, now let us just move on. Now we know that theta is actually the angle between the radius and the x-axis. Clearly we can see that, right? And that we are actually measuring theta in radians. Now as I mentioned to you, we require a unit circle because every value of theta can be associated with a real number. So that means we can always be in a position to connect cos theta and sin theta to a real number. So that means we are talking in terms of function, and once we talk about in terms of function, we would be able to understand what the function is doing. So that means the behavior of the function can be studied, and with that we have greater insights. So with theta being in radians, that gives us that advantage. Now as I mentioned to you, we need unit circle to associate every value of theta with a real number. And how do we do that? I take a point here, I take a point here. Let me represent that particular distance. So I'm talking about this distance. It's an arc to be some value of s. Now I am taking this region actually. So if I were to take this region, then clearly I can write s to be equal to some r times theta. So this is possible from circular geometry. S is equal to r theta. Now r is nothing, s is nothing but this arc length, and r is the radius and theta is the angle. So r is equal to 1. So this means s is equal to theta. So this in turn means that every angle is identified with s, which is nothing but a real number. So that is how we are able to identify every angle theta and associate it with a certain S, which is in turn an element of R. So in short, this produces an association, and that association is every angle is actually a number, or every angle is associated with a number. So what exactly does this mean? So this means we can now think of x is equal to cos theta, y is equal to sin theta as functions, just like we studied exponential functions, logarithmic functions, polynomial functions, and that is what we are trying to achieve. So the reason that we are trying to move in that direction is that for the simple fact that we want to do calculus with them, and that is why that we are so much determined in making sure that our theta is treated as a radian measure. So another vital advantage is that whenever we are talking about the right triangle, we are only limited to angles between 0 and 90 degrees. So that is a great disadvantage. When I have theta to be in radians, I can literally think about any angle of theta, and there is no limitation. So in other words, because I am going to be thinking about the angle for theta in terms of radian measure, and that means I can think of any quantity on the unit circle. Say for example, if I'm thinking of this thing, this to be a point, this to be theta, and that means I can very well take a measure of this and associate cos and sine with that. And in fact, I can do this many number of times. I can simply take a point and move around this unit circle any number of times that I want, and I still be able to associate a cos and a sine. So that is a great advantage and flexibility when we are thinking or when we are treating theta to be in radian measure. Students, in this class we would be learning the unit circle and the coordinates. So that is also very important in our study on calculus. So let me draw a circle. So this is what we are going to be using. So I'm dividing it in. So this is going to be my x-axis. This is my y. So one complete revolution. So let me write that down here. One revolution in radian measure, in radians, is nothing but the circumference, right? So this is going to be the circumference, and that is given by 2 pi r, but we know that r is equal to 1, so that means 2 pi. So the value 2 pi is actually one revolution, which is nothing but 2 pi radians, and that is equal to 360 degrees. So this is what we have to know. Now if I'm going to start here as 0, and this is going to be written as pi over 2. Okay, let me place pi over 2 here. Pi over 2, and this is halfway mark, so this is going to be my pi, and this is going to be my 3 pi over 2, and this is going to be 2 pi. So we are going to be looking at the values of cos and sine. So first what I'm going to do is I'm going to divide this region into pi over 4, and then divide this into pi over 6, and divide this to pi over 3. So this is going to be pi over 3. So let me draw lines to connect these points. And then at this end, I'm going to have a division exactly symmetric to this point. This end I will have a division, and symmetric to this I will have a division. So this is going to be 2 pi over 3. This is 3 pi over 4, and this is 5 pi over 6. So I got to connect these points. And then this is pi, and then similar to this, I'm going to have a division. I'm going to have a division here, and I'm going to have a division here. So this is going to be 7 pi over 6. This is 5 pi over 4, and this is going to be 4 pi over 3. So I need to connect these points. So similar to this, I'll have a division here, I have a division, and then I'll have a division here. So this is going to be 5 pi over 3, and this is 7 pi over 4, and this is 11 pi over 6. So I have to connect these points. So this is a rough, I should have got it here. We need to understand the following, students. This is called as Q1, this is called as Q2, this is called as Q3, and finally we got quadrant 4. Now there are a few restrictions for these quadrants. I'm going to use the letter A here, and letter S here, and letter T here, and the letter C here. Okay, so you can suitably remember this by means of this saying, all silver teacups, or you can say all students take calculus, something like that. So whatever abbreviation you want, you can put it on. And I'm using this, all silver teacups. So that means all ratios are possible here. So when we talk about all ratios, we're talking about sine, cosine, and tan. All of these things will be positive in the first quadrant. This is the first quadrant. The first quadrant stretches from 0 to pi over 2. And here we got sine, cos, tan to be positive. From pi over 2 to pi, only sine is positive. And from pi to 3 pi over 2, so 3 pi over 2 is 270 degrees, only tan is positive. And from 3 pi over 2 to 2 pi, only cosine is positive in the final quadrant. So the question now comes is, how are we going to obtain the values for cos and sine for pi over 6, pi over 4, pi over 3, and pi over 2? So these are all standard angles. So we need to know these standard angles. So I'm going to place down here. Now sine 0 is 0. Cos 0 is 1. So that's why this point will often be represented as 1, 0. Remember, x is equal to cos theta and y is equal to sin theta. So this is the standard understanding in calculus. But we are not getting into it calculus, we are just view of pre-calculus, so that when real actual calculus comes, you'll be able to better apply these things. So this point is actually called as 1, 0. The next point that you will have to know is sine pi over 6 is actually sine 30. Now sine 30 is 1 over 2 and cos 30 is root 3 over 2. So this is a standard value, you will have to know that. And next value is sine 45. Sine 45 is 1 over root 2 and cos 45 is also 1 over root 2. And next is sine 60. Sine 60 is root 3 over 2 and cos 60 is 1 over 2. And finally sine 90 is 1 and cos 90 is 0. So this is the standard value that you will have to know to perform this completion of unit circle. So this is already obtained 1, 0. So over here I'm just placing the values down here because of the lack of space. So this is 30. First you write the cos coordinate. So cos 30, I've told you, is going to be root 3 over 2. So place that, root 3 over 2. Comma, sine 30 is 1 over 2. So I place the sine 30. Next is pi over 4 is 45 degrees. So that is going to be 1 over root 2, comma 1 over root 2. And this is pi over 3, that's 60 degrees. So cos 60 is 1 over 2. I'm placing 1 over 2 here, comma sine 60 is root 3 over 2. So place the value there. So moving on, 90, cos 90 is 0, sine 90 is 1. So that's how we place it. So we can go on to the next value, which is 120. So this is going to be 2 pi over 3. This is 2 pi over 3 is actually 120. So let me write down these degrees here. This is 120, this is 90, this is 60, this is 45, this is 30 degrees, and this is 0 degrees. So this is 120 and 135. This is 150 and 180 degrees. Now whatever value we placed for 60 degree would occur here. But the only catch here is only sine is positive, cos is not positive. So this 1 over 2 is going to be negative 1 over 2, comma, sine value alone is going to be positive. So root 3 over 2 is going to be there. Now whatever we place for 45 here is going to be occurring for 135. Sine alone is positive. So in this case the value is going to be negative 1 over root 2, comma 1 over root 2. Sine alone is positive, that's why it is. Now whatever I placed for 30 degree will be repeated at 150 degrees. So for 30 degree I add root 3 over 2, and this is going to be negative root 3 over 2, and sine is 1 over 2. Now coming to pi, so this is going to be cos of pi, comma sine pi. So that is going to be, sine pi is 0. So cos pi will be negative 1, comma 0. So this is going to be 1, comma 0, and this is going to be negative 1, comma 0. Now I will move on. So this is going to be 210 degrees. Now in this case only tan is positive. Now coming to 210 degrees. Now 210 degrees is going to share the same referencing as 150 degrees. The only thing is that only tan is positive. So this is going to be negative root 3 over 2, because sine is going to be negative, cos is going to be negative. So this is the value for cos. Cos is going to be negative, followed by sine, which is also going to be negative here. Now the next angle is going to be 225 degrees. Now 225 degree is going to share the same referencing as 135 degree. So in 135 degrees we have actually got negative 1 over root 2 and positive 1 over root 2. But in case of 225, both sine and cos is going to be negative. So that is going to be negative 1 over root 2, comma negative 1 over root 2. So that's going to be the value. And next, this is going to be 240 degrees. So this value is going to be 240 degrees. And 240 degrees is going to be sharing the same referencing as 120 degrees. In 120 degree we got negative 1 over 2 and 3 over 2. And in this case it's going to be negative 1 over 2, comma negative 3 over 2. And this is 3 pi over 2. 3 pi over 2 is nothing but 270 degrees. Now 270 degrees let me take these things off. So this 270 degree is exactly opposite to 90 degrees. 90 degree has got a value 0 and 1, and 270 degree is exactly opposite. So that is going to be 0, negative 1. So that's how you place the value there. Now these values are going to be, let me write this down. This is going to be 300 degrees. So let me place the 300 degree here. This is going to be 300 degrees. This is going to be 315 degrees. This is going to be 330 degrees and 360 degrees. Now 300 degrees and 315 degrees. So let me start with 330 degrees. 330 degree is going to share the same referencing as 30 degrees. In 30 degrees we had root 3 over 2, comma 1 over 2. So in this case cosine is positive. So this is going to be root 3 over 2, comma sine is negative. So negative 1 over 2. Now 315 degree is going to share the same referencing as 45 degrees. So this is going to be 1 over root 2, comma negative 1 over root 2. And 300 degrees is going to be sharing the same referencing as 60 degrees. So in the 60 degree we got 1 over 2, comma root 3 over 2. So this is going to be 1 over 2, comma negative root 3 over 2. So that is how we achieve the completion of this entire unit circle. So this is the completion, and we will move on to trigonometric identities.
Students, in this class we are going to look into some of the trigonometric identities which are important. And foremost, you have to know that cos of x minus pi over 2 is equal to sine of x. So this is critical. Number 2, sine x is an odd function. So what does it mean? It means sine of negative x is equal to negative sine x. So number 3, cos x is an even function. So what does it mean? Cos of negative x is equal to positive cos of x. Number 4, we are talking about the periodicity or the periods of sine x and cos x. Now for any n, say element of an integer, we got sine of x positive n times 2 pi will give you sine x, and cos of x positive n times 2 pi will give you cos x, and tan of x positive n times pi will give you tan x. So these are all the periodicity of the trigonometric ratios or trigonometric functions, sine x, cos x and tan x, which will come in handy when you're doing questions. Now the next important property that you will have to know, or identity, is sine squared x positive cos squared x is equal to 1. This is the famous Pythagorean identity, and from here we can also have 1 minus cos squared x is equal to sine squared x, and number 7, 1 minus sine squared x is equal to cos squared x. And if we are talking about tan x and secant x, we can also have something like this: secant squared x negative tan squared x is equal to 1, and from here we can also have cosecant squared x negative cot squared x is equal to 1. Number 10, from here we can very well say 1 positive tan squared x is equal to secant squared x. From here we can say secant squared x negative 1 is equal to tan squared x.
So from here we can say cosecant squared x negative 1 is equal to cos squared x. So from here we can also say 1 positive cos squared x is equal to cosecant squared x. So all these things are possible. Now, one of the most important ratio or trigonometric identity that you will have to know is tan x is sin x over cos x. Of course, we have used this, but just to be on principle, I'm placing them. And 15 is cot x is cos x over sin x. And then 16 is secant x is equal to 1 over cos x, and cosecant x is equal to 1 over sin x. Now there is another important formula which you have to know is sine of a plus b is equal to sine a cos b plus cos a sin b, and 19 sine of a minus b is equal to sin a cos b minus cos a sin b, and 20 cos of a minus b is cos a cos b plus sin a sin b. 21 cos of a plus b is cos a cos b negative sin a sin b. And moving on to tan of a plus b is equal to tan a plus tan b divided by 1 negative tan a tan b, and 23 tan of a minus b is equal to tan a negative tan b divided by 1 plus tan a tan b. So these are all called as compound angle formulae.
Now, apart from this, students, there are a few other formulae that you'll have to know, which will come in very handy when we're doing integration problems. They are sine to x is equal to 2 sine x cos x. This is a very important one. So this is formula number 24. And 25, you have cos 2x. Cos 2x is equal to cos squared x negative sine squared x. These are all power reduction formulae, which are very important. Now I can rewrite cos 2x by substituting for cos squared x, which is nothing but 1 minus sine squared x followed by sine squared x. So sine squared x added with sine squared x will give me 1 negative 2 sine squared x. So this is also a formula for cos 2x. So cos 2x can either be written as cos squared x negative sine squared x or 1 negative 2 sine squared x. So that is a very useful formula. Now you can also change this. Now this is equal to 1 negative sine squared x can be rewritten as 1 minus cos squared x. So that would mean this is equal to 1 negative 2 negative negative positive 2 times cos squared x. So this is going to be rewritten as 2 times cos squared x negative 1. Two more formulae. So formula number 26, which is sine squared x. Sine squared x is equal to 1 negative cos 2x divided by 2, and formula number 27, cos squared x is equal to 1 positive cos 2x over 2. Of course, all of these can be proved, and with this we will wrap up our review for pre-calculus students, and we will move on to calculus 1.